It's absolutely delightful to have all of you here. Some of you from literally across the globe, Steve from California, Yuki from Japan, and also all across the country, and some of you from across the street. So welcome to all of you to Quantum Gravity at RRI. This is a meeting where you'll see all approaches, or many approaches to quantum gravity. And we're very pleased that we have all of you coming here today. This is part of RRI's Platinum Jubilee celebration, 75 years since RRI was established. So we're extremely grateful to the Institute for the support for this conference, not just in terms of administration, but very massively in terms of the funding that they've procured. And this is from the Department of Science and Technology. It's been a very generous amount for this conference, which is why we have a very wide range of speakers coming to us from all over. I think that's pretty much all I want to say right now, and I would like to invite our director, Professor Tarun Sauradeep, to officially open the conference. Yeah.
Thank you, Sumati. So good morning. It's my great pleasure to welcome you all to Raman Research Institute, and particularly in this year when we are completing 75 years of Raman Research Institute. Also, I should mention that we completed 50 years as a Department of Science and Technology Institute, and we are the first autonomous institute of the Department of Science and Technology. So it's not a surprise that when we requested Department of Science and Technology that we should celebrate the Platinum Jubilee year with a lot of international conferences, which is largely reflective of what RRI does. We do research, and we want to bring researchers together. So this is, I think, the fourth of the 6 international conferences that are being held this year. And I'm really glad that my colleagues have put together such a, very rich and diverse, kind of participation from all angles to address the really frontier problem of quantum gravity. I mean, you define frontiers in many ways. There are frontiers which are, kind of quite visible, that it's something just, you need to work harder to surmount. Of course, I guess every one of you would have different views on quantum gravity, but now that I have been whatever number of years in research, when I came in, quantum gravity was something I was told is the hottest thing to work on, because that's the challenge. It still remains quite a bit of a challenge. I know a lot of progress has happened. And I'm also glad to see that there are a lot of approaches where people are trying to connect to cosmology, which is my own field. And that's for a good reason. I mean, that's one of the arenas where you can ever hope to check for what would be somewhat lower energy consequences of each approach. And I think as cosmologists, and this is already happening, I know some of the people who worked with us are now working with many of you. This is important because at the end of the day, we would like to have an approach, kind of supported a lot by some kind of evidence. And that is probably what is going to really decide the, way forward. And so I hope you will have a very fruitful and, vibrant discussion, as well as, I'm sure the younger colleagues here will learn a lot from the extremely esteemed colleagues who have come here. So I'm sure every speaker is esteemed, but I know some of them are really the absolute, almost legends in the field, and I'm glad they are here. and part of not only this conference, but of our Platinum Jubilee celebration. So welcome to everyone, and thank you. I hope you have a great conference.
Thanks, Tarun. We have a few minutes before we can start. I thought I'll just say a few words about how we've made as you can see with the timetable, that there's a lot of time for questions. There's a lot of time for discussion. And it's not a very crowded conference in this sense, and it's meant so that we're not in a hurry. Of course, all the speakers are given 50 minutes, but give or take a few. And we have enough time for questions. So please, especially the younger participants, please don't hesitate to ask questions, because this is what it's all about. So without further ado, even though we're early, is that a bad thing to start early? Maybe we can start, and I'll invite Madhavan to chair. My colleague Madhavan, so both of us have been organizing this conference, so I invite him to chair the first session.
Okay, so thanks a lot and welcome everyone. And as is well known, we are the most punctual country in the world. And in fact, we always start early. And so on that note, I think we have a fantastic lineup of speakers every day. And to get the conference rolling in swinging style, we have Professor Abhay Ashtekar, who has faced one storm and crossed two oceans, and finally is with us over here. And he will give an overview of quantum gravity in general and loop quantum gravity in particular. So Abhay, please.
As Madhavan was speaking, I was reminded of the poor old song. दुनिया ने हंसकर बुलाया लेकिन तस्वीर तेरी लेकिन लिए मैं तराया सबसे किनारा. So that's what happened with this conference. The tasbir was of the RRI, QG at RRI. Okay. All right. So I'm really very pleased to be here. I've known this institute for a very long time. And as Tarun said, that for celebration of 75th birthday, there is really a great activity in many areas of physics. And these are all forefront areas. And I also want to thank very much the organizers, Sumati and Madhavan, for bringing together experts in different areas of quantum gravity, different approaches, because I think that is what is really most needed. People are don't talk enough across the approaches, and so that's very nice. Okay, so my, as the title says, that I'm going to talk about mainly loop quantum gravity, but I want to begin with a general preamble and also end with a general statement. And I want to talk about status and outlook. So the organization is really this preamble with conceptual issues, and then distinguishing is a bit difficult to point, I guess. Distinguishing features of loop quantum gravity by itself, and then some illustrative examples. Unfortunately, I cannot cover everything because loop quantum gravity is over 35 years old, and there are tens of thousands of papers. So I had to select something. I was ambitious in the beginning. And so the only application I'm going to talk about is cosmology, and for reasons that Tarun already mentioned, that it really is an opportunity to make a contact with observations, and in summary and outlook. And I'm going to summarize work of many, many researchers. We were kind of these people and their groups up here. And this will be a rather broad review. Even then, as I said, I cannot touch on all the areas. But I just hope that I apologize in advance to people whose topics I could not do justice to. Okay, so preamble. Conceptual issues. As we all know, the problem of quantum gravity has been open for a very long time, And the question is, why is it open for such a long time? Now, there is an obvious answer, and that is to say that, well, somehow technology has not advanced enough, and therefore, we don't have enough observational data to guide us. But if that were the case, if you think about it for 2 seconds, you realize that it should be a theory's heaven, right? Because there are no observational constraints, so we should be churning out one theory after another every day without experiments constraining us. But we don't have even a single complete consistent theory, and then why is that the case? And I think that the real reason is that, oops, I'm sorry. What happened here? Now I go back. So I think the real reason is the following, that in general relativity, gravity is encoded in the space-time geometry, and the most spectacular predictions, the Big Bang, the black holes, and gravitational waves, emerge from this encoding. And this suggests that since gravity is the same as geometry, a quantum theory of gravity should also be a quantum theory of geometry. And so geometry itself should become quantum mechanical, and then if this happens, the big question is, how do you do physics without a classical background space-time at our disposal that we're used to in all other branches of physics? And we need really new concepts and new mathematical tools, and we have learned to lift this anchor which tied us to a background classical space-time relatively recently, and learn to sail the open seas. And there are several voyages in progress. Many of them are represented here, the ones which are in red. And I believe that this diversity is essential for this hard problem that we have got. Now, because there are no direct experimental checks, approaches are driven by intellectual prejudices. As all the experts know, there are something that they consider as being fundamental, and they feel that if that is solved, then other problems will somehow take care of themselves, because the fundamental core issue is really solved. But there is a big difference about what these core issues are, and these are really driven by intellectual prejudices. And well, but somehow it sounds strange that intellectual prejudice, it also seems so unscientific. Isn't science supposed to be all objective? And what's going on here? And I think that the really answer is given very eloquently in the opening remarks to the collected works of C.N. Young. He says that taste and style have so much to do with one's contribution to physics may sound strange at first, since physics is supposed to deal objectively with the physical universe. But the physical universe has structures, and one's perception of this structure, one's partiality to some of its characteristics and aversion to others, are precisely the elements that make up one's taste. Thus, it is not surprising that taste and style are so important in scientific research as they are in literature, art, and music. I think this is meant to be at the forefront of scientific research. When we are really exploring, we are unknown territory. It's like a voyage, in unknown lands, and we're trying to find this unknown lands up here. But as we explore this forefront of science, all this is true. Of course, what distinguishes science from literature, art, and music is that in science, nature is the ultimate decider. And this is again something that Tarun was saying. After all, the theory that we find, we should try to make observational predictions and either falsify the theories, or falsification is as important as proving a theory, because it really weeds out ideas. And if you have studied the history of quantum mechanics, which I did when I started doing loop quantum gravity, one sees this again and again. One has brand new ideas and one pushes them hard to the end until sort of they break. It's like you hit your head against a wall and then they just break. And then that suggests that we should do something else. I mean, that's how spin was discovered. That's how so many things were discovered. And that's what we need to do up here. And that is what really distinguishes between science from other things. And so now, this is the first part, very brief one. And now I would like to start with the second, longer part, which has to do with the distinguishing features of loop quantum gravity. So now I'm focusing on just one approach. And the first distinguishing feature is really that space-time geometry is emergent. Now, this is something that is, in a sense, well known to people who have followed loop quantum gravity, but in a sense, it's not. So what I'm going to say just now is, now in the next couple of slides, is something that is kind of known to people, but not with this particular perspective, which I think is very important and has led to really significant advances in the last few years, particularly due to Madhavan, and started with Alok, who is sitting in the room also. So at a fundamental level, the statement in loop quantum gravity is that at a fundamental level, what we have is not a theory of metrics at all. We have a background independent theory of connections. Now in the Hamiltonian framework, one can start with any of the frameworks, but I'm going to focus on Hamiltonian framework for the first few transparencies. So we need a phase space, and the phase space consists of SU2 valued pairs, which are complex valued, and then the basic variable is a connection and its conjugate momentum. So in Yang-Mills theory, this would be the Yang-Mills connection, this would be the electric field, and these are given on a 3-manifold M. Now, but unlike in Yang-Mills theory, now we don't have any background metric, and therefore, because we don't have a background metric, dynamics is really governed by constraints of the theory. So what we have to sort of scratch our head is, if you want to construct a Hamiltonian framework of a diffeomorphism invariant theory of connections, what you have to do is to try to find expressions, the functions on the phase space, which can be written down, which are gauge covariant and they are diffeomorphism covariant. They don't use any background structure at all. And it literally is true that if I take some bright student and put them in a room and ask them, write down the simplest functions you can, which don't refer to a background field at all, just A and E, and which should be gauge invariant, gauge covariant, and gauge invariant and diffeomorphism covariant, and they will just come up with these fields up here. One is really, the first one is just divergence of E, because divergence does not require a metric, it is just defined with respect to the background connection, and E is a density valued field, by the way, because electric fields are already density valued fields. So this object is completely well defined, just knowing A and E, and it is linear in E, and because of the covariant derivative, there is also linear in A. The second expression they can write down is just linear in E and quadratic in A, which is just take the electric field, construct the field tensor from A, and just contract the internal indices up here, and also the manifold index up here, and that leaves us a vector. So this takes values in the Lie algebra of SU2, and these takes values in one forms. And then finally, you can write down a scalar, which is just given by the structure constant of the group times E, E, and F, and this is quadratic in E and quadratic in A. And these are the only expressions you can write down which are at most quadratic in each of the phase space variables. And surprisingly, they automatically satisfy a first-class constraint system, a la Dirac. Now, there is no background metric, and therefore, the Hamiltonian is a linear combination of constraints. So the Hamiltonian would be given by taking a smearing field lambda, which takes values in SU2, and then taking a vector field and contract with this one form, and then taking actually this object for technical reasons is actually, those who are interested in technicalities, this is the density of weight 1, so this object is density of weight 2, therefore this object n has to be a density of weight -1, so that the whole thing is integrable without reference to a background metric. So this is actually a density of weight 1, and therefore I can integrate it without reference to a metric. So this is the Hamiltonian. If these are the constraints, this is the Hamiltonian. By the way, the next complicated term that you can write down gives you the cosmological constant, and I could have added it, but I just wanted to make the analysis as simple as possible. So this is our Hamiltonian for the background independent theory of connections, and then therefore one is led to ask, well, what does this Hamiltonian generate? Well, the first term is just the Gauss constraint, therefore it generates gauge transformations. The second term is a vector field, and then which is contracted with this vector or covector one form constraint up here, and what that generates is really gauge covariant lead derivatives along the vector field V up here, vector field N that I got up here. And then therefore the question is now, what do the final term, what does that generate? Well, that is a sort of important question, and the recent surprising result that I obtained with Madhavan is really that the third term generates a generalized gauge covariant Lie derivative. So it also has a geometrical interpretation as a generalized Lie derivative up here. Now normally the Lie derivatives are generalized by vector fields, and gauge covariant Lie derivatives are also generalized by vector fields. The expression of the Lie derivative, which is gauge covariant, just involves replacing ordinary derivative operator with a gauge covariant derivative operator. So the gauge covariant derivative, Lie derivatives, require the knowledge of a connection as well. So this is already true at the, oops, I don't know what I do, I press it too hard, I think, that's why. So the statement up here is that the, okay, this is the gauge covariant Lie derivative up here, and then the one can ask what does it generate, and it just this symbol up here with double line, and that's a Lie derivative, but it is generalized gauge covariant derivative. I call it generalized because it is not generated by a vector field, but rather it is generated by triplet of vector fields, and the triplet of vector fields is just given by taking the lapse and contracting it with the electric field up here, and therefore sometimes it is called but the final answer is really a shift because it is a vector field. So this object which is a vector field in space time in the three manifold and has an internal index is called the electric shift. And furthermore, in the final picture, as you will see in a minute, this Lie derivative, which is such a simple object up here, turns out to be precisely the time evolution of general relativity. And thus, the time evolution is really transmuted to space evolution along this electric shift up here. Because the canonical transformations generated by constraints are all just generalized gauge covariant Lie derivatives, as we will see in a few slides, the Poisson algebra of constraints is remarkably simple. It is a natural generalization of the Lie algebra of the diffeomorphism constraints, and this has led to a major advance in the Hamiltonian dynamics in just the last few years. Okay. So, how does, yeah?
On the fiber bundle structure, these are just standard Lie derivatives or?
So the gauge covariant Lie derivative is a standard Lie derivative, which is just left up here. And I'll talk about the generalized gauge covariant Lie derivative, so that's one of the interesting mathematical questions. So far, of course, you would say, okay, this guy has constructed a theory of connection. It's a background independent theory of connection, but what does it have to do with gravity, right? I mean, we're interested in metrics and what happens? Well, it turns out that both in the Lorentzian and Euclidean signature, general relativity emerges as two real sections of this gauge theory phase space. And again, I'm not giving the technicalities, how it happens, I'm just stating this fact, and we can discuss this if you have questions up here. And there is a precise dictionary from this phase space to the phase space of ADM variables, which consists of three-dimensional metrics and its canonically conjugate momenta, which is basically extrinsic curvature, multiplied by square root of q, which is to give it a density weight. So the statement is that if I go back up here and look at these constraints that I had, namely the vector constraints up here and the scalar constraint up here, these constraints, and now the ADM variables are gauge invariant, so the statement is that, so I don't want to worry so much about the Gauss constraint, and then the statement is that, in fact, these simple constraints just become, the CA that I wrote down is just the divergence of PAB, which is the ADM vector constraint, and the other constraint I wrote down up here, which is just EEF up here that I wrote down up here, is in fact the ADM, the scalar constraint. Now in the ADM scalar constraint, the sign here depends on which signature I have, and this signature just comes out automatically from the dictionary. So in the phase space of the gauge fields, I just have one phase space. I don't have Euclidean phase space and Lorentzian phase space, different constraints or something. I have two different real sections, and this dictionary maps one of them to the Euclidean sector and the other of them to the Lorentzian sector. And then the evolution equations, again, notice the evolution equations, these were just the generalized, these were the generalized gauge covariant Lie derivatives. These expressions are so simple up here. They in terms of the ADM variables become these extremely complicated expressions that we all know of, namely the Q dot expression is not that complicated, but in fact the P dot expression is extremely complicated because it involves non-polynomial functions of the basic variables, inverse of the metric and the determinant of the metric, etc., etc. So this complicated expression is just really just the generalized gauge covariant Lie derivative. So the right hand side is so complicated and non-polynomial in the ADM variables. So why is this the case? Well, this is simply because in terms of the basic connection variables, these are composite fields. You need nonlinear, non-polynomial combinations of the basic variables to come here, and therefore the equations in terms of these composite fields are extremely complicated. And this analogy is really with nuclear physics. I mean, we got QCD. QCD is very simple, but nuclear, the neutrons and the protons and their interactions and multiple in the nuclei, which are multiple protons and multiple nuclei, of course, it's very rich, but it's also very complicated. And the viewpoint is the same thing is true. So the analogy is that QCD is like the connection dynamics, background independent, and nuclear physics is like the metric description in terms of the ADM variables. And now we got this generalized gauge covariant commutator between two vector fields, and this is just given by what I explained a while ago. You take the ordinary Lie derivative. In the ordinary Lie derivative, this would have been a partial and partially here, whereas now it is replaced by a gauge covariant Lie derivatives up here. So this is the big difference up here. But the important thing is that the vector fields that we're talking about, V and W, V, U, V and W, they all have internal indices, and the commutator has now two internal indices. So what happens is that this is really a graded Lie algebra. This is really partial answer to your question. It's a graded Lie algebra, and this is an infinite dimensional. So the question is really, is there an infinite dimensional analog of the graded Lie group? Now, if one couldn't find this infinite dimensional graded Lie groups, and this is an invitation to all the mathematical minded people in the room, then you would have found the content of entire Einstein dynamics, complete vacuum Einstein dynamics. You can also add the matter fields, and the structure there will be more fields, but the structure will be similar. They will involve just these Lie derivatives. So at the moment, this generalized gauge covariant derivative is defined via this operational method of Garrosh and Penrose. You make the definition in terms of the operations that you actually use rather than geometrical ideas, and then one can show that for ordinary Lie derivative and for the gauge covariant Lie derivative, one can show that the operation corresponds just to diffeomorphisms on the manifold or on the bundle. Here we don't know what corresponds to, and that is an open question. What is the geometrical meaning of this? Now I have got a conjecture, namely it actually is just a Lie derivative, but an associated bundle whose fibers are infinite dimensional, they involve internal indices, arbitrary number of internal indices. And that is why the structure is so rich, and that is why it can contain the full content of Einstein's equation. Okay. So this is the emergence of GR. And now the statement is that looking at GR as a theory of connections, then the statement is that we were led to quantization. And now in these steps, yeah.
Sorry, two naive questions. So this triad that you introduced is it invertible?
It doesn't have to be invertible, but to make the contact with it is only the invertible sector that makes contact with general relativity. So the other equations, you have more general equations when these electric fields, which are interpreted as triads, if they are not invertible, the equations are still well defined, and actually that enables you to actually evolve just classically across some singularities like the Big Bang, where the triad is not invertible because scale factor goes to 0. Same thing is true at the Schwarzschild black hole singularity. So one can actually use this equation to give an evolution across the Big Bang. When you are across the Big Bang or across the Big Crunch singularity or the Schwarzschild singularity, again the metric is invertible, this triad becomes invertible, and you can continue. So that gives you a generalization.
One more question. So this real sections that you talked about, can I choose some crazy real section plus, minus?
I don't know. That's a good question. So I not thought about it. So it's a good question. So what we do here is really proceed in the same steps that Einstein did when he discovered the general relativity. Einstein first recognized that in fact what we should do is to fuse the Newtonian potential and the Minkowski metric together to construct a curved metric, and that curved metric incorporates gravitation, and therefore the language of classical physics with gravity should be Riemannian geometry. And that is a natural syntax to describe classical physics in presence of gravity. And then subsequently, the next several years later, actually he found the actual equations that determine this GAB. So this is sort of the syntax, and then this is the dynamics equation. In LQG, one uses the same steps, but now for quantum gravity. So the first step is to find the new syntax. What is the structure, the syntax in terms of which you want to describe dynamics? And the syntax up here is really the following. Because we have got a background independent gauge theory, that naturally leads to an algebra of observables, which is complete on the phase space, and these observables are called the holonomies and fluxes. The connections define holonomies, or if you like, the Wilson lines, and the fluxes, we have got these electric fields, and you look at fluxes of electric field across two-dimensional surfaces. So the holonomies are one-dimensional integrations of connections, and then we've got two-dimensional surfaces like that. Now there is a highly non-trivial result, which I think is really quite impressive, by Lewandowski, O'Connor, Salman, and Tiemann, and then also by Fleischach. Namely that if I look at the holonomy flux algebra, then, and of course you ask a background independent representation, then that algebra admits a unique background independent representation. Now this is a striking, there are also technical conditions which one also uses in Minkowski space field theories, but even with those technical conditions in Minkowski field theories, one does not have unique representation. There's infinitely many representations of the canonical combination relations or the standard algebra that one uses. So diffeomorphism invariance is really extremely powerful. And then the Hilbert space has been known for quite some time now. The Hilbert space is just the square integral functions of these actually generalized connections, because in quantum field theory, smooth connections always are set of measure 0. You need to have distributional or generalized connections. And then d mu naught is in fact a background independent regular Borel measure on the configuration space of the generalized connections. And the physically interesting operators are represented by well-defined self-adjoint or unitary operators on this Hilbert space. And then the rigorous these are all rigorous results, and there are no hidden infinities, and everything is background covariant. On this Hilbert space, geometrical operators have purely discrete eigenvalues, and thus Riemannian geometry is quantized exactly in the sense that energy and angular momentum are quantized for hydrogen atom. So this Riemannian quantum geometry, which is well developed and rigorous, is a syntax to formulate and answer physical questions of quantum gravity. Examples are black hole entropy, where the quantum geometry of the horizon, counting the microscopic states, is what gives in loop quantum gravity the entropy, and spin forms, which are really evolutions between one quantum geometry given by this by wave function in this Hilbert space and another quantum geometry, and that is what that is how the syntax is used to formulate physically interesting questions. Okay. Now, in particular, if I take any surface, mathematical two-dimensional surface, S, then there's an area of that surface, and that is a physical observable on the classical phase space. And similarly, volume of a region R is another observable, is a function on the classical phase space, because you have to give me a metric in order for me to calculate these objects. If you change the metric, the volume changes and area changes. So quantum mechanically, they become self-adjoint operators on the Hilbert space I talked about. And it turns out that the smallest non-zero eigenvalue of area, called the area gap, that plays a key role in dynamics. Why is this? Well, how do you define curvature? Normally, we define curvature given a connection by taking the holonomy around the closed loop minus identity, and then dividing by the area of that closed loop and taking the limit as the area shrinks to 0. In loop quantum gravity, the area has a minimum eigenvalue, so one shrinks it to this minimal eigenvalue. So that gives you at a certain non-locality at the Planck level in loop quantum gravity, and that changes the quantum dynamics enormously, and the area gap plays a fundamental role because the the curvature is defined using this area gap up here. And the volume operator plays a key role in the definition of the Hamiltonian constraint operator. Now, we got the geometrical observable, so you can look at the basis which diagonalizes it, and these self-adjoint operators, and this basis is called spin networks. So these lines up here are really like holonomies. But what one is looking at is making them into matrices by looking at a representation. So this is just SU2, therefore representations are spin labels, and therefore I get matrices up here, and then at the nodes where they meet, I just tie up all these indices that are free coming up here. So the index, I got two indices. So one is associated with this vertex, the second is associated with this vertex, and you tie up these indices at this vertex, and these are called intertwiners. So what we can, for this basis, you have to give a decorated graph. A graph, two-dimensional graph, with some information on the links and some information on the nodes up here. And this is actually a basis that diagonalizes these operators, and they really provide extremely powerful tool. I mean, most of things that we do could not have been done if technically, there's not a fundamental reason, but a technical reason. And that facilitates also the visualization of quantum Riemannian geometry. So given such a graph, so I've taken this graph, I couldn't draw this as complicated as here. So I've taken a simple graph with nodes and some nodes up here and some links up here. And what I do is I just look at the dual picture. So associated with every node, there's a chunk of space, and associated with every link up here, the link really intersects the surface, two-dimensional surface, and therefore the node is associated with the dual picture is a chunk of space, and the dual picture of the node is a surface. And that is why the label J that I talked about is really endows with the surface with the quantum of area J times the area gap up here that we talked about. So this is really the quantum geometry that we got in this quantum Riemannian geometry. And now we can talk about quantum dynamics. And let me talk about the Hamiltonian approach. In the Hamiltonian approach a la Dirac, the quantum dynamics is incorporated by solving the quantum constraint equations, namely they are imposed on the states up here. First, we have to give a precise meaning to the operator C hat I, and the LQG syntax or the kinematics enables one to write down these operators explicitly, because we saw that classically they're actually just gauge covariant lead derivatives or generalized gauge covariant lead derivatives. So we got a nice operation up there. And this issue is still open, making these operators rigorous is still open in the Wheeler-DeWitt theory. In the Hamiltonian general relativity, the structure of the constraint algebra ensures the four-dimensional covariance of the theory in the usual ADM framework, for example. And in the connection dynamics picture, the action of the Gauss and the diffeomorphism constraint has direct geometrical meaning as diffeomorphisms on the bundle, that as you were saying before, which translate to the Poisson algebra. But for the Hamiltonian constraint, which generally in terms of, if we write in terms of metric variables, then we've got structure functions, as is well known, namely two scalar constraints. Poisson algebra is a vector constraint, and the vector constraint has the structure functions, and that has make life very complicated. And the key question for quantum dynamics is the Poisson algebra of constraints faithfully lifted to quantum theory? And until recently, there were consistently liftings, but in these liftings, they were not faithful. They were such that, in fact, the commutator, C hat M and C hat N up here, as well as the right-hand side, they both vanished independently. So, of course, they are equal to each other, but there is an additional constraint, namely, additional condition, namely, they vanish independently. And so, on the appropriate space of states, the appropriate habitat. And this was not completely satisfactory because one wanted some faithful representation, which is also anomaly free, of lifting of the constraint algebra at the quantum level. So classically, we have got constraint algebra, and we would like to write down a quantum extension of the same kind, whereas this is not zero, but this actually is a vector constraint, and the vector constraint you have to write down explicitly. And this is really done recently, and this is a major advance of Madhavan. As I said, Alok had written a paper earlier on, but Madhavan has a series of papers, long 100-page long papers, very, very careful, very technically difficult, but he has really been able to show that in fact there is a lifting of the constraint algebra at the quantum level in the Euclidean loop quantum gravity. And this crucially uses the representation of the time evolution as a generalized gauge covariant Lie derivative. And this really is the climax of advances from simpler models over the last decade. And now that opens up the avenue to Lorentzian loop quantum gravity, because there is a generalized Wick transform that was proposed by Thomas Tiemann, me, and then also Madhavan. And then the statement is that one can hope to apply this to this Euclidean solution to obtain also solutions to the Lorentzian constraints up here. And this is the power of geometrization that I told you about before. Namely, I can just calculate the Poisson algebra between two scalar constraints, Cm and Cn. Now, if you do this systematically in the geometry of dynamics, for example, I think the most complete derivation is in Tiemann's book, but even there he leaves out some in-between steps for reader, and then even then it takes more than 10 pages up here. And this is the complete derivation, and all that is done up here is really expanding out what the E dot is. E dot was just the Lie derivative, generalized gauge covariant Lie derivative, and then after that you just do contractions of indices, and in the only non-trivial step you just do integration by parts. This ln is really brought outside to hit here, and so that's all we are doing here, finally. And when you have done that, the statement is that you just obtain an answer, and this is a complete calculation, and you find that the right hand side is a CV, and in terms of the connection variables, this CV is just generalized gauge covariant derivative of m, the smearing function up here, which is to say m is just m times E, this is the electric lapse, and similarly the smearing function associated with n up here. So it just the Lie derivative of n with n. So but the right hand side is equals the ADM structure, which is just this, but in fact it actually geometrizes it. And I guess we'll also hear from Wolfgang about using these connection variables to simplify things in the discrete setting. So, as I said, what Madhavan has done is really promoted the geometric action of the Hamiltonian constraint to full Euclidean loop quantum gravity. Okay, so let me come to the last technical part, or which is really what are the illustrative applications of loop quantum gravity. Now, in quantum, and that is loop quantum cosmology. So, in loop quantum cosmology, what one does is focuses on the cosmological sector of general relativity using symmetry reduction. In effect, one traces out all but a finite number of degrees of freedom and focuses only on observables of interest to the universe, large-scale universe. For example, the mean density or the scale factors, which are anisotropies, the curvature, and so on. So the immediate question that arises is that, isn't this a drastic simplification? Because you've got infinitely many degrees of freedom, and you have imposed symmetries and made it into a finite number of degrees of freedom. It absolutely is. But it is good to keep in mind the physical issues, namely what happened in the electrodynamics. We had the problem with the hydrogen atom. It's a fundamental problem, the simplest problem of quantum mechanics. And what Dirac did was to just say that, well, let us look at the spherical symmetric sector of quantum electrodynamics. Now, when you tell him that, you say, wait a minute, spherical symmetric sector? But there are no photons which are spherical symmetric, so you have thrown away all the photons. It's a ridiculous approximation. How can it have much to do with reality, with what quantum electrodynamics would actually predict? But of course, we know that Dirac atom predicts, it has all the relativistic corrections to it. It is, of course, not a final description, but it's a very, very good description of the hydrogen atom. It actually, to see the deviations from Dirac hydrogen atom, one has to go all the way to Lamb shift, when the vacuum fluctuations of the electromagnetic field become important. So for many, many observations, this is perfectly fine. And the hope is that the same thing would be true in cosmology, that for the observables that are of interest to cosmology, we really can do this reduction up here. So this is in loop quantum cosmology. What I said just now has to do just with any quantum cosmology. Now I turn to loop quantum cosmology. Here there is no unphysical matter. There is no classical there is no matter which classically violates energy conditions. And there are no boundary conditions such as Hartle-Hawking or Vilenkin boundary conditions appear. Rather, the quantum geometry effects change Einstein's equations, and then we can look at the consequences of these new effects that are added to Einstein's equation. And the distinguishing feature is that one uses methods from full loop quantum gravity to cosmological models. One does not just symmetry reduce and they say, well, I've got a finite dimensional system, therefore I just use Schrodinger quantum mechanics. No. One uses that representation, which is the complete analog of the Lewandowski-Okola, Salman and Thiemann representation. So there is again a uniqueness theorem, just as in full loop quantum gravity for this algebra, and that provides us a new syntax or kinematics and a new Hamiltonian constraint in place of the Wheeler-DeWitt equation. And here the area gap plays a fundamental role for the reasons I mentioned before. And you can think of dynamics as being relational, where scalar field can play the role of time. And what one finds is that the quantum geometry creates a brand new repulsive force in the Planck regime, overwhelming the classical attraction. The Big Bang is replaced by big bounce, and there is a maximum density in the quantum character space-time, and that maximum density is given by a formula here. There is a sup. On the physical stage, this is the upper bound on the density operator, and this sup is just expressed here in terms of fundamental constants that come here, and you can see that area gap comes in the denominator. So the area gap goes to 0, you get the classical result, also the result in Wheeler-DeWitt theory, where there is no area gap, that rho sup is equal to infinity, but here rho sup is now finite. So this has been analyzed in detail using Hamiltonian, path integral, and consistent histories of frameworks, and all strong curvature singularities are resolved in cosmological models.
Okay.
Yeah.
I wanted to ask you a question before you move to the next one. So if I am to take your analogy with QED seriously, then the success of QED is primarily because the coupling constant is very small. Is loop quantum cosmology, is it in some sense in the weak coupling limit of?
No.
Okay.
No.
So
because the success of
optimistic that why should we take the analogy seriously?
Right. It's an analogy. All analogies are incomplete. But the point is that in QED, the full QED is also perturbative. Here, full LQG is non-perturbative, and LQC is also non-perturbative. So one is going from non-perturbative to perturbative. So this perturbative aspect that appeared in QED is not relevant here. So that is why it does not appear in the analogy. I believe it's not important to analogy. I really think that LQC is the hydrogen atom of LQG. It is the simplest system where one can see what is happening, and then one can look at more complicated system, get intuition.
See, this manifold M, you must choose it to be R3 or?
So in this case, it can be R3 or S3 because we're looking at the or hyperbola. I mean R3 or S3 in the just for the cosmologies that one uses, right?
And such results are known for all Bianchi models, or?
It is known for the interesting ones, Bianchi 2, Bianchi 1, Bianchi 2, and Bianchi 9. I think maybe also Bianchi 8. The interesting ones, it is known for all this. In all those cases, one has the result that there is an upper bound. Okay. So now I just wanted to flash this for students and so on up here. There is a short 15 minutes video, YouTube video, which is called The New Meaning of Big Bang. And basically, the interesting thing is that they are interviewed us in completely different cities. And there's Roger, there's Stephen, there's also Vilenkin and Guth and Veneziano. And we're all interviewed separately. And we have followed different approaches, but we said exactly the same thing at the end, that Big Bang as a singularity is not something that is what is meant by Big Bang nowadays in cosmology. Big Bang is really the hot phase, if you believe in inflation, at the end of inflation, and that is what we mean by Big Bang, the hot phase. Not anything, nothing is infinite there. And this really came up in a detailed systematic way in LQG, and this is a Scientific American article about this, and students might like to see the different perspectives and why people come to this particular view. Okay, so now quantum geometry and its manifestations. Now quantum geometry in LQG is subtle. For example, the area eigenvalues crowd exponentially. So they're not like harmonic oscillator, they crowd, and therefore the classical limit can be obtained rather quickly. Now detailed calculations show that quantum geometry effects that dominate the Planck scale physics leading to singularity resolution can leave observable signatures on CMB. But they dissipate quickly after the bounce and become negligible already at the onset of inflation, where the curvature is about 10 to the minus 12 times Planck curvature. So quantum geometry manifests itself in 3 different levels. That's sometimes confusing to students, to younger researchers. The first is, oops, sorry, I keep doing this. Maybe we should just leave it. The first is a fundamental level, which is described by loop quantum gravity and spin networks, and that is associated with the geometric operators. The second is a coarse grain level, where one is interested only in a few microscopic observables, such as average matter density, anisotropies, or homogeneous part of the spatial curvature. And then the quantum geometry is described by a wave function that depends on a few degrees of freedom, such as the scale factor, the anisotropies, the matter, and so on in the early universe. And the singularity resolution is at this level. There are attempts to go from this level to this level. They are not conclusive, but that good progress has been made. And geometry is seen by quantum fields, which are propagating on this quantum geometry. So this is the quantum geometry, and the quantum fields, which represent cosmological perturbations, are propagating on this field. And very interestingly, it turns out that these quantum fields don't see all the detailed structure of this wave function. It only sees certain leading moments of this wave function, and which are captured in a smooth tensor field G bar AB, which is constructed by taking expectation values of this wave function in operators that appear in the Hamiltonian of the scalar field. And therefore, the coefficients of this metric G bar AB, they involve Planck's constant. So it's a smooth metric, but coefficients involve Planck constant. And this is appropriate for the CMB analysis. And very interestingly, this framework can be tested experimentally, because, for example, you can have light, and you can have electron in it. Now, light is normally treated classically, and the electron wave function is propagating in this classical electromagnetic field. But you can also consider coherent state of light, which has fluctuations in it, and we can say, well, what does the electron, how is the electron affected? To leading order, it is going to be just the usual thing, but in the but there will be quantum corrections, and that's what one sees up here. The analogy here is that the light is like the coherent state of the light is like this wave function psi, and the electron is like the cosmological perturbations. Yeah.
So if it takes it away from your talk, I mean, I have a live question. I mean, in quantum cosmology that, one at least I was familiar with, you took standard GR and then dropped degrees of freedom. So you basically looked at a homogeneous thing and all. But now you are working in a different space of classical variables. Now, is it clear what are you dropping in terms of the A's and E's?
Yeah. The homogeneity isotropy conditions can be easily transported to the A's and E's. Yeah, so we can talk about it. I mean, you can write down the answers, which is homogeneous and isotropic, or homogeneous and non-isotropic for Bianchi models on the A's and E's. Okay, so why does Planck scale dynamics matter? Well, contrary to widespread belief, the pre-inflationary dynamics does matter, because modes with wave functions which are much larger, whose physical wavelength is much larger than the radius of curvature of space-time at that time, they, in the pre-inflationary epoch, they get excited. Sorry, that too many, I'm sorry, but there's so many questions. So,
yeah, we have time, but if it's not directly relevant to the flow of the thing, then...
There was a mention of exponentially right crowding of eigenvalues. That I thought was reminiscent of the Hagedorn model, where also the density of states grows exponentially, and that gives you a upper limit of the temperature rather, I mean, just like there's a lower limit, there's also an upper limit. and it looks like connected to singularity resolution. I was wondering if there's a connection.
I don't know. I mean, I don't know the detailed connection because mathematics is quite different, but there could be quality. I didn't recognize it because of a beard.
So, yeah, so I propose that if there are really questions which are impinging on understanding of what Abhay is saying, then sure, ask them. But otherwise, we have lots of time for discussion, and you could raise the questions then.
Right. So the main point up here is that there is actually, what happens is that in ordinary, so what I'm plotting up here is really time scale, time here and length here. And in ordinary general relativity, if I look at the observable modes in CMB, their wavelength is always less than the radius of curvature up here. Whereas in loop quantum cosmology, what happens is that the wavelength, the longest wavelength modes in the observable spectrum, their wavelength is larger than the radius of curvature, because the radius of curvature doesn't go to 0, but rather the radius of curvature at the bounds is a finite one. And therefore these modes, the longest wavelength modes, get excited, and therefore by the time they arrive at the onset of inflation, the modes are not in the vacuum state, Budge-Davis vacuum, but they are in excited Budge-Davis vacuum, and therefore they can leave imprint on the cosmological, on the observations up here. And so the statement up here is that in LQC effects, they really are for physical lambda at the bounds, which is bigger than if the physical lambda at the bounds is bigger than the LQC scale, then these modes will get excited. So interestingly, there is an interesting interplay between ultraviolet and infrared. The singularity is resolved because of ultraviolet, but because of this radius of curvature, it is the longest wavelength modes propagating that are actually getting excited, that actually have interesting results up here. So what happens is the primordial spectrum itself changes. Basically, the longest observable mode is somewhere here, and the longest observable mode is up here, somewhere here, and the L equal to 30 mode is, for example, somewhere here. And so we have whereas actually a power suppression for longest observable modes up here in this range. These are just, if you like, these modes are not going to be observed, only up to here that will be observed. And so what happens is that instead of having an almost scale invariant power spectrum, the power spectrum gets modified, but this modification is only in this range that I talked about for modes which are less than the LQC scale up here, whose K is less than the LQC scale, or whose wavelength is larger than the LQC scale. And this power suppression then causes all kinds of interesting things. Namely, the LQC kinematics and dynamics use the same principles as in full LQG, but to make observable predictions, as in the standard inflation, additional inputs are needed to select the trace metric and the state of the perturbation. And these are provided by certain principles that I don't have the time to go into. I can explain them in the discussion session. The prediction is that with the standard inflation, with the standard inflation, there is overall excellent agreement with observations. So this is not LQC, this is just standard inflation. But there are some anomalies, and the statistical significance of any one anomaly is small, but two or more imply that we live in a very exceptional universe. For example, the Planck T itself has this quote from their 2018 results, which says that if any anomalies in the primordial origin, if any anomalies have primordial origin, then their large-scale structure would suggest an explanation rooted in fundamental physics. Thus, it is worth exploring models that might explain an anomaly, even better multiple anomalies naturally or with a few parameters. And in LQC, two anomalies are naturally elevated. The power suppression anomaly, and again this I'll just stating it, I can explain it in the discussion period. Namely, for large angular scale, which is to say spherical harmonic decomposition less than 13, there is a power suppression here, and that really descends from the power suppression of the primordial spectrum. And this scale, really L equal to 30, descends from the LQC dynamics and the choice of states that I talked about before, and the lensing amplitude anomaly. basically when the light propagates from the last CMB surface to us, it goes through gravitational potential. On an average, it is a Gaussian, and usually people just assume that this lensing amplitude, this parameter, is just set equal to 1 in the Planck data analysis. But what we can do is we can vary it and see what its value is, right? What is the best preferred value? When Planck analysis does it, they find that it's bigger than 1 by 2 sigma, so 95% confidence level. So this is the anomaly, and then in LQC, this anomaly is actually naturally elevated. But the 6-parameter model predicted by the standard ansatz for primordial power and relative error with respect to the Planck data for the 5 of the 6 parameters is less than 1%, while for the 6th one, the optical depth, the error is 13.65%. And this value has changed significantly from the WMAP to Planck mission. And in LQC, these values change. Here is the standard ansatz. Oops, what happened here? Okay, the left-hand column is the standard ansatz. The right-hand column is the LQC values. So the right-hand side is the LQC values, and you can see the tau changed by about 9.8%. And this is a concrete prediction of LQC. And there will be independent measurements of this tau, better measurements of tau, and one would see, in fact, if this is okay or not. Oops, go back, please. I'll not use pointer. I don't want to save time. Go back. Yeah. You're going forward. That's the problem. So it is a problem. Yeah, good. So let me summarize. I'm sorry that I'm late. LQJ provides a specific syntax.
You are not late. There is enough time. Just don't worry about it.
Okay, I'll just use this.
I mean, there were questions in the middle, so I'm adjusting the time. So
Thank you. So LQJ so the conclusion is basically that there is actually elevation of these anomalies. I wanted to just mention one thing, that recently there was articles in Scientific American alluding to the work of Ruth Durer and Delgado and Van Tent, which seems to suggest that there is no bounds, that there is actually a Big Bang. But actually, if you look at his work carefully, and one sees that, in fact, what their work says is that if, in fact, the anomalies are elevated by large non-Gaussianities, then the large non-Gaussianities needed for this procedure are ruled out by observations. Okay. But the anomaly elevation I'm talking about here is not using the mechanism of large non-Gaussianities at all. So it really has no bearing on this effect at all. But again, they publicized this. They misquoted Ivan Aguirre. Ivan wrote to them. They changed the article twice, but they didn't want to change the title. So I just want to say, take this with a grain of salt. If there are questions about this, I will also explain that. Okay, summary. Loop quantum gravity provides a specific syntax for quantum gravity that descends from a background independent gauge theory. There have been notable recent advances in full loop quantum gravity dynamics and applications to the problem of central physical interest to quantum gravity, namely physics of the early universe and also black holes that I did not cover. So as far as dynamics is concerned, the interesting results are basically faithful lifting of the constraint algebra that I mentioned to you already. And in the some more histories of spin-form models that I did not mention, there is an excellent candidate for calculating the transition amplitude, the so-called EPRL or FK, Friedel-Krasnow graviton. Furthermore, graviton propagator has been calculated, which is non-trivial for a background independent theory. There are powerful numerical methods. This is a recent advance which really is helping enormously to calculate this amplitude. For example, because of these numerical methods, there is a resolution of the apparent flatness problem. People thought that somehow there's a problem with the particular spin-field amplitudes that people had written down, these models that I talked about, because it seemed that only the amplitude will be really completely dominated by flat geometries in between. But it turned out not to be the case, because the arguments used very coarse paths connecting them, not fine-grained path connecting them, because people didn't know how to calculate the fine-grained path. But numerical simulations have enabled them to calculate the fine-grained path, and one sees that there is no flatness problem. It is not true that flat geometries actually dominate. And then this issue of refinement, which is really associated with this flatness, resolution of the flatness problem, has been studied, and this has been systematically studied with increasingly more complicated models that mimic 4D gravity by Bianca and Steinhaus. And Steinhaus is actually giving a talk tomorrow on the numerical methods of calculating spin amplitudes in the International Loop Quantum Gravity Seminar. For the early universe, there is singularity resolution by quantum geometry effects, and the loop quantum cosmology predictions. There is slightly better agreement with the observations than the standard ansatz, inflationary ansatz, but standard ansatz motivated by inflation, because the loop quantum cosmology primordial spectrum violates scale invariance at small scale. And then I already mentioned this confusion on the Scientific American. I think these articles used the maximum possible non-Gaussianity that could occur and not the actual predicted value. And in fact, Srinath and one of his students just recently, in a paper in JCAP, have done the analysis more carefully and showed that non-Gaussianities are in fact very small, that there is no problem with loop quantum gravity and observations as far as non-Gaussianities are concerned. And then for black holes, the quantum geometry microstates have been used to calculate the entropy and singularity resolution, and also there is some progress on black hole evaporation, which we can talk about in a discussion session in the afternoon if there is interest. Okay, so outlook. The direct observational check on the area gap. Now this I think is quite exciting, because the area gap was first fixed using black hole entropy calculations, and its value is roughly 5.17 Planck length squared. But now what we can do is we got the CMB observations and LQC analysis of it. So what we can do is we can say that, well, let's not fix the area gap. Let it be variable, just like the 6 parameters that we have got, observable parameters that we have got, which are actually variables. And we find with observations their best fit values within one standard deviation. And so one can ask, okay, now cosmology is telling us something. Cosmology is determining this area gap, because I'm making it vary, and I'm trying to find the best fit value within the standard deviation. And it turns out that 5.17 is in fact within 1 sigma. So it is just like the other 6 parameters of cosmological models that we talked about. They're all within 1 sigma, and so similarly, this is within 1 sigma. So it's a completely unexpected agreement between cosmology and the way using black hole entropy that this area gap was actually determined. If in fact, an area gap which is larger by a factor of 10 is ruled out observationally at 95% confidence level. So I find this quite interesting and quite intriguing, this unforeseen bridge from observations to loop quantum geometry. But of course, like all other approaches, loop quantum gravity is still very incomplete. There are many open issues that are challenging, but they also provide alluring opportunities. For example, we still don't know what the inner product physical Hilbert space structure or the inner product is on the space of solutions to the constraint equations that Madhav 1 has found, for example. Therefore, we cannot really make physical predictions directly from these physical states that have been found. We have nice anomaly-free algebra, but we have to make physical predictions. Again, as I was mentioning before, one can make symmetry reduction and try to bridge loop quantum gravity with loop quantum cosmology, and people are doing that. Relation between these solutions that are there in the Hamiltonian constraint and the spin form in integral, which also produces physical states, it will be fascinating to find out how they are related. Then there is a graviton propagator. So far, it is obtained with very close histories between the initial and the final state. What we would like to have is really much more refined calculations, and this may become feasible because of numerical advances that have happened, and then better understanding of the principles that select the quantum Friedman geometry state, psi of A phi, and the replacement of the Bunch-Davies vacuum that were done in the using some first principle in loop quantum cosmology. And the transition, there is a problem in the black hole evaporation process that is still completely open, which is really, there is a transition between very long length wavelength, very short wavelength Hawking radiation that comes at late times of the Hawking evaporation process, and the very long wavelength infrared radiation that restores purity at even later times at Sky plus, and this transition is not understood at all. So there are some very interesting open problems. These are just a few illustrations. So let me conclude with just a final outlook remark. Namely, some of you might be quite intrigued because I began by saying that loop quantum gravity is based on a duality between a gauge theory, which is background independent, and gravity. But we all know that there is also ADS-CFT correspondence, which really emerges from the gauge gravity duality. This is supposed to provide us the non-perturbative formulation of string theory. But so this looks similar, gravity arising from gauge theory. But I want to say that there are some important fundamental differences which have led to diverging thrusts and results. So the differences in duality. In loop quantum gravity, both the gauge and gravity theories live in the bulk, and the dictionary is complete. In string theory, the gauge theory resides on the ADS boundary, and the gravity theory resides in the bulk, and the dictionary is not complete so far. In MQG, the gauge theory is background independent. In string theory, the gauge theory uses the metric on the boundary, because we've got a boundary which is chi of anti-de Sitter space, and there's a metric there. And in string theory, in ADS-CFT correspondence, we need higher dimensions, we need supersymmetry, and we need a negative cosmological constant. These lie at the foundations of the ADS-CFT correspondence in string theory. These notions have no observational support, and they are not needed in LQG, nor in any of the other approaches like asymptotic safety, causal sets, CDT, that will be discussed in this workshop. So these are differences in the duality, and then there are differences also in the current thrust. And this is taken directly from an article by Casey Cole, which appeared in the Quantum magazine, but also is posted on the IAS website because she was a visiting reporter there. It says, string theory, the strange second life of string theory. String theory has so far failed to live up to its promise as a way to unite gravity and quantum mechanics. At the same time, it has blossomed into one of the most useful sets of tools in science. It's absolutely true. The duality is being used in QCD, it is being sometimes used in hydrodynamics, it is used in low temperature condensed matter physics, and so on. It's absolutely true. In loop quantum gravity, on the other hand, doesn't have such applications. Neither do other approaches we're going to discuss up here. But these approaches focus on long-standing problems of quantum gravity itself, the problem of time, the taming of Big Bang, the pre-inflationary dynamics, and CMB. Neither loop quantum gravity or string theory has really addressed successfully particle physics phenomenology. Asymptotic safety has begun to do that, and we'll hear from Aaron about this on Friday. So this is kind of where we are, and therefore we really need to understand each of these ideas to incorporate them to really make a more complete picture. Thank you, and I'm sorry that I'm a little bit late.
So thanks, Abhay, for a fantastic talk, and allow me to interject with a 10-second personal remark, which is that I met Abhay in 1988, which is 35 years ago, and before that and after that, time has passed. Abhay has been awarded so many accolades, the Einstein Prize, the National Academy of Sciences in the US. But to me, he always seems 43 years of age. I don't know how he does it, but from the talk as well, that's what I see. He's as energetic as he was as when I was a graduate student. So questions, please. I'm sure you have lots of them. What we shall do is, because of my fantastic abilities as chair, I just got interested in all the questions and I lost track of time. So we will have 10 minutes of questions, and then perhaps we'll have a 5-minute break Sumati, is that okay? And then we'll start. And we will not, I mean, we are doing fine on time, and we'll have enough time because we have enough play in the way we've structured things. So after 10 minutes, whoever wants to refresh themselves, there are coffee cups outside, and you can help yourself to coffee and come back in 5 minutes. The actual coffee break will be after the second talk. So please, questions.
This is also going to be a 1 hour
Yes,
discussion
and
session.
in the evening
at the end.
there will be a discussion
so
session.
please, I mean, please feel to ask questions, both.
So in this,
One moment. So Patrick. I guess, man, you have a good voice.
Thank you. Yeah, so very interesting presentation. Now, in the context of loop quantum cosmology, in the hot Big Bang model, when the temperature is of the order of Planck temperature, 10⁻⁹ GeV, one would expect that the discrete modes, the area modes, would thermalize with the hot ambient temperature. So one would need to use statistical mechanics. So is this aspect already been covered, that when one does the statistical aspect of the thermalization of the discrete modes, what kind of equation of state for the gravitational degrees of freedom one achieves?
Now, in the standard inflationary model, for example, which is, it's not Planck temperature, but still, the field is supposed to be at 0 temperature until the reheating time. So the statement here is really this scenario, which was the older scenario, that there's a hot Big Bang. Here it's really very cold Big Bang, even in standard inflation. It's cold Big Bang, and it's only after reheating that the universe becomes very, very hot. So that is the attitude that is being taken up here. It's not that it's going to be impossible if you wanted to change the viewpoint and say that, in fact, what we have is really not the Budge-Davies vacuum, but I mean in the standard inflation, but some statistical state, or here, instead of having that state which I call which I call little psi, if I can go back, little psi of Q as a scalar perturbation, Ti is a tensor modes up here. So we could change the state to statistical mechanics state if you want, but that's not the viewpoint that is taken so far. We don't want to make too many changes with respect to the standard scenario. So in the standard scenario, the universe is cold until the reheating, and so we are using the same model.
So the finite temperature field theory aspect has not yet
been taken into account, because because otherwise we get some results and people say, oh, but you did this thing which is not what everybody else is doing, and so on and so forth. But so even following the standard regime, we have a resolution of these anomalies and agreement at the short wavelength.
Thank you.
Yeah.
Hi, I just want to understand the singularity resolution statement better. So you mentioned, one of your statements was that all the singularity, in the LQC slide which you had,
yeah,
all singularities are resolved.
Right. So that was the result of Param Singh's.
Yes.
So
yeah. So just want to understand. So if you, I mean, there are two kinds of singularities being talked about, right? So there will be a Big Bang singularity, and then suppose I have a black hole embedded in LQC structure. Would I need two different frameworks to resolve those singularities, or only one would suffice? And then the second thing is, you'll also be working with perturbations on top of LQC, right? So then those density perturbations, sometimes the overdensity in them can give rise to these primordial black holes. So what would be the structure in?
No, these all happen much later. I mean, so the statement is that what Param has shown is really cosmology. So in cosmology, there are no black holes, in the sense that we are looking at exact classical and quantum solutions of it. There are no black holes. So when I say all singularities, meaning that there are singularities which can be anisotropic, there can be singularities which also have to be, the sudden death, in which, or different singularities, not Big Bang or Big Crunch, in which scale factor behaves completely differently from the standard one. Usually these, and those singularities is what all the strong curvature singularities within cosmology, that's what is meant up here. So let's talk about it. yeah, matter satisfies all the standard energy conditions. Yeah.
Abai, I have a couple of questions or comments, or to have your opinion. It's about inflation, because I mean, you know, my approach is that this early stage of accelerated expansion should come from quantum gravity corrections. And I remain unsatisfied, even though I did that in the past as well, to take a scalar field from the matter Hamiltonian, put it by hand, and see what's happening. So I think that at the end of the day, given that there are many people who start putting into questions what is the origin of inflation, should come not in this way, taking the field and see what happens. That's my first thing, and I would like to see what you think. And the second one is about the values from the CMB that you quoted. For me, as I always say, the lambda CDI model is a consistency model. You have the data, you put the GR, you put by hand lambda CDI, and you find the parameters. So now here that we have modified Friedman equation, I'm not that confident that the values as they were given by this consistency test of the lambda CDI model with the CMB should at face value hold in a modified version of the GR. So I would like your opinion. Thank you.
The first one I completely agree. Namely that this is certainly not satisfactory, that what one should get is from fundamental principle. But people have been working on that. It's basically like looking at corrections from fundamental gravity, right, a fundamental loop quantum gravity. Because of non-locality of the curvature operator, if you try to do power series expansion, you will get, you know, infinite number of towers of terms. The first terms look exactly like Starobinsky thing, and so the question is, you know, maybe we can get Starobinsky inflation. And the big problem has always been scale. Namely, the coupling constant in front of that thing is not Planck scale, it's much smaller than Planck scale. And how do you get it? And so people have not given up on that at all. People are working on it, but I mean, if you just put that coupling constant by hand, then we can do it. But so that correction term does come from higher order corrections that are embedded in loop quantum gravity, but we don't have a good idea about why that coupling constant is much smaller than Planck scale. Your second question is the following. What we get is something like a primordial spectrum. What CMB analysis does is take this any primordial spectrum, and this primordial spectrum is really at the end of inflation. Right? At the end of inflation, loop quantum gravity corrections are, I mean, even at the onset of inflation, I mean, loop quantum gravity corrections are, because the curvature is 10 to the minus 12, they're completely small, they're completely negligible up here. And what CMB does is, the CMB fast, etc., what they do is they take the primordial spectrum and convert it, taking astrophysics, everything, to what is going to be observed. So in that transition, it's true that we have got a different theory of gravity, but in that region, or even from the onset of inflation onwards, the difference between the two things is completely beyond observable. So that I don't think is an issue or a problem. Yeah. But the first problem, yeah, I think that we should understand. Yeah, great.
So what I would suggest, yeah, so Alok and then, and then Kinjal and then Tarun. What I would suggest is that it's now sort of the official break. If any of you feel a dire need of coffee, then you can just go in and come back. So officially, but if you your thirst for knowledge is more than thirst for coffee, then please, Alok, go ahead.
No, but this is about the area gap that you, as you said, you take the input from the. Can you hear? Oh, louder, okay. So about the area gap, you took the input from the entropy and then use it in the LQC, right?
Right.
Yeah. So my question here was that, but we know the area gap runs because it depends on the running Newton's coupling, and so then.
I don't agree with that. So that's another thing that we should discuss up here. I mean, the point is that it's true that there's G there, but it's a bit like E squared. You know, the fine structure constant E squared upon H bar, if you like, runs.
Right.
But so alpha runs there.
Yeah.
But I don't think that the charge of the electron per se runs. I don't think that if I take Millikan's oil drop experiment,
yeah,
that charge is not going to run. So to me, area gap, I mean, it comes out of fundamental commutation. If you like, the right-hand side of the fundamental commutation relation don't run. It comes from the right-hand side of the fundamental commutation relations. So I don't think it runs. I mean, I think that these are things that we have to understand much better.
Doesn't run. G runs somehow, but delta doesn't.
Yeah, delta doesn't. I mean, it's the same thing like the charge of the electron doesn't run, but the coupling runs. You know. Yeah. So if I take the G in M1 M2, G M1 M2 upon R, yeah, that runs. But somehow, if something that is defined, Planck length doesn't run. That's what I'm trying to say. Planck length is that's what I would. This is something that should be clarified. I mean, struggled a lot to try to understand exactly what the difference.
Just to continue, in the entropy, when we look at entropy and look at the E by 4G, that G is at the scale set by the mass of the black hole. So in that sense, that G runs, and it's a renormalized G at a scale.
No, that G is not run.
Okay. Yeah, there are a couple of quick questions, and we are.
Yeah, also the 1 hour. No, these are very, very fascinating questions that we have been debating them for a long time, and I can only tell you what the status is. But I would love to hear criticisms.
Okay, and very nice review. So I just have a very small question regarding the drift metric approach which is employed. You said that in the matter field evolution, the geometric observables will be replaced by their expectations in this thing. How long we are sure that the variances of those
No, the variances are also accepted. So that's why I was too quick. So for example, if you have got a squared is not replaced by expectation value of a squared. And that is a key point. I mean, it's very important. It's really, whatever appears there, you take the expectation value. So you take expectation value of a squared. Don't replace it by expectation value of a whole squared. So the variances are there, that are kept. And that is important in the whole thing.
So you have to bigger way of doing that. What we have seen that it depends that the variance will go down.
So again, let's postpone. We have one more question from Tarun, and then we should.
Stop, please. Keep your question. I mean, people should go. I mean, again, it's a live question. So if you look at the fact that volume is discretized, and I mean, naively you think of a tessellation, then naturally you break, symmetries. I mean, isotropy or anything, right? I mean, I just wanted to mention that you mentioned two of the anomalies. One anomaly that I have been quite interested in is the fact that there's a lopsidedness. Again, it's statistically difficult to prove, but it would be very exciting if there is a natural explanation in any of the early universe theories.
Yeah, we can talk about this later. I mean, I think in our papers, we refer to your paper, and so I should also look it up as to what we concluded, but we'll talk about it in the afterwards.
Okay, so I'm sure there are more questions, and we can have a lively discussion later, also with the other talks. So yeah, it's amazing nobody went out for coffee because. So can we take a 5-minute break, and you go at the speed of light and come back even faster? All right, but really 5 minutes, otherwise we'll run late. Oh, please, applause. Thank the speaker. Boss, how could I forget?
No, there was applause if that's what I ended. So I'll leave a fresh bottle here.
Yeah. Okay, so yeah, so can we please be ready for the next talk? There is an like old ancient Indian saying, which is that those who have too much coffee miss their lunch. So we will operate slightly on that principle, and it's a really great pleasure to have our next talk by Eleni Alexandra Contu, and I'm really eager to hear. So this, the singularity theorems are very strongly dependent on these positive energy conditions on matter, but quantum theory decides to behave otherwise, and we are going to hear something about how one can still structure the singularity theorems with these energy inequalities and rephrase them. So thanks a lot for coming here and telling us about this. As you wish, I can warn you either only at 5 minutes at the end or both at 10 and 5, whichever you please.
5 minutes.
At 5 minutes at the end. So you have 50 plus 10, and please relax and give. don't feel hurried.
Thank you. And I would like to thank Sumati for organizing this conference and for inviting me, and the Institute for hosting us. First I will start with a disclaimer. This is not a quantum gravity talk. It is a quantum field theory on Kerr space-time talk. I will maybe make a couple of comments on quantum gravity. And if you have heard my talk in the last maybe 5 years, it was probably on that topic. It's been kind of a large project with several papers. So this talk is focused on 3 basic papers. I don't have a laser pointer. I'm not sure why. Can I use this? Yeah. Maybe that's better.
Just a second. You can use this too.
No, but the
laser pointer works here. Yeah. Okay. Yeah, it's working. Okay. So in this paper from 2019, it's the basic method that I will talk about is described. This paper, we have the Penrose singularity theorem, and this is a recent paper on the area theorem that I will also talk about. So let's start with an introduction. So what is my motivation for that? The classical relativity theories have powerful predictions about the universe using only general assumptions. The big breakthrough was that they're not using a specific metric, for example, or specific symmetries, but only make some general assumptions about the space-time. And these assumptions, mainly the energy conditions that I will talk about, are violating the semi-classical regime, which is the regime where quantum effects become important. So the main question that motivates my research is which classical relativity theorems still hold in this semi-classical regime, and what are the new assumptions there? So I'm going to talk about mainly 2 theorems, the singularity theorems, which predict the existence of singularities. And here, the singularities, there are various definitions of singularities. The singularity definition, singularity theorems, is if it has at least one incomplete geodesic. So careful that this doesn't mean that it's necessarily a curvature singularity, for example, or physically something bad happens, for example, that the energy density diverges, or in cosmology that the scale factor goes to 0. It only means that we have some geodesics that are not complete. And in quantum gravity, as we heard also in the previous talk, it is believed that there is a resolution of singularities, and there are also in some theories like loop quantum gravity, there are resolutions of these singularities. However, these resolutions are in loop quantum gravity, for example, they're in a Planck scale, so in a regime where we don't have semi-classical gravity. So my question here is, in semi-classical gravity, are singularities predicted in that context? So before we get to the Planck scale, are singularities still predicted and the resolution happen in that scale, or the singularities can be resolved with just having quantum fields on a Kerr's background? Then I have the Hawking area theorem, which tells us that the area of the black hole horizon cannot decrease over time. So the situation is slightly different for the Hawking area theorem, because it is in tension with the Hawking radiation. Of course, the Hawking area theorem is a classical theorem. It takes some classical assumptions and tells us that the area cannot decrease. The Hawking radiation is perhaps the most famous semi-classical prediction. You require quantum fields to predict Hawking radiation. So with Hawking radiation, if we have, for example, a black hole, an isolated black hole, it will evaporate eventually, and so of course the horizon will shrink. So both things cannot be compatible. So the question here is, there are two questions actually, is the area theorem always violated semi-classically, and what is the reason for its violation? And the second question is if there's a weaker version of the theorem obeyed by quantum fields, so that the conclusion is not that the horizon cannot decrease over time ever, but perhaps there's a different conclusion. So let's dive in the classical theorems. So the singularity theorem structure. The singularity theorems have three basic conditions. The first is the initial or boundary condition. And this in the Penrose singularity theorem, which I'm only going to focus on the Penrose theorem, is that the existence of a trapped surface. So this is a surface, a hypersurface, that the two null normals have always negative expansion. In practice, that means, let's say you're inside the black hole horizon and you shine a flashlight. Even if you're shining outside, the light rays will always come back inside the black hole. So we can see that in this Eddington-Fickelson coordinates Schwarzschild black hole. So the blue rays are the ingoing light rays, and of course they always go inside and reach R equals 0. But the strange thing happens with the outgoing light rays. So if you're outside the horizon, the outgoing light rays will go to infinity. But if you're inside the horizon, these are still outgoing light rays, but they will always reach R equals 0. So it's a pretty strange surface. The second condition, which is the one I'm most interested in, is the energy condition. So energy conditions, classical energy conditions, express restrictions on the contractions of the stress energy tensor. And the idea, when they were introduced as assumptions for this theorem, was to express physical properties of space-time. The physical is in quotes because they're not really obeyed by all kinds of known matter, as we shall see. So for null geodesics, which is the one I'm interested in this talk, we have the null energy condition, the NEC. So let's say U mu is a null vector. We have the physical form of the condition, which is as a contraction of the stress energy tensor. The requirement is that at every space-time point, this quantity is non-negative. If we use the Einstein equations, we can get the geometric form. And this is the form used in the singularity theorems. So the singularity theorems don't know anything about the stress energy tensor. They only care about the space-time geometry. So if you want to get from here, from some matter that you have to the geometry, you have to use the Einstein equations. The perfect fluid stress tensor form helps us understand the physical meaning of this condition, which is that the energy density plus the pressure is everywhere non-negative. The third condition is the causality condition, and this in the Penrose singularity theorem is the existence of non-compact Cauchy surfaces. A Cauchy surface is a space-like hypersurface which intersects causal geodesic once and only once. And I will make a small comment here that there's work that has weakened that condition, and there's some recent work actually that replaced that condition with a much weaker one. So if you're interested in that and maybe its extension in semi-classical theorems, you can ask me later. So what is the proof structure of the singularity theorems? So we have the initial condition. So let's say we have a congruence of geodesics. The geodesics start focusing. Then we have the energy conditions, which guarantees that the focusing of the geodesics continue. And the causality condition tells us that there are no focal points on those geodesics. So the contradiction between the first two conditions and the third one leads to the result that the geodesic must be incomplete. If it develops a focal point, but the causality condition does not allow it to have a focal point, then we have geodesic incompleteness. If you don't understand some of that, I will talk in a little more detail about the proof in a moment. What about the area theorem? So the area theorem, we also have a causality condition, and that in the original theorem is the space-time is strongly asymptotically predictable. So what does that mean? The space-time has no naked singularities, is asymptotically flat, and there's a conformally connected part of space-time that has cozy surfaces. So what does that mean in practice? This is used to define a black hole in the classical sense. So the black hole is the area number 2. This is a picture with spherical symmetry. This condition can be with no spherical symmetry. This is just to help us picture that. And the black hole here, this area 2, is the area with no null infinity. And the event horizon is defined as the boundary of this area. And you can always define this area and this boundary if you have strong asymptotic predictability, even if you don't have a spherical symmetry. The second condition is, again, the energy condition. And it's the same condition as the Penrose singularity theorem. Again, it's a condition on the geometry. And it is the geometric form of the null energy condition. We call it the null convergent condition sometimes. Or sometimes we just call it the null energy condition. You'll see both. So what's the proof structure? First, we start with, we want to create a contradiction again. So we assume that the area of the horizon decreases. And then we have the null geodesics that are normal to the horizon. And so those geodesics are focusing because the area of the horizon decreases. The energy condition, again, guarantees that the focusing continues. But the causality conditions tell us that there are no focal points on these geodesics, which are the null generators of the horizon. So the area of the horizon cannot decrease. So it's a pretty similar contradiction that we're creating here. So let's go into a little more mathematical details of the proof of this theorem. So first, we need to define our surface. So we have a codimension 2 space-like submanifold, and then we have gamma be a causal geodesic normal to that submanifold. So this is quite important. We have our submanifold, we have the geodesic that is perpendicular to that. And then the focal point of gamma, this is not a technical definition, but it's the definition we're interested in, is the point, it has a point where the causal geodesic no longer extremizes the action integral. If we have time-like geodesics, this is the length integral, which is usually easier to understand. So for general causal geodesic, both null and time-like, we have the energy or action integral. And we are taking the geodesic from the hypersurface P normal to that. And let's say that Q is a point on that geodesic. Maybe we can take it as this length from the hypersurface to this point Q, BL. So we're examining this energy or action integral from 0, where 0 is on the surface, to Q, which is the point L. If we take the first derivative of a variation of that integral, so when I mean the variation, I mean, let's say we have a family of curves that the s equals 0 curve is our geodesic of interest. Then we vary s and we get a family of curves. And so on this variation, we can take the first derivative and then take s equal to 0. So we take this family, we vary s, we take the derivative, and then we take back s equals 0. So if we do that, then the first derivative always gives 0 for any kind of causal geodesic. So we have to go to the second derivative. And the second derivative of that action integral is called the Hessian. So we take the second derivative of that variation, and then we take the s to 0. So this is our quantity of interest. And now we can formulate the focusing theorem. So basically, we plug the action integral in here. We take the derivatives, and after quite a bit of calculations, we get this. So let's see what terms we have here. So first of all, remember the two vectors that we have. The one is the tangent vector to the geodesic. The second is the variation vector. So this is the vector in the direction of the family of curves that we have, the S, right? So we have the different curves labeled by S, and the variation vector is in the direction of that. So the first term is the derivatives of this variation vector in the direction of the tangent to the geodesic. The second term, what appears, is the Riemann tensor. And that makes sense, right? We have the metric, we have two derivatives, the Riemann tensor will appear. Now, the third term is a boundary term. So it's a term evaluated on the surface. So this is the shape tensor. So this term is basically giving us information about the hypersurface that we have. All right, so that seems technical, but it's actually a relatively easy process. So we get a tetrad basis on P, and then parallel transport it. So we have a tetrad, we're parallel transporting it, and then we define the variation field in the following way. We have these tetrad vectors, the EI, and then we take f a smooth function. The only condition for that smooth function is that the f of 0 is equal to 1, and the f of L, the final point, is 0. And then we sum. So this is our variation vector. So we define V to be the f times EI. And then we sum over those vectors. So this depends on the space-time dimension n. Right, so this is a codimension 2 hypersurface. So we take from 1 to n minus 2. So if we have 4D, it's just 2 terms. It's not a lot of terms. So if we do that, these terms are modified, right? Because we have a specified V now. And the first term is basically just the first derivative square of this function. The second term becomes the Ricci tensor contracted with the two tangent vectors of the geodesic. So this is already reminding us of the null convergence condition that we saw before. And the third term becomes the mean normal curvature vector field, which is defined just using the shape tensor. So the third term is again a boundary term that is telling us about our hypersurface. And we have the condition for the existence of focal points. So remember that the focal point is a point where after that the geodesic no longer extremizes the action integral. So we're using a second derivative test basically. So no focal point before Q. If the Hessian is positive for all V, then we have no focal point. But if the Hessian is negative for some V, then we have a focal point. That's why it's okay to define a specific V here. So here we take this very specific V. But if we show that the Hessian is less than 0 for this V, then this is enough to guarantee that there's a focal point. So it's basically a condition for finding a focal point. So what we're going to do is take this expression, set it less than 0, and see what that implies. Or use some conditions and see that those conditions imply that this is less than 0. So that will help us prove both theorems. So the Penrose singularity theorem. So this is a more technical definition of the Penrose theorem. So this is the causality condition that we said before. It has non-compact quasi-hypersurfaces, and P is our usual submanifold that the geodesics are going to start from. The second condition is the null convergence condition that we also saw before. So everywhere on these geodesics, we have the null convergence condition. The third condition is the trapped surface, right? So the trapped surface that we saw before, where the two null normals have negative expansion, is exactly equivalently defined with the mean normal curvature vector field. So remember, this was defined on our hypersurface. So our trapped surface is going to be the hypersurface P. And it's a trapped surface if H is less than 0. So this is an exactly equivalent definition with the trapped surface that I gave before. So if we have these three conditions, then gamma is incomplete. And in fact, it has a length less than 1 over H. So you might worry for null geodesics how we define the affine parameter, because we can always do an affine reparametrization. So what we do is we fix the affine parameter in the following arbitrary way. This is just to fix the parameter. So we set that the mean normal curvature vector field in an inner product with the tangent vector is 1 on P. So we fix it to 1. We fix this inner product to 1, and then we have a length for, we can define the length for the affine parameter. So let's see how we prove the theorem. Remember the condition for the formation of the focal point. This is that the Hessian is less than 0. The second derivative is less than 0. So we have these three terms, the one that just depends on f, the one that has the null convergence condition, and this one which is just about the hypersurface that we have. So first, we look at the null convergence condition, and this is telling us that this term is positive. So it has a fixed sign. The second is to pick a function. And here we can pick a very simple linear function. So we pick a linear function, we plug it in, and we get a specific expression for the first term. The third is that we have a trapped surface. And that fixes the sign of this term. So these two terms have fixed sign, and this term we know exactly where it is. So we have a very, very exact condition for where the focal point appears, and this is for length larger or equal to 1 over h. Now we have to go to the contradiction, and I'm not really going to prove the contradiction. It's been done to various papers. So the condition 1 implies that they have no focal points. This was the non-compact Cauchy hypersurfaces. So this is the causality condition. It's telling us that those geodesics that are normal to the P hypersurface has no focal points. And so they have length at most L. So this is telling us that the geodesics are incomplete before this length L. And so we have a singularity. So let's look at the area theorem now. As I said before, the causality condition here is that the M is strongly asymptotically predictable, and the second condition is that everywhere on M is the null convergence condition holds. So now let's formulate the theorem. So we have sigma 1 and sigma 2 be Cauchy hypersurfaces for the globally hyperbolic region. Remember, this is guaranteed by the strong asymptotic predictability. And the sigma 2 is in the future of sigma 1. And h is the event horizon. Sorry about the multiple h's. I hope they don't cause a lot of confusion. So here is this is the event horizon, but I don't think it's used anywhere else. So the area is defined as the intersection of the event horizon with these Cauchy hypersurfaces sigma 1 and sigma 2. And then the theorem telling us that the area of H2 is greater or equal than the area of H1. I have a diagram in the next page that will help, I hope. So this is the H, the horizon, which evolves into time. These are the Cauchy hypersurfaces, the sigma 1 and the sigma 2. And the intersection gives us the H1 and the H2. So this is the area we're looking for. And the geodesics are the null generators of the horizon. So they're these null geodesics. So again, we have the exact same structure to find the focal point. But there is a little tweak. So we have the null convergence condition, which fixes the sign of this term again. We picked the exact same function that fixes this term. But now we do something different. So what we need for H1 to have a focal point is that this term here, that's the tangent to the geodesic inner product with the mean normal curvature, is less than 0. And then we have a focal point. But now comes the contradiction. So the condition 1, the causality condition, implies that there are no focal points on the null generators of the horizon. So since there are no focal points on the null generators of the horizon, this must be false. So this must be greater or equal to 0. And this is exactly the change of the area of the horizon. So the change of the area of the horizon has to be larger or equal to 0. So, so unlike the singularity theorem, we had that, well, it develops a focal point, so the geodesic must be incomplete. Here we have that the generators of the horizon have a focal point if the horizon decreases. So the horizon must increase, the area of the horizon must increase. Do we have any questions up here? Because I'm going to move to the, yes?
So suppose a small black hole falls into a large black hole.
Falls into a large black hole. Mm-hmm.
So then there will be a caustic. The null generators are being added to the,
Mm-hmm.
How is that case taken into account in the proof?
So this is, I don't, this case is not taken into account in the proof. It's taken just about the evolution of one black hole horizon. But I think this case is covered by this theorem because at the end, the end horizon is actually larger than the sum of the original ones. So, but I don't know how the theorem would work if you have two black holes.
What I meant was if a null generator is being added at a future point, then
I mean, I think this is defined for just a single horizon, right? But if I with a grain of salt, I think this would not be a problem because, as far as I know, if you merge two black holes classically, this theorem still holds.
I think the only thing you need is null generators cannot leave.
Cannot what?
Leave.
Leave. Yes?
So we talked about focal points only in the future or the past also?
Yes, you can do it in the future or the past. So here's the future. But for example, if you want to have a cosmological theorem, you do it in the past, and it's exactly the same structure. So, so let's move to the theorems with weekend conditions. So what's the problem with these nice theorems that we presented? The point-wise energy conditions, such as the null energy condition, are all violated by quantum fields. So there's a very old theorem, actually, that in a large class of QFTs, you cannot have only positive energy densities at every space-time point. You need to have some negative values. So those theorems at first cannot hold in semi-classical gravity. Of course, we should remember that the fact that one of the conditions is violated doesn't mean that we have the converse of the theorem. So for example, if you violate the null energy condition, the original Penrose theorem doesn't hold, but that doesn't mean we have a singularity-free spacetime. It just means that the theorem doesn't hold. So, so we're inclined to find theorems with weaker conditions. So in quantum field theory, we have quantum energy inequalities, which introduce a restriction on the magnitude and duration of negative energy densities or fluxes. So, for example, one of the most famous quantum energy inequalities is the bound on energy density in Minkowski. So here we're doing QFT. So we have the stress tensor contracted. Here is two time-like vectors. And it's Minkowski's normal ordered. And we take the expectation value in a class of states. We usually pick the class of Hadamard states as they have a known singularity structure. And then we integrate this quantity over a segment of a time-like geodesic here. So I'm saying a segment because we have a function f here. That's a function with compact support. So wherever is the support of the function f is there where we average this quantity. And what is the bound? So the bound, the important thing about the bound is that it can be finite. If we take a function with compact support, it's a finite bound. And second is state independent. So it does not depend on the choice of states that we make. It only depends on some numbers, basically. So depending on the function that you pick here, you have some number. No. So this is for, I should have written it. It's for free scalars, right? So yeah, maybe I have thoughts about interacting theories, but it is in general difficult to prove those type of results for general interacting QFTs. So let's pick such a function, and then what we have is that the average is goes as minus some number over the support of the function f, t0 to the fourth. So basically, that is telling us for a short time, we can have a lot of negative energy. For a long time, we can only have a little, and if we take that to infinity, the bound is always 0. And given this type of inequalities, we have a weakened condition that is inspired by quantum energy inequalities. So what do I mean inspired? Is that at first this condition is not derived by QFT. It's a classical condition. It's a condition on the Ricci. So it's the same quantity that appeared in the theorem, but it is averaged with a function f. And the bound at this point has some constants qm and q0 that we don't know what they are. We just know they're positive constants. And the function f. And we have the function f. This m means some integer number of derivatives on f, like the two derivatives we had before, and one term that has no derivatives. So I should point out that if we have terms with a different number of derivatives, we can always, the L2 norms, we can always write them as that form of a bound. So one with the largest number of derivatives and one with no derivatives. So if we have a bound that is of the form some constant times the L2 norm of some derivatives of f, we can always write it like that. So this is a condition that I'm calling inspired by quantum inequalities. So what do we want to do? First step is to show singularity theorems with weakened conditions inspired by these QEIs. And also, later we'll see what happens with the area theorem. The second is to actually have a null quantum inequality, which I'm going to talk about, the smeared null energy condition. So this would be derived by QFT, in QFT. And the third one is the applications, which the application I'm going to say is for evaporating black holes. So first, this is the theorem. So this is a theorem that we proved with Chris Pfister in 2019. And it has as the energy condition exactly the energy condition that I showed you before. So as I said, at this point, this is a classical condition inspired by quantum inequalities. So in addition to this condition, we have two scenarios. So the first one is that the neck is obeyed after we measure the mean normal curvature, so after the hypersurface, and for a short time. So we assume that this L0 is much smaller than L. We have the rho, the null convergence condition, quantity larger than some rho 0. Maybe I shouldn't have said the neck is obeyed, because this could be actually negative, as we're going to see. For scenario 2, we look before we measure the mean normal curvature. So it's again a short affine parameter before that, so minus L0, and the rho is less than minus rho 0. So again, it's better to have the rho 0 be positive, but that could also be negative. The second condition is the initial condition. So remember, in the classical theorem, what we have was a trapped surface. So we had the h less than 0. So this is not sufficient here. Because we have a weaker energy condition, we need a stronger initial condition. So this will end up being a more than trapped surface. So a marginally trapped surface is not sufficient here. It needs to be less than a negative number. And that negative number depends on the parameters of the problem. So of course it depends on the constants that we have here. It depends on L0, it depends on L, it depends on rho 0. The causality condition is exactly the same as the existence of non-compact quasi-surfaces. So, yes? So nu is a function of those parameters. Yeah, it's a very specific function that I don't write here because it's complicated and not very illuminating. Mm-hmm. It depends only on the choice of function. So I think for Lorentzian, it's something like 1 over 16 pi squared, or something like that. Yeah. So note that this is for energy density, for Minkowski, for free scalars, right? So this is sort of taking into account that we might have other things. We might have curvature, for example. We might have energy conditions that don't only depend on that. So it's kind of taking into account that, and it's doing a more general thing. The Q's could depend on the geometry, yeah. But at this point, we really don't know what they are.
If the integral is along any causal curve, is it true for any causal curve?
So this particular inequality is for time-like geodesics. There is a version with a general accelerating curves, but then you have actually some other terms here. Yeah, so for example, this is something you can take into account, the acceleration of the curve, and that would appear in your constants. So I'm only going to give you the basic idea of the proof, because it's using the exact same thing as the original theorem. So we have the condition for the formation of the focal point. Remember that the Hessian is less than 0. So that's the condition. And we have this function here, the f of 0 equals 1, the f of L equals 0. And then we have the energy condition that we want to use. So this also has an f. So we might think, oh, okay, great, they both have f's. Maybe we can use the same f. But this is unfortunately impossible because they have different boundary conditions. Remember, this is to be finite, we need a function of compact support. And this is not a function of compact support. So we need to do something different. And what is different is to take one more function. So this is the reason for the two scenarios that I mentioned. So what we have is, I'm going to only talk about scenario 1, but it works pretty much the same with scenario 2. So remember, for scenario 1, we had this L0. So we're taking two functions. The function phi, which is the orange one, which goes smoothly from 0 to 1, and then it's strictly 1. And then we have the f, which is the function here, that is 1 from 0 to L0, and then it goes smoothly to 0 up to L. So it satisfies those conditions. So the condition for the formation of the focal point uses the f, and it goes from L0 to L. And the energy condition is using the product of those two functions. And the product of those two functions satisfies this condition. So we can have any type of function that satisfies this kind of structure, smoothly going from 0 to L0 or smoothly going from L0 to L. So now we only need to pick the function, which is not exactly easy because remember, we have to actually evaluate those things to get an exact result. So we better pick some good functions. And we have two options. The one is to pick some good functions where we can compute these things. For general m is the number of derivatives. And we did that in our Singularity theorem paper, where we picked some incomplete beta functions. The second thing to do is to optimize for one derivative. And this is what we did in the area theorem paper. So here, if you have m equals 1 here, you can solve this variation problem exactly and find those functions exactly. Basically, this is a calculus of variation problem, so you find what functions those are. In any case, we find the functions, and we can compute the nu. So what we do is basically plug in the functions in here, estimate the R using the energy conditions, and then we have to evaluate these L2 norms. So after we evaluate these L2 norms, we find how much H we need based on the functions, right? So, and the Q's, of course. So how much H do we need? And the H we need is less than this new function, which, as I said, we know exactly what it is. I just didn't write it here. It's a complicated function dependent on the functions that we picked on those constants. So let's see what's going on with the area theorem. So the first question, if you remember, well, what was the weakest energy condition so the classical area theorem holds? And you might think, oh, this is easy. This is the null energy condition. But that's not actually true. The null energy condition is not the weakest condition for which the classical theorem holds. And we can see that just from the condition for the focal point. So in order to have a focal point for this exact thing, to create the contradiction and conclude the non-decrease of the horizon, we only need to have that. So we only need to have an average condition. So it's a condition where the RT, the non-convergence condition, is averaged, and the right-hand side depends on the function f. Now note, this is not a quantum energy inequality because the right-hand side is positive. So we do not expect this condition to hold for quantum fields in general. However, it is a much weaker condition than the NEC. An example of such a condition, for example, is the half-average null energy condition, the half-anic. So this is the condition that tells us that this quantity is positive if we integrate from 0 to infinity of a null geodesic. Note that this is very different than the anic. The anic is integrating over minus infinity to infinity a complete null geodesic. And anic holds in a variety of situations, is a very strong condition for semi-classical gravity. However, this condition can be violated by quantum fields because you can arrange having your negative energy on only half of the geodesic, and this is fine from a quantum field theory perspective. This condition that is sufficient to prove the area theorem was also noted by Leschurd a few years ago. So the second question, what happens if we have a condition inspired by quantum energy inequalities? So here I want to put the condition that I had for the singularity theorem. We know that this condition is not sufficient to prove the non-decrease of the horizon, but can we prove something else? Well, let's see what we can prove. This is the theorem that we saw a few months ago with my student, Veronica Saki. So this is the energy condition that we have here, the same energy condition. We only use scenario 1, but that doesn't mean that the neck holds here. This could be negative. In fact, we can take it negative. The causality condition, we take it as the same. And the conclusion is actually relatively similar to the singularity theorem. So remember, we had a 0 on this side here for the classical area theorem. But now we have that the change of the horizon is larger or equal than a negative function. So that means that the horizon can decrease, but it can decrease too fast. How fast it can decrease is controlled by the parameters of the problem, and in particular, how much negative energy we can have. So if we can have a lot of negative energy, then the horizon is allowed to decrease fast. The black hole is allowed to evaporate fast. Note that I say allowed, right? This is only a bound. It doesn't mean the black hole actually evaporates with that rate.
In both these cases, this case and the previous case, it was inspired by quantum inequalities. Now, quantum inequality on the right-hand side depends on h bar.
Yes.
So here, QAM depends on, as you explained, depends on geometry.
You're wondering how strong this bound is. Yeah. I'm going to talk about that in an example.
What happens does it depend on the h bar? Because you're just postulating, you're just putting it there. But do we have an h bar there?
It depends on the inequality that you have right here. So basically, what is the QM and the Q0? So if it's a quantum effect, yes, it will depend on h bar. Yeah.
And so what happens to all these results when h bar goes to 0? Do you just get some of the previous results? Or?
Oh yeah, you get 0. Of course, like if you get 0 here, right? You get this. You get the generalized area, right? It's kind of like having this, right? So having a 0 on the right hand side, and then that holds. It's actually kind of related to your question. This we have an example in our paper where we have a classical field, the non-minimally coupled field, which violates the NEC, but obeys an inequality of that type. And there we don't have h bar, of course, and you have a bound, but I think that bound is not very interesting because you don't have a mechanism to produce Hawking radiation for classical fields. All right, so now let's go to QFT. That's the very last thing I'm gonna talk about. So the question is, can we prove a quantum inequality? The first question is, can we prove a quantum energy inequality over a null geodesic? So before I showed you the time-like one, so what we would like to have is to have a condition of that form. So to have the same thing over a null geodesic and have a right-hand side that is state independent, and this is just a numerical constant. And now this has one derivative because of dimensions. And we want it to be invariant under a fine reparameterization. So unfortunately, we can't have this nice quantum energy inequality over null geodesics. And that's because there's a counterexample. So this was proven by Fuster and Roman about 20 years ago. So they considered a particular state, but it's a pretty irregular state. It's a Hadamard state that is generally well behaved. It's a vacuum plus 2 particle state. And what happened there was the 3 momenta of the excited moons were unbounded. And then as they grew, so this quantity became more and more negative. And as it became more and more negative, it went to minus infinity as the momenta grew. So that means there's no lower bound for this state. And this is sufficient to say that there is no quantum inequality of that form, because this is for a class of states. So if you prove that for one state you do not have a lower bound, then you can have it for the whole class of states. So what can we do about that? Well, clearly the problem here was that the 3 momenta were unbounded, and as they grew we couldn't have a lower bound. But in QFT, it's a semi-classical theory. We can have an ultraviolet cutoff, an LUV, which restricts the 3 momenta. So this LUV is at most Planck scale. So if this is equal to, it has an inequality, then the UV cutoff is of Planck scale. This here, n is the number of fields. We can have multiple fields. But it is an inequality if the UV cutoff is further from the Planck scale. So this cutoff will depend on the type of theory that we have. For example, some effective field theory. So with this consideration, we have the Smirnov energy condition, or SNEC, where we do have a quantum inequality of that form, but with the UV cutoff encoded in this constant B. So basically the bound will depend on the UV cutoff. So what is B is this numerical constant that gives us a scale of the UV cutoff. And basically if the UV cutoff is Planck length, then the B is of order 1. And if B is of order 1, then a lot of negative energy is allowed. This is not a very good bound. However, if the UV cutoff is much larger than the Planck length, then the B is small, and then this bound becomes small and becomes controlled. Yes? Sorry, I didn't hear you very well. The B depends on the numerical. It depends on the UV cutoff, yeah. It's a numerical constant.
Right. So manifestly, I mean, this inequality is manifestly violating Lorentz.
It is, so this inequality At this point, it's just for QFT, right? And it holds. But it depends on the UV cutoff, how strong the bound is.
So I was wondering if you could have done this in dimensional regularization. Was there
I'm not sure about that. Yeah, maybe we can talk later. So now we can prove the semi-classical versions of these theorems. And this happens with the semi-classical Einstein equation. So the semi-classical Einstein equation is a hybrid equation. It connects the expectation value of the stress tensor with classical curvature. So note that we're not solving this equation at all. It is a very hard problem. What we're doing is basically saying, let's say that in our space-time, there is a solution which includes a state and a metric which consistently solve this equation. And then we can connect what appears in the quantum inequality with the classical curvature which appears in our theorem. And this is a direct correspondence. So based on that, we have a semi-classical singularity theorem using the snack. So I should note that the snack is for Minkowski spacetime. And you might think that it's not very interesting to use a condition for Minkowski. The thinking here is that we have quantum inequalities for curvature. And the first term, the dominant term, is always the term that appears in Minkowski. So we think that the snack does capture the main correction, let's say, of a negative energy, even in curved spacetime. So we will have some extra terms if we have curvature, but the first term, this term, the Minkowski term, should be the same. So we think it merely captures this idea. For the time-like case, we actually have a bound with curvature, the cosmological case. So now we know what this Q is, and Q is basically B. And the H depends on those parameters. So basically, how trapped our curved surface is going to be depends on the value of B. So how trapped the surface needs to be is controlled by how much negative energy we can have and how close the UV cutoff is to the Planck scale. And we have a little toy model for evaporating black holes. So here we fix the background to be Schwarzschild. Of course, we know Schwarzschild, we have singularities, but here we just fix the background and we're not assuming the neck, we're assuming the snack. And what we want to find here is to compare the mean normal curvature of Schwarzschild to the nu that is required from the theorem. And basically, we want to see how far inside the Schwarzschild radius this hypersurface P needs to be. So the solid line is the classical Schwarzschild radius. The P is our hypersurface, which we need to conclude geodesic incompleteness. So basically, we have to go inside the black hole to conclude geodesic incompleteness here. But how far do we need to be? Are we close to the classical horizon? Then we have a good theorem. If we're very far inside, we don't have a good theorem because then we need the knowledge of what happens before. And this is the results. So for two values of B. So this is the largest value of B where the Q1 is equal to 1. So this is the UV cutoff being exactly on the Planck scale. This is the worst possible scenario. And there the situation is relatively bad because we see that the lowest value is 1/3 of the Schwarzschild radius. So we have to go 1/3 of the distance of Schwarzschild to conclude geodesic incompleteness. And this is a pretty large distance. However, if we take the Q1 only 1 order of magnitude less, then we can go much closer to the classical horizon. So this is how close we can get to the classical horizon. I should note that this axis here is the L. So this is about singularity prediction. So how well can we predict the location of the singularity? And if that goes to infinity, it means we don't have any singularity prediction. That goes to infinity. But remember that the theorem tells us that there's a singularity before that, so we don't have to predict it accurately. And what about the null semi-classical area theorem? We do the exact same thing with the snack. We apply the semi-classical Einstein equation, and here we're using the scenario 1. This rho 0 is something negative. And we want to evaluate the nu in the case of evaporating black holes again. So what do we know about evaporating black holes? So this is an old result by Page, which is the evaporation rate for spherical black holes. That alpha depends on the kind of particles the black hole is emitted. What we're interested in is that goes as t to the cube. And now we need to have some kind of estimate for this rho 0. And we take an estimate that is from numerical simulations close to the black hole horizon. And these tell us that the numerical simulations actually with some analytic models agree that this rho 0 is negative and it goes as t to the 4th. So this is for close to the horizon. It's a pointwise bound. And with this assumption, we have from the theorem that the decrease of the area of the horizon is less than something that goes as the square root of b. So of course it depends on b again, and goes as t squared. So this goes as t cubed, and this goes as t squared. So there is some temperature where our bound is actually restrictive for the evaporating black hole rate as is computed. How restrictive is it? The answer is it's not very restrictive for a large b. So this is the first line is the one that goes as t to the cube. It's the known result. This is our bound. The orange line is our bound. For b of order 1, so for LUV in the Planck scale. And kind of as expected, this happens in a very high temperature. So it's not a very restrictive bound for the UV cutoff being in the Planck scale. Of course, if we take a smaller b or a UV cutoff larger than the Planck scale, then this will go to smaller and smaller temperature. So it will be more restrictive. But we would need a better bound for that. So I will conclude. And I just showed you we can get versions of the classical relativity theorems and semi-classical gravity. And we had two different results for singularity theorems, which singularities are proved semi-classically, are predicted semi-classically mostly, while the area theorem is easily violated by quantum fields. However, there is a bound on the evaporation rate. And I will leave you with some future work. So in 2021, we proved this different energy condition, which doesn't have a UV cutoff, but this is integrated over an area. So these are the two null directions, x plus and x minus. So we're integrating over an area. And when we're integrating over an area, the bound depends on how much the support of this function is on the two null directions. So basically, if we integrate on x plus and x minus, how much is the support? The bound depends on that. But it does not depend in any arbitrary UV cutoff. So it would be nice if we could have versions of singularity theorems and the area theorem that instead of a line bound, we had an area bound. And we have some progress done, but only in the time-like case. But I am hopeful that maybe we could do that in the null case too. Thank you.
Thanks, Eleni, for a fascinating talk. If we can take questions now. So lots of hands. I think Deepak first, and then Steve.
Okay. So my question is that if we consider, for instance, quantum gravity, right? Then we would expect a modification of this Ray-Chaudhuri equation, right? So
note that I'm not using Ray-Chaudhuri equation here. Do you mean the condition for the focal point formation?
Okay, well, but
do you mean the condition for the focal point that I showed earlier? Quite earlier? Yeah, this one. Do you mean this condition?
Right, I suppose so. I mean, because when you are in the regime of quantum gravity,
I would expect that because this is classical, right?
Right. In particular, for instance, if you consider area quantization, right? Mm-hmm. How would that affect the focusing of geodesics or not?
I don't really know. Okay, you would need to have a theory of quantum gravity that has well-defined geodesics, which, as I know, this can be a problem, and then redefine that equation. So I don't really know.
So I'm trying to understand your very last point about the evaporation rate limits. Are you, first of all, are you saying that that even with B of order 1, so Planck scale cutoff, that a black hole that is somewhere near the Planck size can't evaporate as fast as the standard page rate?
Yes, but we should be a little careful for that, because this evaporation rate is accurate mostly for early stages of evaporation. So this, I don't think it will hold for that high temperature. The second thing we should note is the energy condition we're using there, and the limitations of that energy conditions. So I wouldn't take that as a strict bound, because neither of those results is very accurate in that regime. It just shows that we could get maybe a restriction on the evaporation rate, something that shows us that maybe the evaporation rate that we have is not the correct one in that regime.
Okay, but that in itself would be interesting. If you can show that evaporation slows down, then you're more likely to get, at least it gives you a lot more time to solve black hole information problems and things like that.
Yeah, I think that would be interesting.
In the first part of your talk, when you were talking about classical and also without averaging, you assume that T contracted with 2 U's is positive. I was wondering if, in that part itself, if you permit T contracted with UV, where both U and V are null, whether that assumption, which is the dominant energy condition, if you assume that condition in the classical part, whether it would give you better control in the second part when you're talking about quantum effects as well as averaging.
So first of all, you can totally prove the classical theorems with the dominant energy condition, because the dominant energy condition implies the null energy condition. So there's no problem with that. I would expect to probably have worse results in the classical case, because in the quantum case, because it is harder to prove quantum inequality. You have worse, let's say, quantum inequalities for the dominant energy condition. Maybe you're saying that because I said that the null energy condition in the quantum case, we don't have a good inequality. But note that the problem here is actually the integral over the null geodesic. It's not the quantity that you have here. So if you have null vectors here, but you have a time-like geodesic, you have no problem to have a state-independent nice bound, as in the energy density. And the same thing would happen for, I assume, with the dominant energy condition. So if you just change the one vector here to be the dominant energy conditions, if you still integrate over a null geodesic, you still have the same problem.
Okay, so you alluded to the fact that when you use the classical fields, then also you got a negative lower bound. So I guess that might have happened that for this classical field configuration, the energy density plus pressure was negative.
Yeah, this was for the non-minimally coupled field.
Non-minimally.
Yeah.
So would that mean that if you take the fields that are the candidates for the dark energy, which violate the strong energy condition, you generically get a negative lower bound for?
No, that's not actually sufficient. Because, for example, the massive free scalar violates the strong energy condition, but does not violate the null energy condition. So as far as I know, the classical scalars and actually the spin fields, they obey the null energy condition, except if you have some non-minimal coupling with gravity. This is the case that I know that violates.
So you need a non-minimal coupling.
That's the only case I know. There might be some other case for classical fields, maybe with interaction, something like that, but that's the case that I know. I would find it hard if there is a different case, because in the null energy conditions, the terms that have the g mu nu go away. So if you have a mass, it doesn't affect it. If you have some potential, it doesn't affect it. So I don't know of any other case.
Thank you.
So I might be getting confused with the different H's, but the H that was referring to the horizon, that really means that it's the horizon in a spatial hypersurface, right?
Yeah, exactly.
So now then I'm wondering about the following thing. So you come up with essentially quantitative statements about the relation between how much smearing you have in the null energy condition and how far you need to be inside the horizon to make statements about singularity theorems.
These are two different theorems. We're talking about the singularity theorem.
Yeah, yes, for now, okay. We can
Okay, yeah. So for the singularity theorem, you don't really care about the event horizon. What you care about is about the trapped surface, right? So the classical trapped surface is the marginally trapped one. So what we want to know is you have a marginally trapped surface, and you need to go further inside the black hole to have a more than trapped surface.
But
right?
so what I'm wondering about is in either of these theorems, whether it's a horizon or an event horizon or a trapped surface, I'm wondering about whether the quantitative relation between the smearing and the statements about how far you have to be inside depend on your foliation. Do you have an understanding?
So the examples, both examples that I gave have a Schwarzschild background, so there's no issue with that. And that's why I said these are toy models, right? So for example, in the singularity theorem, we have a spherical symmetric case, and so we can define those things. So this is just an application, right? Because we want some h from the geometry to compare it with the theorem. So sorry, this is the mean normal curvature, not the horizon, right? This is the mean normal curvature of the geometry to compare it with the theorem. So if you have a different geometry than Schwarzschild, then you would have a different h. Is that what you mean? So the comparison will change if you change your background geometry. I wouldn't expect the quantitative statement to change, but the exact expression would change. Does that make sense? This is a comparison of Schwarzschild with what is required from the theorem to have incomplete geodesics. Yeah. So to get this, you needed background geometry. This is not gotten from any background geometry. It's independent of background geometry. So if you take a different example, you have a different h.
Okay, so you say it's not foliation.
It could be foliation dependent, yeah. So this part, yeah. I mean, but maybe we can talk about it later. Yeah.
Yeah, I just kind of a similar question. So as you said, there is a singularity theorem and then the black hole area theorem. But for the singularity theorem, then the usual thing was just that you have a marginally trapped surface. But now you replaced it by saying that in fact it's a trapped surface with the expansion negative and some bound on that, right? Now again, I'm going back to this because I'm trying to understand physically some sense of some intuition for this. You got a bound on the right-hand side, so the expansion is negative and its absolute value is bigger than some value. Now that value depends on h bar again. So my first thing was, well, I mean, it's probably it's Planck scale, so but dimensionally, then it would be 1 upon length but it can't be 1 upon length because in the classical limit you get 0. So somehow the Planck length is coming in the numerator, and I'm confused about, I mean, are we saying that your theorem requires...
Oh, you're worried here how you take the classical limit of this inequality.
Yeah.
Yeah. So you can, that is a good point. That it's not immediate to take the classical limit of this inequality here.
I mean, is that just because you put a cutoff and that's why it is?
I would expect that because it's because of the cutoff that you have.
But
yeah.
even before you did this, right? I mean, just looking at the singularity theorem, you still had this thing about the expansion being negative and absolute value of it being bigger than something, right? And that case where there are no cutoff or anything like that, I'm still confused about whether your requirement is huge expansion or very little expansion. That's all. Because if I think about the Planck length coming in the numerator, then
exactly.
it's a very little expansion.
So that depends on, here it depends on B, right? So it's that relationship that if B is Planck scale, then you need to have a very trapped surface. But if you have B that is small, then you don't allow a lot of negative energy, so you don't need to have a very trapped surface. It's close to marginal. So there's this relationship. So the nu, you can think about it as, let's say, proportional. It's not exactly proportional, but let's say it's proportional to B in this case.
So, I mean, there are more questions. In fact, I also have a question, but we have run out of time. So we should go now for, Sumati, you had to announce?
Just quickly, that there's supposed to have been a half-an-hour break, but if we can rush and drink our tea and have our coffee downstairs, there's also this machine here, within 20 minutes.
So, I mean, maybe we can reconvene at
55?
55. I was thinking 50, but yeah, 55.
50 would be great. 50.
Yeah. 50 would be good because then otherwise you'll have less lunch, according to the conventional Indian wisdom. So let's thank the speaker again. And you'll hear one announcement repeatedly again. So please, today we are having a special event which really requires your participation. So please come for dinner at 7:30 sharp, please, today. Thank you.
Thank you. Thanks. Great.
Is the pointer you have taken?
Yes, yes.
Okay, fine. It's on, right?
Yeah.
It's on.
Yeah, now it's on. Yeah.
Okay, fine.
Hi, Sam. How are you?
Good, good. On it now.
No food for everybody.
Okay, so please sit down and we can start the next session. your time. So. Okay, so our next speaker is Mark Ehler, and I don't know, nowadays he likes to sit on light rays and wait for infinite time and tell you what he sees. So either in the past or the future or both, I don't know. This is probably one of a few talks which will be dealing with asymptotics at null infinity. And it's a great pleasure to have Mark over here. So without further ado, Mark is talking about fine asymptotic structure of general relativity. Mark, would you like to be told at 10 minutes or 5 minutes or both?
Yeah, 10. I also have I will check the time.
So you
10.
don't need, you don't.
No, 10 is fine.
10 is fine. Okay.
But
so
no stress for you.
no stress for you, mainly. Okay.
Thanks. Well, so thank you, of course, to the organizers for the kind invitation to be here. So thanks to Madhavan and to Sumati and also to Manju and Sachin and the help with organization and hospitality. It's great to be back in this wonderful institute. And yes, today I would like to talk about results in classical general relativity, but which I hope can be used for quantum gravity. And this is based, you will see, on the work of many people, but also some of my collaborators and also some heavy use of Mathematica code that we had to develop. I can explain you why. So I start with some motivations. And of course, a motivation which we probably all share is that we would like to understand symmetries in general relativity. So why? Because we know that symmetries are a very precious tool to understand systems, both at the classical level and also to have control on the quantization of a system. Now we know that in gauge theories, especially thanks to Noether's second theorem, we know that if you try to ask what quantity we assign to gauge symmetries, well, the Noether theorem tells us that this leads to surface charges, so surface integrals. And in fact, if we now specialize to gravity, to general relativity, there is something even more peculiar which happens, namely the fact that, as we know, in general relativity, all we have are constraints. So in fact, these surface charges, in a sense, they are all that there is in general relativity. So very loosely speaking, you can think of GR as being already naturally holographic, in the sense that it has this tendency to encode on boundaries relevant physical information, such as the Hamiltonian, for example. So a natural question is what type of physical and mathematical structure is actually encoded into these boundary charges? This is what we would like to understand. And of course, this question has been asked a long time ago and is understood extremely well, in particular in the case of asymptotically flat spacetimes, where there is a very striking and useful relationship with gravitational radiation. So also the question is, what is the focus then of recent activity in this field? I mean, since we understand this structure fairly well since a long time now and very rigorously, what is the point of all the recent work? So I want to touch upon some of these topics here. This was also to cite many people who work on these fields, and of course this list of contributions. I mean, many people here have worked on many different topics. They just appear here. Yes, for example, Abai, who is here, Wolfgang and Aluk, they have worked on many different aspects. And so to mention a few of these aspects, so the first one is there is now recent interest because people would like to define a notion of flat space holography, so holography for asymptotically flat spacetimes. There is also a lot of work on classical and quantum soft theorems. To understand this, people have had to develop covariant phase space techniques. There is also interest in the construction of so-called dual charges, the study of DS and ADS spacetimes. There's even work on asymptotic symmetries for cosmological spacetimes. There is also the recent work of Abai and Jurek and collaborators on multiples and non-expanding horizons. There is also research on understanding the role of potential logarithmic terms. Also work on new memory effects, inclusion of matter, and something which I will briefly mention, W1 plus infinity and twisters. Another motivation, which you have probably heard of, is this structure which sometimes people call now the infrared triangle. This is a set of relationships between things which were known for a long time, of course. On the one hand, you have soft theorems, which are statements about the behavior of scattering amplitudes in the quantum field theory. Another tip of the triangle are the so-called memory effects. So this is the famous displacement memory effect after the passage of a gravitational wave. And the final tip is asymptotic symmetries. So this will be the focus of this talk. And sometimes people kind of loosely argue that given this triangular relationship, well, you could ask what is the largest amount of asymptotic symmetries you can have, because the more asymptotic symmetries you have, the more such triangles you have, and then you can understand kind of deeper the fine structure of your theory. Because we know that soft theorems, they come with also subleading soft theorems, and they have lots of subtleties and also logarithmic corrections, as Alok will talk about. Memory effects, people have also, in addition to the displacement memory effect, people have mentioned all sorts of other types of memory effects. So we would like to understand how this fits in this triangle. But this has to be done extremely carefully, and at the end I will mention an example where there is a subtlety here. Also, motivation is, of course, holography, and you could ask what are the different types of holography. Of course, historically, we're used to ADS holography, ADS-CFT, but in ADS holography, so we know that the boundary is a time-like boundary, and due to the choice of rigid boundary conditions, this prevents radiation from leaving the system. So it's a very, physically speaking, it's a very particular system. There is no outgoing radiation. So in a sense, you could think of this as being, in a sense, unitary by design. There is no radiation leaving your system because you have closed the system. In contrast, for flat holography, for asymptotically flat spacetimes, it's very different because asymptotically flat spacetimes are genuinely open systems in the presence of radiation. There is energy loss due to gravitational radiation. But yet, this is an interesting context because this is where, for example, we make contact with the S matrix. And this is also where we know lots of things about gravitational radiation. So therefore, we have to understand maybe how to go from ADS holography to flat space holography. You could even think of going further and having maybe a notion of local holography. This we mentioned briefly in a recent review with Laurent and Wolfgang. You could ask even yourself, what is the symmetry content that I can assign to finite regions of spacetime and not necessarily asymptotic boundaries? And can I say something meaningful about the quantization of these quasi-local symmetries? And the last motivation is that I think that there are maybe some nice and exciting prospects for loop quantum gravity itself. Because as Abai mentioned, loop quantum gravity is relying on some key features. And two of them is, of course, the use of tetrad variables instead of the metric itself. And another one is the typical inclusion of this dual term in the Lagrangian, so the Holz term with a so-called Barbero-Emirzi parameter. So maybe there is a prospect that somehow it could be that there are asymptotic observables which are somehow sensitive to this structure. And of course, holography and LQG, they share this feature that they both rely heavily on understanding the symmetries of the theory. Not from the same point of view, because LQG is fundamentally a bulk theory, whereas holography relies on boundary structures. But in both cases, the symmetry play a central role. Therefore, the question for us, how do we talk about symmetries and charges in general relativity? So there is a very nice setup to do this. And this setup is to think of null infinity as a boundary of spacetime. So this was pioneered by this list of people. Maybe I also forget people. But we know very rigorously how this works. And the idea is the following. So we just to set the notation and the stage, I just write Minkowski spacetime in these retarded null coordinates. Then on this Minkowski spacetime, we just put some structure. So we give names to these regions. And so you know that if you go with the radius going to infinity along u equals constant directions, you reach future null infinity, which has topology R cross S2 in 4 dimensions, R cross S1 in 3 dimensions. Here is time-like infinity. Here is space-like infinity, where spatial hypersurfaces die. So there is this geometrical picture. Now the question you could ask is now, okay, in this space-time, imagine that you have a physical process of interest, for example, binary black holes orbiting and emitting gravitational radiation, which goes out to infinity. Well, you would like to know how to describe this. Of course, this is not Minkowski spacetime anymore, because in the bulk here, you have very extremely complicated system with full nonlinear general relativity. So you could ask yourself, well, asymptotically, this radiation, does it somehow give some corrections to this Minkowski spacetime? Can I make sense of this Minkowski plus radiation asymptotically and make sense out of this little correction to Minkowski spacetime? So this is very schematic, but we can give now more precise flavor to this. using so-called Bondi coordinates. So first, a disclaimer here. So of course, the authors which I mentioned on the previous slide, they had a very clever way to set up this and to be able to obtain all the rigorous mathematical proofs that we have. They carefully worked in a very geometric setup, which allows you to prove things without using coordinates. But often in general relativity, it's convenient to go to a set of coordinates to have kind of more hands-on control on some of the equations. So it's a bit unnatural from the point of view of the philosophy of GR, but it's convenient for calculations. Therefore, let me go to coordinates and use Bondi coordinates. So these coordinates are essentially null coordinates in which you impose three conditions. So GU upstairs equals GU and angular coordinate upstairs equals 0. First one means that U is a null direction, partial U is null. The second one means that the angles are constant along these null directions. Now, if you lower these components, you will get with the downstairs metric that GRR is vanishing and GRA is vanishing. Therefore, the most general line element you can write is this line element, which is called metric in Bondi gauge. So any solution of GR you can bring to this form by a choice of coordinates. Yes?
But only any solution in GR.
Sorry?
Does it require GR?
I have not solved any field equations yet, so this is just a choice of metric, right? Now the point will be exactly to solve the equations. So here in particular, you notice that there are 4 free functions of all the coordinates, u, r, and the angles. So v, beta, and ua. These are 4 free functions. Now, to solve the Einstein equations, you have to put some more inputs. Namely, you have to assume a behavior for the transverse metric. Otherwise, you cannot go on with the Einstein equations. Typical choice is to assume that this transverse metric starts like the Minkowski metric with R2 times a metric on the sphere. And then you have a subleading expansion, which here precisely, kind of motivated, you will see, by the work of these people and for some other reasons, I want to include logarithmic terms in this expansion to see what happens if we include these logarithmic terms. So this is the expansion which we assume. And just to start mentioning a bit some more structure here, typically CAB, you may know, is what we call the asymptotic shear, and a very important quantity is the time derivative of CAB called the News tensor. And then basically from here on, you can solve the Einstein equations and let them decide what is the structure that you get from this metric. But now you could worry about the fact that, you see, we have only picked 3 gauge conditions. And if you want to completely fix the gauge, you would like to pick 4 conditions and not only 3. In particular, you notice here that the radius is completely free. If you change the radius r, you preserve this gauge. So there is freedom here in choosing the radius. So even though you can solve the Einstein equations, as we will do, you are free to choose the radial coordinates. So the question is how to complete the gauge fixing. There are several known ways to do this. Famous one is so-called Bondi-Sachs gauge. In the Bondi-Sachs gauge, you impose a condition on the determinant of this angular metric. You demand that it's related to the determinant of a flat round sphere metric in this way. Now, if you expand this condition in 1 over r, you will find at first order that this implies that CAB is trace-free. So as we kind of expect or want, CAB is trace-free, is the asymptotic shear. That's why CAB encodes the 2 degrees of freedom, the 2 polarizations of gravitational radiation. And geometrically, in this gauge, the radius r is actually the luminosity distance. Now there is another famous gauge, which I will briefly mention a bit later, called the Newman-Unti gauge, used, of course, by Newman and Unti. And in this gauge, you don't impose the determinant condition, you impose beta equals 0. If you do this, there is already something a bit peculiar which happens. Namely, you don't actually get a trace-free condition for CAB. So you have some extra field in your theory which is hanging out, and therefore you have to ask the question, what is this field doing here? How does it impact the asymptotic structure? I will come back to this a bit later. Geometrically, the reason for doing this is that in this gauge, r is the affine parameter for this null geodesic. Okay, now that you have this setup, we can go and solve the Einstein equations. Now I will allow myself to be a bit more general, even though I wrote a Penrose diagram of asymptotically flat spacetimes. Now I want to introduce a cosmological constant. We can do this because essentially in Bondi gauge, solving the Einstein equations don't care about whether there is lambda or not. Of course, if you have lambda, and if it's positive, negative, or 0, the global structure of spacetime, the geometry completely changes, right? The nature of the boundary is not the same. But algebraically, from the point of view of solving the Einstein equations, you can just carry lambda around. You cannot do this in the usual Pfefferman-Graham gauge that people use typically in ADS, because there the flat limit is ill-defined. But you can do this in Bondi gauge. Therefore, to see what happens, let's put this cosmological constant. Then it's beautiful because you can solve the Einstein equations following this so-called Bondi hierarchy. The Bondi hierarchy is essentially the fact that the Einstein equations, they're organized first as ordinary differential equations in the radius, which you can solve, and then you get just equations which are evolution equations in time. And you can just solve them recursively and list them, and you have access to full Einstein equations and to their physical meaning. And I think it's interesting to go through this solution, so it's a bit kind of pedestrian, but I would like to go through this with you. So the first equation is the completely radial Einstein equation, ERR equals 0. This is the equation which fixes beta, essentially. You solve this equation, it fixes an expansion for beta. This is the first order differential equation, so it has one integration constant. This integration constant, we call it beta naught. So here, of course, when you solve this in 1 over r. All the functions which appear are functions of u and the angles. So beta naught is a function of retarded time and the angles on the sphere. And then you have this shear squared and then some expansion which you can take as far as you want. Now you can move to the second Einstein equation, which is the angular Einstein equation, ERA. This determines UA, this vector UA. So again, you have a 1 over r expansion. Importantly, this equation is second order now, so you get two integration constants. The first one is at this order. Then there is something U1, some expression, not important. U2 has some expression, it's not important. Importantly, at order 1 over r3, you have an integration constant, which will play the role of angular momentum. This is where it appears. And then the solution starts to develop logarithmic terms, sourced by this tensor DAB, which was in the transverse metric. Now, finally, you can solve the last Einstein equation, which is first order differential equation. It has one integration constant. It has this expansion. The integration constant sits here, and it's the mass of the solution. Now, once you have done this, you have essentially solved, you see, for the 4 unknown functions. They're all determined, so we have determined the solution. However, we have clearly not solved all the Einstein equations. Therefore, the question is, what is contained in the other Einstein equations? Because we have already fixed everything, so what's in the other equations? Well, very interesting information. So what type of information? So now you have to look at the purely angular Einstein equation, EAB, so the equation on the asymptotic sphere. At leading order, this equation takes this form. It's a very interesting equation because it involves the shear, the time derivative of the leading metric on the sphere, and this integration constant U0. You see, if you are in the flat case, if lambda is 0, you just get here on the right-hand side a constraint on the time evolution of QAB, relating it to U0. Typically, people actually fix QAB to be time independent. U0 is set to 0, so this equation is not even here. It's automatically satisfied. But importantly, you see that if you have cosmological constants, this equation is telling you that CAB is not an independent quantity in the solution space. You cannot treat CAB and QAB and UA as independent variables. What you have to do is replace CAB by 1 over lambda times what's here. So loosely speaking, you can think that the shear CAB is not an independent data if you are in ADS. It is in flat space-time, but not in ADS. So already showing that there is crucial difference between the flat case and ADS. Now at next order, you get this equation, lambda DAB equals 0. Now recall that DAB, where it appears here with a logarithmic term. So now in the flat case, this is trivially satisfied, 0 equals 0. But if you have non-zero lambda, this equation is forcing you to set DAB to vanish. This means that this logarithmic term is not here if you have cosmological constants. In fact, you can look everywhere in the solution space. You go to very subleading order. You will see everywhere equations popping out, telling you that if you have lambda, you can have no logarithmic terms. This is just the translation, if you want, of what's actually a theorem, known as the Starobinsky theorem for positive lambda, and the Pfefferman-Graham theorem for negative lambda, saying that the most general solution in ADS has no log terms. Here you just recover this from the structure of the Einstein equations. Well, now you go further. You see the first equation has to do with C, the next with D. So the next one will have to do with the tensor I called E. Before that, you have another equation, which is a time evolution equation for this tensor DAB. Again, if you are in ADS or DS, this equation, there is nothing here. DAB is 0. If you are in the flat case, you get an evolution equation for this DAB sourcing this log here. This is an equation which was already obtained by Winnicourt, I think. Yes?
Asymptotic ADS, you mean locally flat ADS in the sense that it's a spherical ADS.
Yes.
Not with those other exotic topologies.
Yes.
I mean, or is it a local equation? That's, I guess, what I would ask. I mean, does it matter what the global boundary topology is, or is it independent of that?
So this is asymptotically locally ADS.
Okay.
Now at next order, so we go down C, D, you have an equation for E. I don't write this equation for the moment and tell you the meaning of this equation, but just, you see the structure is kind of logical. You go down in these Einstein equations, you constrain C, D, E, you have some evolution equation. This equation has only kind of received interest recently, and it's interesting because it's just one of the Einstein equations, so the question is what is the content of this Einstein equation? Now, in fact, at order n, in this Einstein equation, you have this pattern. This pattern is very interesting because, again, it tells you of a difference between the flat case and the DS or ADS case. In fact, this equation always has this structure. There is time evolution of the tensor appearing in the 1/n expansion of the transverse metric. And on the right-hand side, you're relating this to a term, a subleading term in the transverse metric, times the cosmological constant. So if you are in the flat case, if lambda is 0, you are forced to interpret these equations as evolution equations for this data here. It means that all this tensor here, well, you can only specify initial data, and then you have an evolution equation in retarded time. But if you are in DS or ADS, the interpretation changes radically. In DS or ADS, these are not evolution equations for these tensors. These are equations which algebraically determine all the subleading tensors from just a few set of overleading tensors. So in summary, you can say that in ADS, there's a finite amount of data, in fact. All the subleading data in this angular expansion is just determined by completely overleading data. And again, here you see a striking difference between the flat case and DS or ADS. In DS or ADS, there is finite data, in a sense. And in the flat case, there is infinite amount of data, and which is constrained by infinitely many evolution equations. So there is this tower structure of evolution equations. And now we are still left with two equations. One of them is the U and angular equation. This gives you the evolution of the angular momentum. So, okay, it has some right-hand side, which I will not show, but in the UU here now you have an important equation, which is the evolution of the mass. So in this general context here, where I keep, this beta 0, this U0, lambda, time dependency in Q, and the logarithmic terms, these are very complicated equations, which is why it's better to use Mathematica to extract these equations. But of course, if you go back to the case of vanishing cosmological constant, for example, this equation is something very famous. It's the so-called Bondi mass loss. It's this equation which relates the evolution of the mass to this. So here there is a divergence on the sphere, and here crucially there is minus the news squared. So this is the equation which, of course, Bondi was very happy when he found this, because that's the equation saying that the mass is decreasing due to the emission of gravitational radiation.
Actually, the person who found it was Trautmann. He was very happy.
Okay. Okay.
I sort of, sorry. But I mean, what you say in the lambda equals 0 case, I completely agree with. But with lambda either positive, negative, particularly positive, I mean, you can do these expansions, but they don't have any invariant meaning. And as you pointed out nicely, that several Roger and then other people following him who have given geometrical meaning to the time back in the 0 case. But in this case, for example, you say mass and you say momentum.
Yeah.
There's no symmetry that's
Yes.
associated with it. So these are just coordinate quantities which are looking for the source. So to say.
Yes.
Okay.
Yeah, I absolutely agree with that. Yeah.
There's a difference between
Yes. No, I absolutely agree. Yeah. So which is one of the motivations to better understand the lambda non-zero case, because precisely there is no geometrical meaning to these quantities, which is why one should actually work on this as you do. And yes.
One of the slides you had E and the log term.
Yes.
It appears on the right-hand side there.
It appears in here, in this evolution.
Not in the D. In the D equation.
Also in the evolution of no, not in the evolution of D. Yeah. I can show you if you want. Yeah.
Very quickly, just I'm trying to clear up my confusion with the first slide.
Yeah.
So because you said 4 free functions.
Yes.
Now the GAB is also a function within term.
So the 4 free functions were these functions of R. Now we have fixed this R expansion. Yes. Now we have only functions of the angles and retarded time. Now there is 2 types of such functions. There are functions which satisfy no evolution in U. For example, the shear. You see there is no equation, well, in the lambda equals 0 case, there is no equation for the shear. So shear is completely free on Scri+. And then there is data which satisfies evolution equation in U. And for this data, you just need initial condition. For example, this data, the mass, the angular momentum.
But I can still think of the other Einstein equations determining now these free functions, whatever the other 2 variables.
So which Einstein equations and which functions?
So the EAB Einstein equations, they now determine the GAB.
No, GAB, because this term is not here. So these equations are just equations, evolution equations, which have to be satisfied by the GABs. Just like the mass has to satisfy this equation. The momentum, there is an equation which it has to satisfy. It's the same status for these equations in the flat case.
Is there consistency in the evolution equation of DAB? If I multiply by the cosmological constant, then we have del U multiplied by lambda DAB is dot into lambda.
No, because this
DAB is 0.
no, because this equation here only appears after E.
No. Above the evolution equation of DAB.
Yes.
If I multiply by the cosmological constant.
Yes, there's a consistency. Yes. Yeah, of course. Yeah. Yes. Yeah, sorry, I didn't flash these things, but I can show you. Yeah. Yeah. The most general case, del U dAB is not 0. I can show you why, what is sourcing this equation, but yeah. If you don't have log terms in the initial GAB, yes, then this is du d equals 0, yes. I mean, there are lots of particular cases here, and it's just, yeah. I just wanted to give you an idea of the structure, then you're free to kind of put, yeah, Wolfgang?
So you say CAB not free in ADS.
Yes.
But still there is free radiative data on the NAR cone or the NAR surface, also for lambda, not for non-dimensional lambda.
Yes.
So where is this now encoded?
Well, the question is exactly this, is in what now, what fields you are going to put this data. So for example, you could put it in du of QAB, or you could put it in U.
So there's a choice.
Yes. I will go back to this in a minute. Yes, the tower of sphere modes in the flat case is here, yes. Yes. Okay, so now to just summarize this point, what I have shown here is just some extended solution space where you have lots of things turned on, and these things are just here because Einstein equations allow them to be here, right? All we have done so far is use the Bondi gauge and assumed an expansion for the transverse metric. So in particular, here you see the interpretation of these integration constants, B0 and U0. What they do, they actually parameterize the induced boundary metric on Scri. You compute the boundary metric on Scri. You see, it's essentially the form of the restriction to Scri of the metric in Bondi gauge, except that now you have beta 0, and here you have U0. And here you have the leading metric. So if you keep all these functions free, you have a free metric on Scri+. There is cosmological constant, time dependency, logarithmic terms. So of course, the early analysis of BMS does not contain any of this extra structure. In fact, even the leading sphere metric is fixed to a fixed round sphere metric. And this is, of course, not, I don't want to give the impression that this is because BMS, they forgot something. Of course, it's the other way around. It's because they were clever enough to just select precisely the right amount of, the right setup, the right metric, and the right conditions such that you can describe gravitational radiation and learn something useful without any of this decoration. So they were careful enough to not put extra stuff that a priori we don't care about. Yes, and in this case, so that's the kind of typical case. So in BMS, it's lambda is 0. You don't have any of this extra data. You just have the mass, the angular momentum. Again, this data is subject to evolution equations, and this is the data which is completely free. So now what is the role of these various extensions included here? All this extra stuff that I have added in the solution space, what is the role of this? So of course, lambda, you have to include it if you would like to study symmetries and charges in the ADS case, radiation and memory effects. Of course, it would be desirable to have a geometric setup, which enables you to work without coordinates to make rigorous statements. For example, this field U0 has been used recently by Beatriz Bonga, Claudio Bunster, and Wilfredo Perez, precisely to describe radiation in the DS case. Beta 0 has been used recently to describe interesting shockwave geometries related to the memory effect. Time dependence in QAB, this is what you would include to describe Robinson-Trautmann solutions. Importantly, so this was important work, maybe Alok will mention it, by Alok and Miguel. One of the motivations for relaxing already the leading metric on the sphere is to account for the subleading soft graviton theorem. Metric on the sphere is to account for the subleading soft graviton theorem. Another point is that if you keep the metric on Scri plus completely free, this I suspect that you could use this to maybe, in a sense, close a radiative system, because you have extra data on the boundary whose time evolution is not specified. So you could fix this time evolution such that the radiation that comes out, you encode it in the metric on the boundary. I can give more details later. Now there are also these logarithmic terms which I have included. Again, there are some physical motivations for including them, because although typical systems for which we study gravitational radiations are black hole binaries, you can also have setups, for example, such as hyperbolic encounters of black holes. And this would just be like hyperbolic scattering in the Newtonian theory. There is a tail which is logarithmic, and this naturally produces logarithmic terms. So that's one of the reasons to kind of try to extend this analysis of the solution space and the symmetries and the charges to the presence of these log terms. Also, probably Alok will mention this tomorrow. There are logarithmic corrections in the logarithmic terms in the soft theorems. And also I mentioned in the beginning the Newman-Unti gauge. One reason to consider also this is because if you, for example, gravitational wave people like Blanchet, Fay, what they usually do to characterize the source is they work in harmonic gauge. And if you want to match with data at Scri plus, it's kind of easier when you come from harmonic gauge, you end up with the Newman-Unti gauge and not with the Bondi-Sachs gauge. Then you can do a diffeomorphism from Newman-Unti to Bondi-Sachs, but I will briefly mention this later. This diffeomorphism is charged, in fact. So there can be some subtleties even here if you want to talk about the charges, because you have to worry about how the charges transform under such a diffeomorphism. And there are also some subtleties here. So that's why we also included in this general analysis the possibility to describe the Newman-Unti gauge at the same time as the Bondi-Sachs gauge. Okay, so now I want to write the equations of motion, and I want to advertise that to do this, it's kind of very interesting to use the Newman-Penrose formalism. So maybe it's a motivation to study the Newman-Penrose formalism. If you haven't done so, you can look in the book by Chandrasekhar. It's really nicely explained. So just briefly to mention the ingredients, you may know that for the Newman-Penrose formalism, you pick up a null tetrad and you project the components of the Weil tensor. When you do this, you find the so-called complex Weil scalars, which in this case at hand here for us, the Weil scalars have this expansion here. I will explain in a minute this expansion. But essentially in this expansion, there are several things to say. The first thing is that there is a behavior of the Weil tensor, which is called the Penrose-Sachs peeling. This behavior is that psi 0 is 1 over R5, psi 1 is 1 R4, here is 1 over R3, R2, and 1 over R. This is the so-called peeling. Here you see that the peeling is explicitly broken because we have included these logarithmic terms. And there is no other source of violation of peeling here. It's not due to the time dependency of the metric or to cosmological constant or to the choice of gauge or anything. It's purely due to these logarithmic terms. And you have full control onto how the peeling is actually violated. So this setup was called logarithmic asymptotic flatness by Winnicourt. And again, there's many people who are motivated to study this a bit further. Now I have to tell you what these curly quantities are. Essentially, you will see that M is some enhanced version of the Bondi mass, P is some enhanced version of the momentum, and EAB, curly, is some enhanced version of the EAB that we had previously. In fact, even though I haven't talked about the asymptotic symmetries yet, there is a very beautiful symmetry argument which says that, well, imagine you knew the asymptotic symmetries. If I jump ahead of myself, part of the asymptotic symmetries here are diffeomorphisms of the sphere and Weyl rescalings of the boundary metric. You could ask, well, in the solution space, are there fields which transform nicely, meaning as primary fields, like you would look for in a CFT, under these asymptotic symmetries? And if you look for fields which transform as primaries under the asymptotic symmetries, well, you find these quantities here. It's not surprising, in fact, because these are components of the Weyl tensor. But if you did not know that they were in the Weyl tensor, that's the explanation. In fact, for all these observables, the conformal dimension is 3, and there is a label which is the spin. You see that the mass here is spin 0, momentum is spin 1, this is spin 2, and then there is a tower, which I will mention a bit later. Now let me just set these things to 0 for simplicity, because I don't want to clutter the slides too much, and explain what you can read further. Well, first I give you the form of these covariant functionals. So as I said, M is just the Bondi mass, but now shifted by some term involving the news and the shear. P is again the initial angular momentum shifted by some quantity. E is a shift of the initial E. Curly J is the divergence of the news, and curly N is the time derivative of the news. There's also some complicated lambda terms and DUQ terms. Typically from this, what you can get, some interesting information is to ask, for example, about the mass loss and the symplectic structure. So the mass loss, for example, if I introduce this quantity, curly S, which is this curly N, so the radiation in Newman-Penrose, plus lambda squared times E, you find that the Bondi mass loss takes this general form. And here I call it loosely Bondi mass loss because, of course, as Abai mentioned, in the case DS or ADS, this has no real interpretation as a mass loss because the right-hand side is not negative definite, so it's not like the mass is decreasing like in the flat case. But still, there is this kind of compact general formula, which in the flat case reduces to the usual Bondi mass loss. Now, in the flat case, you can ask what is the symplectic structure on Scry, if you wanted to go ahead with, for example, Abai's asymptotic quantization. In the flat case, the symplectic structure is just saying that CAB is conjugated to the news. This is the Achtekar-Streubel symplectic structure. And in the lambda non-zero case, you find that the symplectic structure is telling you that QAB, so again, now CAB is not free data in DS or ADS. Now, in a sense, what plays the role of C is encoded in QAB, an overleading term in the metric. So you have QAB conjugated to this tensor SAB here, which is this radiation plus this cosmological term. So you can construct quantities like this, which you see if you were to construct this without using these covariant functionals that you get from the Newman-Penrose formalism, these equations would be extremely heavy and you would not really kind of be able to compare and see the structure in these equations. Yes? Yes, in fact, if you, on the previous slide I mentioned compare Fiorucci, Ruzziconi. They derived the symplectic structure coming from Pfefferman-Graham and doing a diffeomorphism to Bondi gauge. If you do this, you get the same result. The problem is that when you do that, you're missing some terms such that it looks like the flat limit is not well defined because you end up with this and then you have 1 over lambda. You cannot take the flat limit. So it's, yes. Yes, yes, this thing is yes. So now let me turn off the cosmological constants I turn off little by little all the fields and which also tells us what we should do to generalize this. So I turn off some fields. Now we can ask about the evolution equations.
How did you construct those covariant functionals?
You just compute the Weyl tensor and they just appear. Yes, yes. Or you could use this symmetry argument. Ask what are the observables which are
Can you go back to the last answer so we understand the question?
Yeah. He's asking how do we get this? So we just read this from the Weyl tensor.
Is there natural relation to the boundary stress tensors? If you contract the boundary stress tensor in FDP,
Yes, yes. But probably that's easier to do in Pfefferman-Graham because talking about the stress tensor is harder in Bondi gauge. So, but yes. Now I want to repackage a bit the evolution equations because I still haven't talked really about the evolution equation for the mass and Well, I gave the one for the mass here, but there is also the momentum, and EAB is also evolving. So to write the evolution equations, you can actually rewrite this Newman-Penrose expansion in terms of these so-called helicity-weighted scalars. Because if you remember on the previous slide, in the expansion of the Weil tensor, there is the frame on the sphere which is appearing, together with the complex conjugate, and you can think of this as trading the spin of the object for some helicity, so positive or negative helicity. And typically in the leading order here, in psi 0 you have this EAB, so it's EAB, so it's a spin 2, which is now helicity 2 object. The angular momentum is helicity 1, the mass is helicity 0, curly J is helicity -1, and curly N is helicity -2. And then you also have... Yes, here I have switched off lambda, yes. Although actually it doesn't matter here because the expansion is the same even if you have lambda, but... Yes. But for the evolution equation that I will display, lambda is turned off, yes. And just to remember in terms of what I said earlier, in this solution space there is completely free data, and there is also data for which you need initial condition. So where does this sit? The completely free data is here. So the shear is here and here via the news, and the data for which you need initial condition is here. Mass, angular momentum, EAB, and then FAB, GAB, HAB. Here is this tower of tensors in the transverse metric. So this is what we call the incoming radiation. Now you may also be familiar with the so-called Newman-Penrose charges. So Newman and Penrose, they exhibited interesting charges which have the property of being conserved in the, absolutely conserved in the linearized theory. And in the nonlinear theory, there's just a subset of them which are conserved. These Newman-Penrose charges, they sit in this expansion which is here. Now what is kind of beautiful is that if you just denote now the shear, again I use this indexless structure, well the asymptotic Einstein equations, at least up to order r minus 3, so for this guy, this one, and this one, they take this extremely compact form here. So it's a very beautiful repackaging of the Einstein equations, which, okay, you have the time evolution here. Here I should have said this et is this Penrose covariant derivative on the sphere. Here we have the spin which appears, the shear, and q of spin s minus 2. So you have this beautiful evolution equation, yes. And again, this nicely follows, you can recover this from a simple symmetry argument. You can ask now, again, I haven't mentioned the asymptotic symmetries, but you may know that in the asymptotic symmetries, there are also asymptotic time translations along in the u direction. These are so-called super translations. And if you ask in the solution space for the quantities which transform as primaries under super translations, you essentially single out these evolution equations. So now I just want to very briefly mention the content of this structure here. So as I wrote before, these equations, they have this form only up to spin s equals 3, only when you go up to this tensor, this quantity which is here. For spin s minus 1, this equation is in fact tautological. It just follows from the definition of curly j and curly n before. But the first three equations are just the evolution of the mass, the angular momentum, and the spin 2. So these are a tight, compact repackaging of these evolution equations. Now there is some extra structure, namely that if I define now these renormalized charges, so I cannot work with Q, but I work with these charges which are some combination of the initial charges with some time dependency. I define these little q's. Well, these little q's, you can show that they are functionals of the news and the shear, so you can act with them on the radiative phase space. And essentially what Q0 and Q1 do is that they generate super translations and super rotations. And similarly, you can ask if, for higher spin, these charges generate some symmetries. And in fact, you can think of them as generating some transformations, but as opposed to super translations and super rotations, these transformations, they act actually non-locally on phase space. So they are a bit kind of strange charges from this point of view. What you can also show is that from looking at the conservation of these charges through I naught, so from scri minus to scri plus, essentially the conservation of these charges implies, well, sometimes people say loosely that it implies the sub S leading soft graviton theorem, but this was only shown up to spin 2. So the leading soft graviton theorem, sub-leading, and sub-sub-leading. And if you look for higher spin now, if you work out carefully what this evolution equation is for the rest of the fields in this tower of higher spin quantities, Well, you find that this equation actually fails for higher spin. After spin 3, this equation has extra terms here. But I mentioned this because recently you may have seen that there was this kind of discussion people have discovered through a completely different route, namely through the OPEs in celestial holography, and also people from twistor theory. They have kind of argued that in the self-dual theory, or the theory in the sector in which you neglect one of the helicities of the graviton, so the single helicity sector, there is a huge symmetry which is precisely generated by this tower of higher spin charges. And if you use this first point here to compute the bracket of these charges, it's a kind of complicated proof, but you can recover this, the bracket of this so-called W1 plus infinity symmetry. But from the gravity, so as I said, these proofs, they come either from celestial holography, they have lots of extra structure, or they come from twistor theory, and they have also some structure which is not available here. So the natural question is whether you can actually recover this proof and see what is the meaning of this symmetry really from this point of view, from the point of view of the gravitational phase space. And this is not so obvious because, as I said, this pattern fails. And if you want to prove this symmetry, you have to assume that this pattern holds. But there is subtlety because to write this pattern, you have to make a careful choice of Newman-Penrose tetrads, and this equation is sensitive to this choice of Newman-Penrose tetrad. So there's a subtlety in how to actually go about to showing this. Maybe I can say this later because, yes. I can tell you there is a subtlety, but yes. And now I think I will soon run out of time. But so now I have to mention the asymptotic symmetries because I have not mentioned this yet. So the asymptotic symmetries, so again, here we're not using this geometrical approach of Abai and Penrose and Guéroche. We're using coordinates. We're using a gauge fixing approach. So the asymptotic killing vectors, they are just the vectors which preserve the form of the metric, the gauge, and the follows that we have chosen. If you look for these vectors, you just have to solve this asymptotic killing equation, and you essentially find that the vector is given by this.
You're again restricting to lambda equals 0.
Yes, I'm again, yes, sorry. Now, since before, it's lambda equals 0, yes. Yes. Although this, strictly speaking, this would be true even with lambda, because this...
I mean, so up to some place it might be okay, but then after that, it cannot be okay. So.
Yes, I mean, at leading order, this is... because this just follows from preserving the Bondi gauge, right? Which is true even if you have lambda. But yeah, we can... Okay. Now you can look at the algebra spanned by these vectors, and this is, well, what people call now the BMS Weil algebra. And yeah, so the BMS itself is generated by these vectors on the sphere, so dFS2. The Weil part is generated by this quantity W here, and the super translations are generated by this T, which is here. And again, these are angle-dependent quantities, which is why they are super rotations, super translations, and super conformal transformations. And now from here, you can kind of restrict or recover or understand why there were initial restrictions to historical BMS and then extensions. So for example, if you look at how the leading metric transforms, you find this, and the volume transforms like that. So if you were in the initial historical BMS setup where QAB is fixed and the volume is fixed, this would have to be 0, this would have to be 0. This would constrain the Y's to be conformal killing vectors. They would only span the Lorentz group. This is why the historical BMS group is just super translations and Lorentz transformations. You don't have super Lorentz transformations.
What is capital T?
Capital T is the super translation. Yes, arbitrary function, yes. But then motivated by kind of flat space holography, Baramish and Trossard have kind of suggested to, instead of using conformal killing vectors, using meromorphic killing vectors, then you get Virasoro algebra here. Then Miguel, Alouk, and Compere and his students proposed an extension to all of dFS2. This is if you keep the sphere metric completely free, you get all of dFS2. And then if you allow for the volume factor to be also to vary, then you get also Weil transformations. So this is the Weil BMS group. And in fact, I mean, this is not yet published, I should have written, but you can even exhibit a gauge in which you enlarge even further the asymptotic symmetry group. And what you can show is that this actually stops somewhere. There is kind of a maximal amount of symmetries which come with a non-vanishing asymptotic charge. And when you do this, you get an extra factor of R2 here. So there is 2 extra abelian symmetries, and this is what you get. And this is kind of nice because it starts to look a bit more closely like what is known as the quasi-local symmetry group. You can also ask, from the local point of view, if I don't put any boundary conditions, which symmetry group can I assign to finite surfaces? Naturally, this is here because dFs2 are just tangent diphios of the local sphere. SL2R are boosts in the orthonormal plane. And this R2 is due to time translations and radial translations. So kind of intuitively speaking, this is what you get locally, and this was proven by these people. So yeah, you can exhibit a gauge in which asymptotically you get something which is almost this full local symmetry group. Yeah, now I will just stop with this mention of the charges. So if you were now to compute the asymptotic charges, well, to do this, there are many ways to do it, but a very powerful, convenient way is to use this so-called covariant phase space formalism. So how this works, so for this, you just have to recall how Noether charges arise from the Lagrangian. If you remember, you have these 2 formulas. This is a very useful formula for the variation of the Lagrangian. It gives you a boundary term here. If you act with a diffeomorphism on the Lagrangian, you get this boundary term. And now the Noether charge is essentially defined like this. You evaluate this boundary term on the Lie derivative, and you subtract this boundary term. And now the second theorem tells you that this is a total derivative. So this K is the Noether charge. And then there is this ER-Wald procedure to compute the asymptotic charge. And using the Noether charge and the potential, the asymptotic charge at Scri plus is essentially given by this. The important point, the subtlety, is that you see that the asymptotic charge is not only given by the Noether charge, there is also this contribution here. And because of this contribution, well, the charge may not be integrable, may not be delta exact on phase space, meaning that for the symmetry that you're looking at, there may not be a Hamiltonian generator on the phase space. And if you want to compute this charge, in fact, for the general setup which I showed, with this free leading boundary metric and logarithmic terms and cosmological constants, there's lots of kind of subtleties of the covariant phase space that you have to work through. And this also explains why recently you probably saw so many papers on the covariant phase space itself. So you have to understand all sorts of subtleties. But again, if we go back to the historical vanilla BMS case, where I turn off all these extra decorations, the result for the charge is this. Just the only thing to see here interesting is that, see, as you expect, together with the translations, you get the mass. So symmetries go hand in hand with some function in the solution space. Translation goes with the mass. Super rotation goes with the momentum. This term is integrable, is delta exact. And then you have, importantly, a non-integrable term, which is precisely sourced by the radiation. So the charges fail to be integrable because the phase space is radiative. And it's sourced by the shear and the news here. And now you can define what is known as a Wald-Zupas charge, namely a charge which is conserved in the absence of radiation. That's a reasonable physical requirement, that you select the integrable part of the charge, Q0, such that when you evolve it, it's proportional to the news. So if the news is 0, the charge is conserved. Now, a last thing which I mentioned, which you may want to compute to finally have some nice structure, is to compute a bracket of these charges, because this is what will give you the algebra of asymptotic symmetries. But we have a problem because the charges are actually non-integrable, and so because they're non-integrable, it's not obvious how to define a bracket for these charges. So we need a prescription for this. There is a well-known and used prescription known as the Barney-Strossard bracket. This is essentially a prescription which tells you how to compute the Poisson bracket between these integrable parts of the charges, which are conserved in the radiative vacuum. And there is a very powerful representation theorem which tells you that, in fact, you can expect that the algebra of asymptotic symmetries, so the asymptotic charges, will represent the symmetries of the vector fields, which are the BMS symmetries. So we'll have a charge representation of this algebra, which is given by this, plus potentially a term which is a cocycle, so a central extension. And okay, I just mentioned this briefly because it's work in progress. I can tell you more detail, but the Barnish-Trosset bracket suffers from the fact that it actually depends on the split between integrable part and flux. There is recently now a new proposal known as the Causal bracket, which is insensitive to this split. And this is a better candidate for computing the charge algebra. Yes?
All these formulas will give you the raise to the n momentum charge.
We give you, sorry? What?
So, Amitabh, can we just hold till the question session?
Yeah,
We're
we'll
running
conclude
a bit
now
late.
because, yes. Yeah, so I will go through this, but we can talk if you're interested. I just wanted to mention 3D gravity because this is maybe, as a Bai said, this could be thought of as the harmonic oscillator of all these studies because 3D gravity is simple. There are no degrees of freedom, so you can, even though it has no degrees of freedom, it has interesting boundary symmetries. In the ADS case or in the flat case, there is BMS3 symmetries, and a lot of things are understood, and more things are understood and under control in this three-dimensional case. For example, you can do...
So Mark, I mean, just complete your talk.
Yeah,
Don't worry. We have extended lunch by a little bit. So,
okay.
So, yeah. Go ahead.
No, but it's already too long, so we can discuss. Yeah.
Okay.
The last thing I wanted to flash was this 3D Einstein-Maxwell. I will skip over the results, but again, if you're interested, we can discuss this. So just what I want to mention is that in 3 dimensions, you can introduce a degree of freedom if you do Einstein-Maxwell. 3D Einstein-Maxwell has a single helicity photon. There's a single degree of freedom. You can use boundary conditions for the Maxwell field, which are radiative. Here you have Coulombic data in here and radiative data in this C. If you compute these Newman-Penrose Weil scalars for the Maxwell curvature, you have Coulombic data and radiative data. What is interesting is that with this model, you get a dimensional reduction of 4D gravity with gravitational radiation. For example, you have a Bondi mass loss, which is now sourced by the electromagnetic radiation. So because of this, this is a toy model which has all the features of the 4-dimensional theory, except the geometrical setup is simpler because it's 3 dimensions. And the last thing why I wanted to mention this is that there is something which is mathematically not very well understood, which is where I would like to go next, is that if you compute these charges, of course, as you expect, they are non-integrable because there is radiation. As in the 4-dimensional case, this non-integrability is sourced by the electromagnetic radiation now. And if you compute the bracket of these charges, well, again, you find this says that it represents the symmetry algebra, which is BMS3 plus U1. But there is a cocycle, which importantly is field dependent. The cocycle itself depends on the point in phase space. It depends on the fields through this Coulombic data. And when you encounter this, it actually means that the structure is not really a symmetry algebra, but it's an algebroid. And so if you wanted to study the representation theory of such an object, it completely goes outside of what has been done, for example, for BMS3 and BMS4. So, and yet this is a very simple setup where you have to face this fact that the asymptotic symmetries form an algebroid and not an algebra, which is something that has not been studied. And the very last thing I mentioned, sorry, is that you can also compute here the memory effect, because there is also an electromagnetic memory effect. This memory effect in electromagnetism is essentially, you take the Lorentz force law and you compute how the relative velocity of 2 charged particles changes in the angular direction. If you compute this, you find that, as you expect, this is sourced by the electromagnetic radiation, the electromagnetic shear. However, here, the electromagnetic shear, so what appears in the memory formula, is not what appears in the charge of the large gauge transformation, unlike in 4 dimensions. This means that in this example, there is a photon, so there is a soft photon theorem, there is an electromagnetic memory effect, which is here, and there are asymptotic symmetries. However, the asymptotic symmetries have nothing to do with the electromagnetic memory effect. And this is due ultimately to, in fact, the fact that in any dimension other than 4, Coulombic and radiative behavior have different fall-offs. And this is essentially what you see here. Because of this mismatch of Coulombic and radiative fall-offs, the 3 tips of the triangle, they exist, but the connection with asymptotic symmetries is meaningless because, yes, the memory effect is not related to the U1 charge. So that's an example of a subtlety when you look at this asymptotic infrared triangle, because things might not work the way that you expect them to work. Yes, so this is just to conclude, to mention some interesting prospects which some people are working on. The last thing I wanted to say is that I don't want to give the impression that we can relax all sorts of things and go in all sorts of crazy directions. So now we should choose, I think, between mathematics and physics, in the sense that we should choose between doing what some people do, which is proving some rigorous mathematical statements about the geometrical structures which are at play here, for example, in DS or ADS. This one can do. And if we do not do this, we should actually focus on really seeing if these things have physical effects. For example, these logarithmic terms, what is the physics encoded in these logarithmic terms? And one should choose between doing this or that and not stay in between like I've done here. And thank you for your attention. Sorry.
Thanks a lot, Mark. No, thank you so much for this nice talk. And we'll go to questions now. Sumati.
Just a very quick naive question, which is to do with, you know, the Troutman, Bondi mass, the news function, that relationship. In the lambda less than 0 case, so we have the Ashtekar-Magnon mass also, mass function. Are there relationships like this even in the ADS case? Because there again you have the Weil tensor being used in something which is a function. I mean, it's a general mass function, so I was just wondering, are there equivalent things?
Yeah. No, unfortunately, I did not compare this here. So, yeah, I don't know, fortunately.
I think they are. In 4 dimensions they are. In 4 dimensions they are. In higher dimensions, we can talk about it because there was, in my view, some. I mean, the thing is that you have to do some usual way of doing it. You have to do this subtraction procedure from the stretch-Lie tensor, and there is an ambiguity in the higher dimensions, and we can talk about that more. But yeah, in 4 dimensions they are.
Okay, so first I have to object to your final statement. We don't have to choose between mathematics and physics. that would put me out of business immediately.
Yeah, me too, obviously.
but more on the serious note. So the discussion about, like, you know, various Poisson structures, brackets, algebroids, and so on. So do you know this work of Aldo Riello and Michele Schiavina?
Yeah.
So, I mean,
I've seen talks and heard of it, but I cannot say that
for me personally, it seems like a nice sort of framework to actually address these questions, like, you know, what's the correct bracket and how it relates to other structures and so on. I thought, so you mentioned that the Causal bracket at the end, and I thought that this kind of might be related to what they have done, but I don't know the work you mentioned, so I was wondering what's your feeling?
Yeah. So to be honest, I did not compare yet with the work of Aldo and Enrique and Michele, but yeah, it could be related because
it's long, but worth reading.
Yes. But also to translate it to this setup is a bit, I think requires some work. So
yeah, no, because they also use this covariant phase space formalism. So I thought that, okay, thank you.
But that would be interesting.
You mentioned the symplectic form on scry in the flat case and asymptotically flat case and asymptotically non-flat. So in the asymptotically non-flat case, you have to subtract some infinities to define it.
Yes, the symplectic structure has divergent terms in the, yes, that's true. Yes.
Just.
You can define symplectic structure without any algorithm whatsoever, lambda, positive or negative case.
Yeah. I mean, to say what this object, what I wrote here, this is just essentially the radial component of the symplectic potential. And if you just compute blindly this is divergent, but at you can subtract counter terms, but at finite order you get this. Yes.
You can do it manifestly finite without any subtraction whatsoever. That's what I'm claiming. So there is symplectic structure on scry, and for example, in the DS case, which is just defined, well-defined period. It's not defined in this way, but it's delta QAB times there will be the electric part of the times the electric part of the Weil tensor, and that would be well defined without any counter terms. So
I think that can be related to this.
Yeah, it can be, but I mean, I'm saying that counter term is not essential.
But if lambda tends to 0, does it go back? Lambda tends to 0, does it immediately go back to lambda equals 0 case?
Well, not like this, but if you want to take this limit, you have to undo the fact that to write this, I had to trade C. Yeah, there is this equation, lambda CAB equals something. I had to invert this equation. So you have to use this equation again to put lambda upstairs. And yes, but you can do it, yes.
So Mark, maybe related to Kasia's question also, that if you look at the, if you go from asymptotic symmetries, you really only get charge at u equal to minus infinity sphere, or what we say we would get a flux. Right? And in scattering, the conservation law will only relate the flux. So these charges that you are now defining, which are not integrable on a cut at Scri, I mean, they don't really, I mean, having a co-cycle also, like, it doesn't really obstruct anything in the word identities of the asymmetrics, or in the conservation laws, for example. So I'm saying the charges we get from asymptotic symmetries are integrable, because those are really the charges which are fluxes, what we would call flux.
Yes, yes. If you work, yes, if you work with the fluxes, it's true that you don't have.
But that's what we would, that's what is conserved between in a scatter.
Yes, yes, yes. No, this I'm not arguing with this. Yes, that's true.
Okay, so I'm sorry, Amitav, last time you didn't get, but lunch is important. So yeah, so I mean, lunch is there. Do you want to make any?
Same place as the breakfast.
So on top of the astrophysics building, and we aim to convene here at 2:10, if possible. I hope so. And please thank Mark and all the speakers for the morning. Thank you. We'll have to lock up then.
behind is better than the front. Okay. Should I? It's just saying that if you don't mind the behind the desk area is better than in front, unless you really want
to
If it doesn't
prance
make a
about.
difference, she suggests.
I have to do some kind of interpretational dance, and I can come here.
Wearing your favorite pants.
Just show off.
So welcome everyone to the afternoon session. Hopefully everyone had a nice lunch. And if you skipped dessert, don't worry because you're in for a treat. So the first talk of the afternoon will be by Faye Dowker, and she'll tell us about causal horizon entropy in causal set quantum gravity.
Thanks, Yasmin. Thank you to Madhavan and Symmetries for all the work that they've done to create this wonderful meeting. It's really a joy to be back here at RRI in this beautiful place on this special occasion. So I chose a topic that hopefully will do the job of bringing together different approaches to the problem of quantum gravity. I'm going to talk about a specific one, causal set theory, but the problems that arise and the questions that arise are common to many approaches. And as you'll see, I don't really have a summary section, but just a set of questions, which I'm hoping to get all of your input on. I know there are experts on certain things that will come up here, and I'd like to hear your thoughts about some of the questions that arise in our particular approach. So here's the plan of my talk. I'm going to tell you two heuristics for working towards the statistical mechanics of black hole entropy. So it's a funny thing. We have the answer to a quantum gravity question, which is what's the entropy of a black hole. And it's a quantum gravity question. Well, it's the answer, and we know it involves quantum gravity because it has both G and H bar in it. But we don't have a full, agreed upon, fully working, successful theory of quantum gravity. So we have an answer to a question, but we don't have the theory that should give us that answer. And that's what many people in different approaches are working towards. And then I'll talk a little bit about how black hole, the event horizon of a black hole is an example, a special case of a more general concept, which is that of a causal horizon. I'll define that for you. I'll then move on and set out the causal set approach to the problem of quantum gravity very briefly. So I think I have 3 slides on that. So I know that there are people here who have heard many heard talks about causal sets and know this basic structure, but I know there are also young people who won't have heard about causal set quantum gravity at all. So I'm going to try and just give you the very basic ideas. I'll then tell you what a strategy is for work within causal set quantum gravity. The strategy is for working towards an understanding of the statistical mechanics of causal horizons, using the 2 heuristics, both of them. These heuristics that I will have given you in a moment. I'll then briefly tell you a little bit about how that strategy is working out. And then, as I said, I'm going to end with a bunch of questions which I would like to ask for your help on. And I'm going to take Boltzmann's constant to be equal to 1 throughout. And here just are some references which give the basic framework for trying to understand black holes and black hole thermodynamics by Raphael Sorkin, who's well known to many of you here. He's a regular visitor to RRI and loves it and is sorry not to be able to be here, but sends his best regards to his friends and colleagues here. Okay, so here are the two heuristics. Black hole entropy, as I said, it has a quantum gravitational value, and that value sets a scale, which is the Planck scale. So if we let the Planck length be equal to this combination of G and H bar, because amongst relativists we don't need to mention C, which is that's always 1. But I put this 8 pi G here, that's cosmologist conventions, so which is nice in this case because if you take the Planck length to be this, and then you take the area of the event horizon of a black hole in units of this Planck length, this one with the 8 pi G, then the entropy of the black hole is just the number of Planck area plaquettes tiling the horizon up to some factor of order 1. And with this particular convention for the Planck length, that factor of order 1 is 2 pi rather than the usual, the more common factor of a quarter. So you can see that's where the 8 pi G is just the factor relating a quarter and 2 pi. Anyway, I like 2 pi, it sounds more geometrical, so, so I prefer that. Okay, so that's the black hole entropy, or conveniently Bekenstein-Hawking entropy. So that's the actual answer. And I suppose I'll say a little bit more about when you don't get that answer just at the very end. But so the first heuristic is just to look at kinetic theory in the high temperature limit. So the entropy of a box of gas is proportional to the number of molecules. There's a temperature dependent prefactor, but if you double the number of molecules, then you double the entropy. So the first heuristic is let's look for horizon molecules and just count them and see what you get. And this heuristic is physical or physically motivated to the extent that you can think of the horizon as being at high temperature, which is obviously a bit contentious. I mean, from some point of view, it's at very high temperature for an observer who is stationary just outside the horizon. They will experience an enormous temperature. For an observer who's very far away, they experience the Hawking temperature. And if you're falling through the horizon, then the temperature is 0. So whether or not it makes sense to think of the horizon as being at high temperature, that's certainly debatable. But anyway, that's one heuristic. The second heuristic, which is slightly more sophisticated, is a Boltzmannian state counting. So if you really imagine that the black hole is tiled with these Planckian plaquettes, with little tiles, if there's a binary state, 0 or 1 on each plaquette, so you can think of that as these tiles being painted either black or white, then the number of possible tilings that you can have, of course, is just 2 to the n. And then if you take the log of that, then you get n log 2. So you again get something proportional to n with this prefactor of order 1. So the second heuristic is to look for such horizon states, try and identify what you might mean by a plaquette of the horizon and try and identify what it might mean for that plaquette to have a state. Oh, and then count them and take the logarithm, see what you get. Black hole event horizons are a special case of causal horizons. I should always put here black hole event horizons because there are other definitions of horizons for black holes, but whenever I say black hole horizon in this talk, I mean the event horizon. So one framework for understanding black hole thermodynamics is tied to the causal nature of the event horizon. It's defined in terms of the causal structure. And I've just picked out one example of that, which is the understanding of Hawking radiation in terms of Unruh radiation. and Unruh radiation being related to the vacuum entanglement across Rindler horizons. And there's a unifying concept of causal horizons that was introduced by Gibbons and Hawking. Jacobson and Parentani have a paper which I think is just called Causal Horizons, or maybe Thermodynamics of Causal Horizons, but they stress that black hole event horizons are special cases of these causal horizons. And a causal horizon is the boundary of the closure of the causal past of a future infinite time-like curve. And you can think of that as just some observer that lives forever. So some observer in a black hole space-time that stays outside the black hole forever, the boundary of the causal past of that observer is the black hole event horizon. And causal horizons include black holes, but they also, including both stationary and dynamical black holes. So it doesn't matter if the black hole is has settled down or whether it's forming. That causal definition covers both cases. Rindler horizons, they're the infinite time-like curve is a constantly accelerating world line, and cosmological horizons, including de Sitter horizons. These are all conjectured to have entropy and to obey the laws of thermodynamics, suitably interpreted and tweaked where necessary. Turning this around, there's another popular heuristic due to Jacobson that the thermodynamics of local Rindler horizons is a more primitive notion than GR, that you can derive GR from considering first and second laws of thermodynamics of these local little pieces of Rindler horizon. And causal order, of course, it's not just important in black hole thermodynamics, but in classical GR too. Of course, when we heard this morning how important null geodesics and causal analysis is to GR. You just open any GR textbook and it abounds with Penrose Carter diagrams, the conformal diagrams that are pictures of the causal structure of space-times. And that was honored by the Nobel Prize in 2020 to Roger Penrose. Here's just an example, a representative light cone here. Black holes, of course, epitomize GR, and many results in classical black hole physics, the uniqueness theorems, no-hair theorems, Hawking's area theorem, they're all tied to this definition of the black hole event horizon in terms of the causal order. And also, there's a theorem which by now I've called it many things over the years, basically because I think I didn't understand the full history, and I'm not sure I do even now, but I'm now calling this theorem the Kronheimer-Penrose-Hawking-Malamud theorem. It's a series, the proof of the theorem is a series of results, as you can tell, over a number of years. But the theorem states that the space-time causal order, that's the information about which points in space-time are connected by causal curves and which aren't, plus the information about the volume of every space-time region. So in other words, if you know the volume measure, square root of minus g d4x in 4 dimensions, for example, if you know that, then you know the full geometry. There's some causality conditions on the space-times that go into this, that this theorem applies to. But for globally hyperbolic space-times, for example, obey this theorem. So the space-time causal order includes a huge amount of information. If you think about the volume measure as just being one function, just the conformal factor, then there are 10 functions in the metric. So that's in four dimensions. So in 4 dimensions, the causal structure is 9/10 of the metric information. It's 9/10 of the geometry. Okay, so I'm going to give 3 slides summarizing causal set quantum gravity. So it's an approach. It's not quantum gravity. We don't have a theory of quantum gravity. Quantum gravity is a problem rather than a theory. And the causal set approach rests on 3 pillars. The first pillar is that physical space-time is fundamentally discrete. And if you like, that's a repudiation of a physical for those of you of a philosophical bent, it's a repudiation of physical infinity, any infinity at all in anything physically relevant is going to be finite. The second pillar is that order is a more primitive organizing principle for physics, even than space or time or geometry. And it's the space-time causal order, which in the continuum you can think of as being synonymous with the light cone structure. Of all continuum space-time structures, it's what survives in the deep theory in quantum gravity. If you put these two things together, discreteness and order, you get a discrete order. And a discrete order is a causal set. Mathematically, there is a concept of order, and a discrete order is what is the definition of a causal set. So here's an example of a very small causal set. It has 5 elements. And the order relation is just indicated by these arrows. So we say that element D precedes element A, and element A precedes element B. And that order, by definition, a mathematical order, is transitive. So that means that D precedes B. But on the diagram, we don't need to draw the arrow from D to B because it's implied by the two that are drawn. So we save ourselves a lot of pencil by not drawing on the relations which are implied by the transitivity. So this is called a Hasse diagram for a partial order. It's a partially ordered set, or poset for short, and we call it a causal set or coset for short. What else should I? Oh, so there's no relation between A and C, as there's no ordered path of arrows that takes you from A to C or C to A. So they're not ordered, and they're the analog of space-like separated events. And yeah, this order, it's often called causal order, but cause and causal and causation, they're words which are overused, just like locality and non-locality. Exactly what someone means when they say something is local or non-local, you have to be very careful because different people mean different things. In fact, the same person can mean different things by them, depending on what time of day it is. So when I say order here, I just mean precedence order. So D is before A, and A is before B, and D is before B. A and C don't have any precedence order. It's not the case that A is before or after C. They just don't have an order. And there's no a priori notion of causation. So we don't say that D causes A. It's just that D is before A in this order. Okay. And the fundamental slogan of causal set theory is order plus number equals geometry. So building on the Kronheimer-Penrose-Hawking-Malamud theorem, we conjecture, we suppose, that the disorder between these discrete elements will give rise in the continuum approximation to the space-time causal order. And the space-time causal order, remember, is almost all of the metric information, but not all of it. You also need volume information. And the volume information in a discrete structure is given just by the counting measure. So if you want to know what the volume is of a particular region of space-time that corresponds to some subset of the causal set, you just count the number of elements in that subset, and that is the volume in fundamental units. So the counting measure furnishes the volume information that's missing from the causal order. So the order, so in the continuum you have the theorem order plus volume equals geometry. That's a theorem. In causal sets you have the conjecture that order plus number gives you approximately the continuum approximation, the continuum geometry that approximates that causal set. And then the third pillar, about which I'm not going to say anything, but in the talk by Steve Carlip, he's going to say something about the dynamics of causal set theory as a path integral, or sum over histories. But the dynamics, we believe, is going to be based on a path integral. And the path integral furnishes a framework for quantum theory that's a genuine alternative. It's not equivalent to the canonical psi framework. The idea underlying this is that quantum mechanics is a species of measure theory, so it's less of a generalization of classical Hamiltonian mechanics than it is a generalization of Brownian motion, or described by the Wiener measure. Okay, so a discrete order is a causal set, that's just its definition, and the physical idea is that the elements of the causal set, or space-time atoms, are indivisible, smallest events that you can't divide. Say the event of lunch at RRI today, that you can't divide that event. You can divide that event into smaller sub-events, which is I had the lemon rice, and you can divide that into sub-events of me eating one spoonful of the lemon rice, and just keep dividing it into smaller and smaller sub-events. At some point, there's some indivisible sub-event. You can't divide the sub-events anymore, and they are the space-time atoms, and they're the elements of the causal set. This proposal has been made many times, actually, probably more than the ones that we know, and that's a good thing, because if an idea is a good one, then many people are going to have it at various points. By Gerard Ethoft, by Jan Meerheim, by Bombelli, Lee, Meyer, and Sorkin, and Raphael has been the major champion of this approach to quantum gravity since then. Another synonym for causal set is transitive directed acyclic graph. I've already kind of described that. So the elements of the set are the nodes of the graph. The order relations are the edges of the graph. It's directed, of course, because the relation has an order, an arrow on it, and it's transitive, as I said. So D precedes B, even though on the graph, the picture, the Hasse diagram, I haven't drawn that relation, but it's there. And then the idea is that a continuum space-time is an approximation to a causal set. Of course, continuum space-time is not going to be a good approximation to a 5-element causal set. You're going to need a lot of elements to be able to reproduce the structure of a continuum space-time. And I've written this number here, 10 to the 240, that's the volume of the observable universe in Planck units, give or take a few. And so you'd need a causal set of this cardinality to be able to for it to have a continuum approximation that describes our observable universe. But the idea is that the causal order of the causal set gives rise in the approximation to the light cone structure of the continuum, and the number of causal set elements gives rise to the volume of regions of the continuum approximation. So a space-time, mg, is a Lorentzian space-time, is a continuum approximation to a causal set if, so I'm going to make this, what I've just said, a little bit more formal, if C is a uniform sampling of the causal order of mg. In other words, if you choose a bunch of points in the continuum space-time, you endow them with the order relation that they inherit from the light cones, and you make sure that the points that you've chosen are uniformly spread in the space-time. That is, for every region, there are roughly that volume's worth of the number of causal set elements that you choose from that region as given by the volume in fundamental Planckian units. Then that space-time is a continuum approximation to that causal set. So this is a conjecture. We call it the central conjecture of causal set theory, or Hauptvermutung, and there's good evidence for it. And part of the evidence is that Hawking, Kronheimer-Penrose-Hawking element theorem.
Sorry, I have a quick naive question.
Yes.
So does that mean that because the space is discretized, so you have this Planck scale volume element, is each event one-to-one associated with one of those Planck volume elements, or not?
No, it isn't. It's really a continuum approximation. So if you think of a fluid, the smallest unit of a fluid that makes sense is not a single point of the fluid, it's sort of a fluid element and in the fluid element, there are many, many molecules. So you can't think of the individual space-time atoms as constituting an element of volume of the continuum. That just doesn't make any sense. And in the same sense that a single molecule doesn't make sense as a unit of a volume element of a fluid.
But if we go to the fluid microscopic level, they're individual atoms, of course. So if we go to the microscopic level of this approach, how do these volume elements connect with these events?
So each volume, I mean, there will be some smallest meaningful volume elements, and they will have to be constituted by many causal set elements. Otherwise, it won't make sense as a.
Each of those small volumes are constituted of many causal sets?
Yes. So if you try to imagine the continuum broken up into a bunch of Planck-sized volume regions, you can't identify each causal set element with each of those regions, because a region of the continuum has continuum structure, but a single causal set element has no continuum structure. So you need it. Let's discuss it after. Ask me again. Yes?
Uniform sampling of the causal set, if it uniformly samples a manifold, then that is a good continuum approximation to the causal set. But what measure are you using while saying uniform?
The volume measure. Root manifold, yeah. Okay, so you might think that, yeah. I think the conjecture might be if and only if, but let me think about that.
Just to add, so the uniform sampling leads to a continuum of space-time without any metric structure, or you are implicitly assuming symmetry of emergent space-time as well?
So
suppose I would have gone non-uniform sampling, what would it lead to? If I would have gone for non-uniform sampling.
Oh, non-uniform sampling.
Would I not get continuum approximation, or I would get something with more drastic symmetry?
I think you wouldn't get a continuum approximation at all, because it would be something that's not a manifold. You would get something like a whole conformal class of metrics or something like that. So but yeah.
Next time anyone has a question.
Yeah.
Yeah. So. Thank you. Because the elements of the causal set is ordered, and the indivisible events, there is a notion of before and after. Does it mean one can glean a concept of time from this order?
That's a fantastic question, but it's not really a point of clarification. So I'd rather get to the end. So maybe we could save that for the discussion period. Yeah.
So,
it's a brilliant question, but yeah, it's sort of not germane to the. Okay. So because causal sets are discrete from the start, it seems like they are sort of well endowed for answering or addressing at least the question of the nature of the black hole, of causal horizon entropy, even in the absence of a full theory of quantum gravity or full theory of quantum causal sets. So just some comments about the area law. So the area law is not established physics in the sense of observation and measurements, but nevertheless in practice it undoubtedly plays a phenomenological role in many quantum gravity approaches. And we heard that from Abai's talk this morning. So the area law suggests that the entropy is a property of the horizon itself and not of any internal microstates. And that's particularly so if you take this more universal perspective on black hole event horizons as being causal horizons. So for a Rindler horizon, or even for a cosmological horizon, it's very difficult to imagine what one might mean by internal microstates. So if you hang your hopes for the understanding of black hole entropy on the horizon itself, then it's more likely that one will be able to understand the entropy or thermodynamics of causal horizons in general. And we're going to use the particular heuristics, heuristic 1, which was find horizon molecules and count them, and heuristic 2, which is find whole horizon microstates and count them, in pursuing an understanding of horizon entropy in causal set theory in the way that I'll describe now. So here's a strategy for understanding horizon entropy in causal set theory. So suppose we start with a continuum space-time which has a horizon, here it is, H, and we want to calculate or understand what the entropy is of that horizon. But entropy, of course, is entropy at a particular time, because, of course, you know, entropy satisfies the second law, so it has to increase. So you can't have entropy of this whole three-dimensional or codimension 1 hypersurface H. So it has to be entropy at a particular time. So we need a hypersurface sigma which intersects H. So let's take it to be a space-like codimension 1 hypersurface. And then that divides the space-time up into 4 regions. There's the past and future of sigma. There's the inside and the outside of H. They intersect in these 4 regions, which I call plus, 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 minus, 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 and minus, plus. And we want a causal set that could, this is supposedly in causal set theory an approximation, it's a continuum approximation, like a fluid-like description of the fundamental underlying structure, which is a causal set. What kind of causal set? Well, in order to get one, we're going to just uniformly sample, according to the volume measure, this space-time. We'll do a point process of choosing elements as points of the space-time. They will have an order relation which they inherit from the space-time. Then you throw the space-time away and try and recover the entropy just from the causal set itself. Okay, so we choose these points and get a causal set, and I've chosen to draw a few representative causal set elements. Here they are. The ones in red are below sigma, and the ones in blue are to the future of sigma. And from the and so these 4 regions of the continuum correspond to a partition of the causal set into 4 subcausal sets. And the first heuristic is identify horizon molecules in the causal set. So forget the continuum now. In the causal set, we want to identify small subcausal sets that could play the role of being horizon molecules. The horizon is made of them, if you like, and just count them. And then the second heuristic is identify plaquettes that comprise the horizon and certain states that each plaquette can have, and count those, and then take the logarithm a la Boltzmann. And again, I want to stress that we're seeking a universally defined entropy of causal horizon. So I'm not going to say that H is an black hole event horizon, it's just some causal horizon. So we want to have a universal definition of entropy. And this universality, or not, it has the potential, I think, to discriminate between different quantum gravity approaches. So if you hear someone say, oh, we have an understanding of black hole entropy in theory X, then you can say, does this tell you how to calculate the entropy of a de Sitter horizon? And I think that will discriminate between different approaches. I mean, I'm not saying that it should or it shouldn't, but and you may have your own opinion about that, but it does. It's something that may potentially discriminate different approaches. Okay, so here was the first attempt by Jamel Du and Raphael to identify horizon molecules. So this is heuristic 1. So again, this is the same picture. We choose these points that they have an order relation between them. They're divided up into 4 sub-causal sets, and then we take away the continuum. So we consider a causal set that's a random sample. It's a Poisson sampling. This is the only way we know, and it's a conjecture that it's the only way that it can be done to uniformly sample according to the volume measure, a space-time. And of course, choosing how to Poisson sample sets a discreteness length, L, and just think of L as being of Planckian scale, but we don't know exactly how it's related to LP. Then we propose the horizon molecules, and then the number of them will be a random variable in this sampling process. So success for heuristic 1 would be that in this random process, the mean of the random variable n, which is this number of molecules, is equal to some constant of order 1 times the area of the intersection between H and sigma, which we called, in our paper, we called it the joint, or in several papers, we've been calling it the joint. Whether or not that's a good word, I don't know, but that's, so it is the horizon, but it's H intersected with sigma. So the area of H intersect sigma in discreteness units, where this number is universal. It doesn't depend on what kind of horizon it is. It doesn't depend on what the space-time is, and it doesn't depend on what this hypersurface is. Up to subleading terms, in other words, terms which as L gets smaller and smaller, are less significant than this leading term. And the fluctuations around the mean should be small, so that if you just do one sampling, then and you count n, then it should be close to the mean. Okay, so Raphael and Jamel proposed that horizon molecules should be links from elements in minus minus, that's to the past of sigma and outside the horizon, to elements in plus plus, that's causal set elements which are inside the horizon and to the future of sigma. And a link is a nearest neighbor order relation. So it's a relation that's not implied by transitivity from other relations. It's a relation that you would draw on the Hasse diagram. And this proposal works for 2D Rindler and 2D dimensionally reduced Schwarzschild. It's universal for those two cases, but it fails, or it diverges for d greater than 2. And you might think that any definition of molecule, causal set, horizon molecule is bound to work. It's bound to give you something that when you count them, gives you something that's roughly the area of the joint in discreteness units. But it can fail. Oops. And this example shows that one way it can fail is that you get something which diverges. That it's just as you take the discreteness. It's not the discrete. It diverges when you take the region in which this little picture is embedded. As you take the cutoff to infinity, then you get more and more of these links, and it diverges. This counting.
Could you just say what the discreteness length L is? I just missed.
Ah, yes. So it's set by the density of the sampling. So if you choose to sample at a particular density, rho, say, that's the number of elements in a unit volume, but you have to say unit volume in what units. So a particular density fixes a particular unit of volume, that fixes the length, because the unit of volume is just that length to the power d. Yes.
The number of points in your causal set is finite, right? Then aren't the links also finite? What is diverging exactly?
So, well, in a finite volume of space-time, there's a finite number of causal set elements. But this, for example, if this were a black hole, if this were a Schwarzschild event horizon, then this would just be a picture of a small portion of the whole space-time, which would be infinite. So when you do the calculation, you have to do it in a finite box. But then when you take the size of the box to infinity, say in the Schwarzschild case, it diverges when you do that. That's the...
Okay.
Something being locally finite versus, countable. So it can be countable. A causal set can be countable, but it's locally finite.
Okay, so here's a different...
Sorry, can I just go quick? I'm
yes.
just a little bit confused over something elementary here. Namely, because in the beginning, as you told us that somehow entropy is a property of the horizon itself and not of any internal microstate. So I understood that to mean it doesn't really matter what is happening in plus region and so on. It's a property of that only. But now these links obviously depend on what is happening in right? How many... So the two things seem to be conflicting with each other. So can you explain?
It will crop up a little bit later.
Okay,
Let me.
thank you.
Yes, you'll see. It does depend on plus and minus, but only a little bit. So it contributes to subleading terms. So yeah.
But then, I could consider two different space-times, both of which have this horizon. But I come and just change the volume element way far away, from this horizon up here slightly. And so I would get these two causal sets. But then I'm going to attribute to it completely different entropies, even though in the neighborhood of the horizon, everything is completely the same. So then it's not a property of the horizon by itself.
Right. That would be the case if what you said happened, but what you said doesn't happen. So the structure of the causal set down here doesn't affect this counting. So which I'm going to show you why it doesn't affect the counting. So yeah. Okay, so here's a different proposal. So we have the same picture. Here's H, here's sigma. There's the causal set that's embedded in this continuum approximation, the 4 regions. And for this proposal, we restricted attention only to the causal set that's underneath sigma, so to the past of sigma. So it doesn't care what's to the future of sigma. Whether that's good or bad, I don't know, but this is the proposal. And the proposal is that a molecule now is, again, a link, as it was for Du and Sorkin. So it's a link between two causal set elements, P and Q. P is inside the horizon, and Q is outside the horizon. And P is maximal in the causal set. That means that between P and sigma, there is no other causal set element. So P is it's as close to sigma as you can possibly get in the causal set. And then Q, this is a definition. It's not something you can derive from anything. It's a definition, a proposal. Q is maximal but 1. So P is in its future, but no other causal set element apart from P is in the future of Q. Remember, we're just ignoring everything, all part of the causal set that's to the future of sigma. So below sigma, in the part of the causal set that's below sigma, P is maximal, there's nothing to its future, and Q is maximal but 1. Only P is in its future. That's the definition of the molecule. And what that means is that, so what does it mean for P to be maximal? Well, X is a maximal element, also a maximal element out here. It means that its causal future in the continuum has to be empty of elements. And if this is a random sampling at uniform density, then if this volume here is very small, then it's very unlikely that there's going to be an element sprinkled. But if that volume is very large, it's very likely that there'll be some other element chosen from that region. So whether or not X is maximal depends on what the volume is of its causal future below sigma. So this definition, it keeps P and Q in this link very tight to sigma, and the fact that P is inside the horizon and Q is outside keeps the link very tight to H. And in fact, it turns out that that works in the following sense. You can show by doing an analytic calculation that this, the mean in this random sampling process of the number of these links does it scale in the right way. So it's equal to the area in discreteness units times number of order 1. And in 4 dimensions, for example, that number is √3/10. And you can calculate it for this number for any dimension. There are subleading corrections. I'll say a bit more about that later. And it's universal. So it's for any space-time, any causal, so the space-time can be anything at all, any causal horizon, any sigma, and it only depends on D. Now, here's the subleading corrections as this is what Abai anticipated, because these links are not, they give the horizon, if you think of the horizon as being formed of these links, then it has a certain fatness, a certain thickness. And that thickness sniffs out the geometry to a certain extent away from the joint, so away from here. So this term here depends only on the geometry here, exactly on the joint. But because P and Q have give the horizon a certain thickness, then there's a subleading correction to this term. And the subleading correction is geometrical, it's not logarithmic, and it goes like this. So it's an integral over the joint of some linear combination of the scalar, of the extrinsic curvature of the component of that extrinsic curvature in the 1,1 direction. That's along sigma orthogonal to the joint, and the horizon expansion. And you can calculate these numbers B1, B2, B3 again and they're different in different dimensions, but they're again universal. So so the coefficients are universal, but of course K, K1, K11, and theta, they're not universal. They depend on the geometry away from the horizon. Okay. So let me come back to the logarithmic, not being logarithmic. Okay. So is this counting entropy or is it counting geometry? Well, you could just say, well, that's a nice way to read off the area of this joint, and it's just a geometrical thing, has nothing to do with entropy. I'm somewhat sympathetic to that criticism. Okay, so to go further and say that we can count something which has something physically to do with entropy, we need, first of all, a proper state counting, and secondly, we need a proof in the full quantum causal set dynamics of the generalized second law. So the sine qua non of entropy is that it should never decrease. If you don't have that, then you don't have an entropy. You might have some nice thing, but it's hard to justify that you call it an entropy. Okay, so let's try heuristic 2. All right, so if you look at the links that I defined before, for every link PQ that straddles the horizon below sigma, Q can only be linked to one P by definition, because Q has to be maximal but 1. So it can't have 2 P's in its future. It can't be linked to 2 of them. But each P can be linked to more than one Q, like this, for example. So you can have a link that's PQ1, and you can have another link that's PQ2. And in the previous counting, that counts as 2 molecules. Now, what we're going to do is lump those all together and call it a single molecule, and say that I'm going to call this a 2 lambda. So all the links that form the in inverted commas, the horizon that we had before, they form disconnected subcausal sets, and there's one disconnected subcausal set for each P. Sometimes that is just a link. Sometimes it's a 2 lambda like this. Sometimes it's what we called a 3 lambda, where there are 3 elements Q which are linked to a single P, etc. So there are subcausal sets which you can call n lambdas, which have cardinality n. Now, here's the heuristic coming into play. Let's consider the p's as the analog of plaquette. So each element p, which is the maximal element of one of these lambda molecules, is a plaquette. And the number of q's that's linked to it is the state of that plaquette. And if there are capital N p's, and there are m different states that each p can be in, and each different state occurs in a fixed fraction, then you can just count the number of horizon states, and it's just given by this combinatorial expression. And if you take the log of that, for large n, so I should have said this is an asymptotic expansion in large n and fixed fractions p. No, these are fractions f. F1 is the fraction of 1 lambdas, and F2 is the fraction of 2 lambdas. So you take the logarithm, then in the limit of large n, then it becomes n times the sum of over the number of over the states of fi log fi to the minus 1, and then there's a logarithmic term log n, and then there's a order 1. The next correction is order 1. Okay, I've run out of time. So you can run numerical simulations of this. You find good evidence that the states do come in fixed fractions. You can calculate S as log W. There is some evidence of universality so we can't do analytic calculations for this. I showed you before an analytic calculation. We can't do analytic calculations for this. We can only do simulations. And there's much still to understand, including this subleading term, which, although this looks like the subleading term will go like the logarithm of the area, it doesn't, because n itself has subleading terms, which are those geometrical corrections that I showed you before. Okay, so there are discussion questions. So this is my final slide. So in theories other than GR, the entropy of a black hole is not equal to its horizon. And for this type of proposal, this sort of small causal sets that straddle the horizon type of proposal to hold water, do we need to conjecture that the low energy theory of gravity is GR, and that higher derivative theories, for example, or F of R theories are not the low energy theory of gravity, even though they may be interesting to study? Is there a contradiction with semi-classical calculations which give logarithmic corrections to the black hole entropy? Or is the semi-classical ambiguity in these calculations, the ambiguity in calculating the leading term, which always requires some form of cutoff to be performed, is that enough wiggle room to reconcile these calculations? And will this identification of microstates of the horizon continue to make sense in a quantum theory of causal sets, in which we don't think that our continuum space-time is an approximation to a single causal set, but space-time will emerge from constructive interference between many manifold-like causal sets in the path integral? And more generally, how is entropy to be understood in a path integral framework for quantum theory, full stop? Not just quantum gravity, but any quantum theory. And then what about that generalized second law in full quantum gravity? I don't think anyone claims that we have such a thing in any approach. So, and with that, I'll just wish RRI a happy 75th birthday. Thank you. Sorry.
Thank you, Faye. Are there any questions?
Yeah, thanks for the talk. I'm somewhat failing to see the quantumness in this approach. Like entropy calculation is fine, I guess, but what about other quantum effects, like superposition? I'm not understanding. Is the uniform sampling taking care of the fact that geometry is superimposed, or what is the quantum effect really?
Yes, very, very good question. We don't know the answer to that, so that depends on progress. We must make progress in understanding quantum causal set theory in terms of a path integral, or it'll be a sum over histories, a sum over causal sets. So you're right to anticipate that that interference between causal sets in the full gravitational path integral will be important, may play an important role. So we don't know. I mean, in some sense, there's there's some kind of quantumness inherent in the kinematical proposal of causal set theory, because the discreteness is a Planck scale discreteness. So there is an H-bar in there already, but I'm not claiming that this is a full, this takes account of or does justice to the full quantum nature of causal set theory, and we don't have that theory, so I can't tell you, I can't answer your question today.
Also one more slide, sorry. In the black hole case, are you also sampling the interior in the sense that close to the singularity and all? Like,
no, we're not.
That exactly?
So in the case of just the link counting, we have an analytic result that says you don't need to sample away from the horizon. So you can sample just in the neighborhood of the horizon, and that will be good enough, because the definition of the molecules of the links, it keeps them very close to the intersection of the horizon and the hypersurface. So if you were to sample the rest of the space-time, then it would play no role in the counting. Those causal set elements that you sprinkle far away will never be molecules of the horizon.
Can you speak up louder?
It was off. So the subleading corrections also go with area, right? As you explained in the last slide. The corrections to the leading term also went with n, but because you didn't, the leading term was area by the link length to the power d minus 2, and because the Newton's constant is not fixed, so why can't I just combine? I think that's what you said. Why can't I combine both the terms proportional to n, and think of that as proportional to the the area term? I mean,
is this one you were talking about?
So I have this one which is going as n with the coefficients, with the f log f inverse, and the leading term was also proportional to n, I guess, right?
This is the leading term in this case. In n, it's leading in n, but it's not leading in. So n itself can be expanded, and the leading term of n goes like the area.
Exactly.
The next leading term in n goes like this surface expansion involving the extrinsic curvature.
And that doesn't scale with the area of the horizon, because it was integral over h intersection sigma, right?
It doesn't go, right, so let me, it actually goes like the square root of the area in some sense.
Oh yeah, because of the central limit theorem will tell you, right? The leading is going as n, then the subleading will go as square root of n, I guess.
Possibly, but you can do this exactly in the short shell case, because in the short shell case, for surfaces of constant, say, Eddington-Finkelstein coordinate, K and K11 and theta, well, theta is 0. They are constant on the joint, so they're constant on this surface, and they go like 1 over m. So the area gives you m squared divided by m. That's just m. That's the square root of the area. So the leading term goes like the area. The next leading term goes like the square root of the area.
Okay, thanks. Yeah. Just one more question. So when you compare with, for example, the Euclidean quantum gravity results of Ashok, I mean, it's important to know which ensemble we are in, because I mean, as Ashok has so shown now last year with his collaborators, that if you are in microcanonical ensemble, the coefficient of the log change. So when you do this computation, which ensemble?
Good question. Does anybody know? Probably. Yes, I think you're right. Yeah. Yes.
Yes. Yeah. Thanks for a clear and beautiful talk. As a first commentator, hit the nail on the head. I mean, where's the quantum in here, in part from a slightly heuristic H bar that's thrown in at some stage. So, and you started, of course, by motivating, let's say, with the standard heuristics. Look here, I have a formula with G and H bar. It must mean that this is about quantum gravity. But of course, we know that that is not true, right? Look at the Schrödinger equation and the Newtonian potential or something. Right? So could it be that it is just something semi-classical, and maybe also what you were saying, look, it doesn't really depend, the arguments you were making didn't depend in detail on any deep underlying quantum gravity theory. Well, maybe because they just don't. Or maybe we shouldn't even be looking for it. I mean, I agree with your last question. There might be something in the full quantum theory. But you're leaving this option open, or do you have an opinion or a heuristic expectation? It should tell us something about quantum gravity. I mean, that's what everyone has been repeating for, since the 1970s.
Yes, personally, I think that it does. I mean, that it's a good clue. I mean, I think I said to you before, if we were overflowing with real phenomenology, as in cosmological data that is just crying out for quantum gravity to come and explain it, then we may not pay so much attention to this, because, as I say, it's just on paper phenomenology. We don't have experiments on black hole entropy to test which sub-leading term, or even the leading term, right? So we don't have any such experiments. So in the absence of all this rich cosmological phenomenology, then I think it's fair to choose what we can as guide. So to me, it's a guide. That's it. Yes. Yes, of course. That can always happen. I agree, and it's absolutely a fair criticism to say there's not much quantum in it, and it is the major frontier for us in causal set quantum gravity to have a definition of the quantum dynamics. If Symmetry were not organizer, then she would be speaking here about state sum models for quantum causal set theory. So that there isn't. But Steve will be saying a little bit about the path integral over causal sets. But you're right that all of this may go away in the full quantum theory of causal sets.
In loop quantum gravity, we have a model of quantum horizon, which is a punctured sphere, and to each puncture there is inside infinite set of possible. I mean, it's assigned number, which is element of some infinite set, which is not necessarily equally distant. So what would you do is, if you would like to construct your approach from this quantum model, then you would somehow coarse grain our horizon, or how does this model fit your
the loop quantum
general theory?
The loop quantum gravity. Well, the little I know about it, and the experts, including yourself, who probably answer your own question better than I. But to my mind, the loop quantum gravity calculation has much more in common with this approach than sort of micro-state counting of D-branes in string theory calculations, in the sense that it's really a property of the horizon rather than a property of something inside. The heuristic picture is that you're counting the internal states rather than something which is a property of the horizon. So the loop quantum gravity calculation is a calculation about the horizon itself. So in that sense, this is in sympathy with that. Whether I don't know the answer to the question of whether it can be extended to all causal horizons. That's maybe, if it can, then it's even more in sympathy with this approach. I don't think that answered your question, but yeah. Okay.
Thanks for the very nice talk, and also thanks for this very first comment. I think it's quite interesting that I also would guess that many other classical theories of gravity don't obey that the area always increases. But so even if I just write down a patch of a semi-classical space-time which evaporates a black hole, then the entropy decreases. Your strict entropy would decrease, is that correct?
Yes, kind of by definition, because it's tracking the area, so it will.
And then
the black hole entropy will decrease. Yeah.
And would you then expect that a full quantum dynamics of the causal set rules out that geometry, or how does it account for it? Because you made that statement that if it's really an entropy, you would want it to obey the second law.
Oh, generalized second law. So generalized second law is that the total entropy, which is black hole entropy, plus the matter entropy, the entropy of the matter external to the black hole, cannot decrease. So if you include the entropy of the Hawking radiation, then together the entropy.
And you would expect that.
So what I mean by second law is generalized second law in that sense, the Bekenstein generalized second law. So yes, to me, I think, and this is what I called, what did you call it? Prejudice. My own prejudice is that the generalized second law is a good guide, is a guide to us in seeking a theory of quantum gravity. So.
And do you have an idea how the meta side of the generalized second law is going to happen in causal sets? No.
We struggle with matter because so far we can only put particles and scalar fields on a causal set. So yes, not in detail. So yeah.
Thanks.
So, oh, sorry, Abhay was going to say. Well, I'm not sure if what I was going to say is more insightful than whatever Abhay wanted to say, but you were saying that there is a lack of observational evidence regarding, let's say, the area law, right? You mentioned this several times. I just wanted to point out that there is work by Niesh Afshordi, I think, if I'm saying the name correctly, from a couple of years back, where they talk about verifying the area law by studying the gravitational waveform measured by LIGO. Now, how exactly they do that, I'm not sure, but I just thought I'd mention that there is some existing phenomenology which claims to validate the area law.
Yeah, I think we've already. Is it short, Abhay? Is it short or no? Okay, so discussion session. Yes, yeah, so let's thank Faye again. And I think there's a short break now until 3:30. Is that okay?
Yeah, we could either do that, or does everybody want a nice long break after this? Because we can have a nice long break and then wrap up by 6 if we can forego the short break, if that's okay. I mean, maybe 5-minute break, just like to get water, go to the loo. The coffee might take a little too long. Sorry, yes, Ananya. I'll just set this up. Thank you. Announcement before we begin this talk, and that has to do with the discussion session. We've been live streaming everything. We heard no objections. We told everybody, so I hope nobody objects to the live streaming. It's already done for today. But we were wondering whether there were objections to live streaming the discussion. Would people be okay with it? If anybody has an objection, please come to us during the big break time, and then we will, yeah. Criticize? Okay, so, okay, that's one, right. Sorry? Okay.
Younger people might feel more reserved if it's live streaming. So really should depend on the younger people. One day, if they think that there's no problem of their speaking up, we want them to speak up.
Yes. So anyway, think about it. You have about an hour and plus to think about it. And if you have any questions, come to me or Madhavan, and then we'll make a call. We'll just take a call. So either way. But yeah, please come to me after the talk and we can have a discussion about it, and then Madhavan and I'll just take a call on that.
Okay, so we're gonna have the second talk of the afternoon now, and if you didn't have time for coffee, don't worry, because the next speaker is gonna collect your attention. So Sumanta Chakraborty is going to tell us about probing quantum effects of gravity through gravitational waves.
Yes, thank you, and good afternoon to you all. I hope you have enjoyed your coffee. So I must thank Sumati and Madhavan for inviting me here, and also to put forward this very nice conference. And so many young people are here, so they can learn quite a few things from the world-renowned experts over here. So I came from the Indian Association for the Cultivation of Science, which may not be very well known to all of you, but this is the oldest research institute in India. And in particular, Raman Research Institute, which was founded by C.V. Raman, actually did his Nobel Prize winning work at the IACS, and the instrument which he used to get those results are still there at IACS. And secondly, this year is actually the 100th birth anniversary of A.K. Raichaudhuri, the Raichaudhuri equation. And the equation was also derived in the same institution. So, it's pretty good. I'm feeling proud to be from this particular institution. Anyway, now cutting back to the physics part of this talk. So what I'm going to discuss, we had several talks, where in fact Abhay mentioned that falsifiability of a theory is as important as giving a new theory. So I'm going to describe how gravitational waves can be used in order to probe quantum effects in the presence of gravity. In particular, I will discuss some of the results that all the quantum gravity people argued, like area should be discretized, how those results can actually be tested using gravitational waves. And so this work is not just a single piece of work. It has been done with collaboration with several people, including Ajit from in ICTS in Bangalore, Stefano Liberati from CISA. Then we have Sudipta Sarkar, who is going to speak in this conference, I think on Friday, and then Paolo Pani and others. So without any further ado, let me give you a brief outline of the talk. First, I will discuss why we should look alternatives for black holes, just for the younger audience. Then I will describe how quantum effects can be probed using gravitational waves. What are the observables that we can look for, and what are the implications that we can learn? And finally, what are the directions to look forward? So these are the two papers which are already published in this direction, and two other papers are work in progress, and we hope to sort of finish them in this particular month or so, and so we'll also state some results from those calculations as well. So first of all, we have been discussing with black holes and so on and so forth, so it is good to ask why we are so interested in black holes. To be honest, black holes are the simplest objects that you can construct, and you can actually construct them in very simple collapse scenarios, like the Oppenheimer and Snyder model, and then you can go forward to build more complicated gravitational collapse scenarios, and black holes are generic outcome of any such collapse model. Then black holes are unique, and they have very universal properties. We have been hearing this time and again. For example, if you are talking about static and spherical symmetry configuration, then you know Schwarzschild is the unique solution to your Einstein's field equations. And there are very interesting universal properties, some singularity theorems, area theorems, and so on and so forth, many of which you have heard today morning. Then black holes behave as thermodynamic objects. They have temperature, they have entropy associated to this. And as we have seen several times again today, and I guess we'll hear them again and again throughout this conference, that the presence of black hole entropy is a hint towards quantum theory of gravity. And whatever quantum theory of gravity you are pursuing, you always try to explain the black hole entropy, the 1/4 factor or its proportionality to area, and so on and so forth, including subleading corrections. And black holes, again, are stable under all possible perturbations. So this started by the Wheeler in 1950s, and then it sort of continued. And even though people have shown that the stability exists for scalar, electromagnetic, and gravitational perturbations to the black holes, but there are renewed interest whether the perturbations are indeed stable. In the sense like the quasi-normal modes, and which I am going to discuss in a few slides later, they sort of denote the stability of black holes, but are the quasi-normal modes themselves stable is a question that is currently being asked. And this is because the sort of the perturbation Hamiltonian, which governs this equation of the evolution of the perturbation, is non-Hermitian, and therefore that leads to generation of pseudo-spectrum and making these quasi-normal modes unstable. So for example, you never have someone isolated. I mean, for example, I am disturbing all of you with my talk here. So since everyone is in an environment of other people, black holes are in the environment of other galaxies, there is going to be environmental effects on the system, and that is going to change the quasi-normal modes. And it seems, at least the results suggest, that the quasi-normal modes move away more than what perturbation you probe on them. No, first order, but what you do, you have a QNM frequency, then you have a potential which is fixed like Regge-Wheeler or Zedili, and then you add the environmental effects which modifies the potential, and then you ask what are the new quasi-normal modes. So you find the difference between the older and the new quasi-normal modes is larger than the amount of perturbation that you have given. So that is also an active field of research. And another thing that is emerging right now is about the nonlinearities in the ring down signal, like whether you can really probe nonlinearity, like just what you asked, that whether second order effects can actually be probed, and that is also something which is currently being pursued. And then we have excellent results from the Event Horizon Telescope as well as from the LIGO and Virgo collaboration. In particular, the observation of shadow from the Event Horizon Telescope and the ring down signal from the LIGO and Virgo. And they are all consistent with the existence of black hole, but I am going to discuss that they are also consistent with other things, not just black holes. And I will completely focus on general relativity. I will not go beyond that, but you can of course ask what happens if I go beyond that, which maybe when we have 100 years of RRI, maybe we can discuss something on that. Okay. But as you know, I mean, always, I mean, if you have something very good, there must be some issues associated with it. So classical black holes, of course, have issues. So they have singularity problems. So all the classical black hole spacetimes have a singular region or singular point. I mean, until and unless you invoke some exotic matter, some very weird matter source like nonlinear electrodynamics and so on and so forth. And therefore, your theory breaks down over here. And as we have heard, resolving the singularity is one of the key motivation of studying quantum theory of gravity. Then there is a loss of predictability. I mean, most of the black holes, like the astrophysical black holes, for example, like Kerr black hole, they have Cauchy horizon. And as we know, if you are interested in what happens at a point beyond the Cauchy horizon, like what happens in the future of the Cauchy horizon, you cannot determine that from some initial data. I mean, that's by definition of the Cauchy horizon. And people generally get around this by citing the strong cosmic censorship conjecture. But there was a recent paper in 2018 which sort of showed that if you have a finite and positive cosmological constant, then this strong cosmic censorship conjecture can actually be avoided and you can extend your solutions beyond the Cauchy horizon. Later on, so the future cannot be determined, which is a very serious problem. So later on, there are several proposals, and ultimately Wald has given a prescription where he actually showed that if you include quantum fields into the background, and if you add back reaction coming from the expectation value of the stress tensor of the quantum field, that actually diverges at the Cauchy horizon, and thereby it restores the strong cosmic censorship conjecture. So therefore, you can see, even though something which looks pretty innocuous at the classical level, in order to clarify that, you have to go or invoke quantum fields in that background. Then of course we have this infamous information loss paradox, that is the existence of thermal radiation results into loss of information, and that also people try to invoke various other approaches in order to get rid of them. I mean, whether in loop quantum gravity or string theory and so on and so forth. So it would be very nice if we can have some alternative curing all of these problems altogether and yet remaining consistent with the experiments. And one possibility is that you get rid of the event horizon altogether, or you add some quantum corrections to the event horizon in whatever manner possible, and then you can see all of these problems are resolved. If you change your horizon structure, the information loss paradox can possibly be avoided. If there is nothing beyond your horizon, there is no singularity, and loss of predictability is not there because Cauchy horizon anyway forms beyond the event horizon. So that motivated people to look for is, have we really seen the event horizon into any of these observations that have been done so far? Namely, the event horizon telescope, the black hole shadow measurement, or the ring down signal of the LIGO. So that brings to this question, which Cardoso asked in this paper in 2016, is that does the existence of a photon sphere implies the existence of an event horizon? So just to be very clear, I mean, if you plot the potential that a test field is going to experience in a black hole background, you will see generically the field, I mean, the potential vanishes near the horizon. I mean, this is in the tortoise coordinate. So r star going to -infinity corresponds to your horizon. And it also vanishes at infinity, so r star tending to infinity. And in between there is a maxima which is there, and this maxima corresponds to the location of the photon sphere. I mean, of course, the maxima can slightly differ depending on the mass of the field, but generically, if you talk about the eikonal approximation, it very much matches well with your photon sphere for Schwarzschild, which is at r equal to 3m. And it was also observed, I mean, even much before, that the ring down spectrum has nothing to do with the black hole horizon really, it has to do with the photon sphere itself. So if I give you, for example, the real and the imaginary part of the quasi-normal modes can be obtained from the properties of the, yeah, please.
Sorry, is that statement about the ring down?
Which statement? This statement? Yeah.
Is the statement about the ring down also valid only in the iconal approximation, or is it valid also for the actual quasi-normal modes that we measure?
Actual quasi-normal mode, because we measure gravitational quasi-normal mode, and that is L equal to 2. So indeed, so L equal to 0 and L equal to 1 mode has some issue because there the ring down. So if you do scalar field perturbation and then you look at L equal to 0 mode, there it does not faithfully reproduce, but L equal to 2 onwards, if you compute, it very much matches. I mean, you do it numerically and you do it analytically using the photon sphere, the results are in very good agreement, I mean, to a percent or so.
Okay, thanks.
But you have to put ingoing boundary condition that.
Absolutely, absolutely. That is there. That is absolutely. That is definitely there. But I'm saying the values, for example, that is governed by the properties of the photon sphere. So as I was saying, that the structure beneath the photon sphere in that way cannot be probed directly. So the question is, can such object exist? Like, can you have an object which is larger in size than your black hole, like whose radius is larger than the event horizon, but smaller than that of the photon sphere? So then you will have exactly the same ring down. So you would see exactly the same ring down as LIGO has seen. You will see exactly the same shadow structure that event horizon telescope has seen, but it's not a black hole. I mean, it is something else. So the question is, as I was trying to argue, that can such objects exist and what will be their observational properties? So for that, the first proposal was about exotic matter. I mean, that's what people started with because you always get driven to something exotic. And Rai-Choudhury equation always guarantees that with normal matter you cannot cure singularities. So I mean, it's a natural thing to include exotic matter. And as I was saying, if you want consistency with observation and still not be a black hole, the radius of the object should be larger than 2m. I mean, just take Schwarzschild for example, and it should be less than 3m because 3m corresponds to the photon sphere. It turns out that actually you can get such a configuration even using normal matter. So this is a paper, I mean, this is a work that Bugdal did long back, and this goes by the name of Bugdal limit, which says this m over r, this is the compactness ratio of any object constructed out of normal matter, has to be less than or equal to 4 over 9. So you cannot go beyond that. Now you can say that, well, this is a very well valid possibility. So this is within 2m and 3m radius made out of normal matter. So it should be a valid alternative to black hole. But it was objected with the Sagittarius A star observation, because they argued that the Bugdal limit should be violated, since if you have, so what the idea is, you have a photon sphere and you have a horizon inside, and between these two you have a surface, you have a star, say, for example. And then there is accretion which is happening. So this accretion is not being properly absorbed by the black hole because it's not a black hole. So therefore there must be an outflow from the particulars, from the surface of the star. And this outflow, this event horizon telescope people claim that they should have observed if it is present, which they do not see. And therefore they argue that whatever that Sagittarius A star object is, it must be some object with a compactness which does not satisfy the Bugdal bound, and therefore exotic matter is necessary. But I would like to mention that this result, which the event horizon telescope collaboration quoted, depends on the details of the accretion model. For example, there is a paper later on by Stefano Liberati's group and Matt Visser, where they argued that actually if you change the accretion flow to some extent, you can actually get rid of this bound. So therefore it's not, you should take it with a pinch of salt. But then what I am going to discuss is not about exotic matter, because I guess all of you will come down if I say matter is exotic, since it has various difficulties. The most difficult part is to make things stable. So if you have a rotating exotic object, which is something you expect, then there are many instabilities, and the most important of it is the Ergo-Region instability, and which is sort of tied up with the super radiant instability that we have for rotating black holes. So instead of a black hole, if you have a star, then what happens? You have a photon sphere at one side, you have a star at one side, so there is like a cavity. And the cavity can actually resonate. The waves which are going to be absorbed by the black hole are not now being absorbed, but they can sort of they can travel back and forth between the photon sphere and the surface, and therefore the energy can build up, and this like a structure like a black hole bomb or something. So therefore these instabilities are present. People are of course clever, so they can play around with parameters and make the time scale of instability as large as you want, but the instability is there. So then we tried to ask the question, can quantum effects play any role? And I think in the last talk there was a comment about the Niesh Afshordi's work, and this is from his group, because he was the first one to point this out, that what happens if we include quantum effects into the system. So I will discuss two particular sort of model for driving the point home. The first model was given by Ivan Agul. It's not his model, but he sort of prioritized it. So the idea is that area quantized black holes, which we have heard several times in today's talk, are generic predictions of theories of quantum gravity, which I guess we'll all agree, and they have non-trivial physics at the horizon. So they sort of tried to give how to model this area quantized black hole and whether there can be any observational signature of this in the gravitational wave signal. So effectively what everyone does, these are some of the references which discusses this in somewhat detail, is to modify the horizon by a reflective membrane kind of a structure by taking into account all these quantum effects and then seeing what is going to happen out of it. So all of this result will turn down to a reflection coefficient that is present over there, and whether you can measure it or not. If you can measure it, there would be some parameters associated with it, and those parameters would be related to your quantum theory of gravity, and therefore you can use gravitational wave data possibly to constrain. So I will show in which context it can be done. So this is sort of the basic picture again. So you have the angular momentum barrier over here, and this is in the tortoise coordinate. So this is your infinity and this is your horizon. And so you have an outgoing wave at infinity, because that's what generally happens, and you have an ingoing wave at the horizon. So these factors of delta and r with this 2s minus 1 just comes because of boundary condition in the Teukolsky equation. But let's not get into those mathematical details. Now when you go to non-black hole objects, whether is it some star made out of exotic object, maybe it is some quantum effects taken into account, you have effectively some surface over here, and that introduces a reflective coefficient. So therefore there is not just an ingoing part here, there is also a reflected part which is present. And you can guess what is going to happen is that earlier in the black hole case, if you are standing at infinity, you will just see this outgoing part to be present. But now due to reflection from the surface, just like you have an outgoing part, this reflected part will also come in, and it will come in a repetitive fashion, in the sense that this reflective part will hit this angular momentum barrier, a part will tunnel through, but the part will be reflected back, which will again reflect from the surface and come back and again leak towards infinity. This is like a leaky cavity kind of a system, and if you are observing it from infinity, you will see several pulses coming towards you, and this is what is referred to as the black hole echo. In the sense, the black hole, from black hole you are getting repetitive pulse with a time delay, of course, and the time delay is given by the time it takes for the signal to travel from the angular momentum barrier to the horizon and back. Please.
What is the exotic matter? I mean, could you not just have a regular star and
yeah,
a
but
similar effect? Or I mean,
no,
I've lost some key thing that you said, so I'm sorry, but
sure.
Yeah.
Let me.
What would be the signal of it being exotic here? I mean, what
Sure.
would be the sign of it?
Sure. So first of all, as you can see, I mean, the main point is this angular momentum barrier. So if I take Schwarzschild black hole, for example, this resides at r equal to 3m, right? So therefore, we want some object whose radius is between 3m and 2m, right? Now you try to make such an object with normal matter. Now the best you can do is the Bugdal bound, but if you sort of take the result by the shadow people, I mean, you know, with confidence, then they say that you can, the Bugdal limit has to be violated. Because if there is a star of the Bugdal size, there should be outflows present, and which they claim they should have seen in the signal.
That's a particular, I mean, that's a particular class of observations, right? I mean,
Yes.
The Bugdal bound is theoretical, so.
Yes. So the point is, if you have any star, I mean, its radius has to be larger than that. It cannot be smaller than that. And if the radius is larger than that of the photon sphere, then, I mean, there is no ring down. I mean, you should have seen them in the LIGO. Because the ring down effectively is governed by the angular momentum barrier alone. So if you want it to be consistent, this angular momentum barrier has to be there, and it has to be smaller than the angular momentum barrier. But again, it cannot be larger than Bugdal bound, and which is because it's ruled out. So therefore, if it is smaller than Bugdal bound, exotic matter or quantum effects are the only possibilities. That is. So, okay, I don't know why these are not appearing here, but let me still explain. I mean, so the point is, let us restore some units, and I will try to argue why gravitational waves can act as a magnifying glass. So I hope there are some chalks here. Yeah, sure. No, I can do it here. Yeah. So the change in area, for example, is LP square. I mean, that's the basic we always have. So let us suppose there is a process in which a black hole absorbs a gravitational wave, and its area changes by an amount LP square. And let us assume non-rotating black hole. So for a non-rotating black hole, the change of area would be simply 4 pi into 2m whole square. And therefore, you can, the area would be 4 pi into 2m whole square. And therefore, the change of area, you can relate to the change of mass, because that corresponds to a change of mass. Change of mass can be converted to a change of energy, and hence a frequency with which the black hole is going to absorb that. So that frequency that the black hole is going to absorb, the frequency in hertz, say for example, this actually goes as 1 over mass, but there would be c cube over g which is present. So if you plug in all the values over there, like the value of c, g and m. So for example, if you take m equal to 10 solar mass, this frequency turns out to be about 32 hertz. And the operational range of LIGO is from 10 hertz to a few kilohertz. So therefore, you can see this frequency lies exactly within the frequency band of LIGO. And that means the gravitational wave that you are seeing in the LIGO can actually come from a change of area which is of order LP square. So therefore, the gravitational wave observation can actually measure things or measure changes in the area of the event horizon down up to the Planck length. And that is what I am going to argue, that using that particular result, and this result was actually from the Ivan Agullo's paper, because they were the first to point this out. And as I was saying, this is precisely in the LIGO frequency band. And therefore, gravitational waves actually act as a magnifying glass in order to see quantum effects near the horizon. And actually the information of Hawking radiation is also encoded into it. So how? Because these are discrete frequencies, as you can see, if you take delta A to be LP square, but normally you have a spread into the lines, and the spread in the line corresponds to the spontaneous emission from the black hole, which is the Hawking effect. So therefore, you can actually predict how much the spread would be. I mean, I will show you how exactly it appears into the observables. And therefore, the information about Hawking radiation is also encoded into the frequency or the frequency spectrum that we are going to observe over here. So that is one of the main point. And if you are sort of feeling sleepy, maybe after this slide is done, you can go to sleep, because I will sort of summarize what I am going to discuss next. So there are three main avenues which I am going to discuss for the quantum effects at the horizon. So first one is, of course, the quasi-normal modes or the ring down spectrum. The second is the tidal love numbers, which corresponds to the deformation of a black hole or any compact object against external tidal field. And the third is the tidal heating associated with the inspiral regime. So one observable from the ring down and two observable from the inspiral regime. So for quasi-normal modes, there will be significant deviations at late time. I will show you exactly how. But these are difficult to detect in the present generation of gravitational wave detectors, because we can only detect first one or two overtones which are present, late time behavior. The tidal love numbers, on the other hand, hold a high hope for us, because it expected to show a log epsilon behavior, where epsilon corresponds to the distance between the surface of your object and the location of the horizon. So for example, if you are interested into quantum gravity, this epsilon could be of order LP, and as you can anticipate, even if LP is very small, its log is not necessarily a small quantity and can in principle be observable. But people were not very happy, because it appears at the 5th post-Newtonian order, or V to the 10 in the phasing of the gravitational wave, and therefore may not be a very significant effect. What we have shown recently, and this is the paper which is work in progress, is that this result is not really correct. What happens is that the tidal love numbers really behave as a power law in epsilon and not as logarithmic, and therefore you can expect that it is a power law, means, I mean, it goes as LP, so all hope of getting anything out of tidal love number is not really there. So I will discuss in detail how that is arrived at. So then the only hope that is remaining is with tidal heating, and I think this is sort of something which can give us some concrete answer, because it starts at a very high value of post-Newtonian expansion, namely at 2.5 pn, that is V to the 5 order, and it may be more important in this particular context. So these are the three cases which I am going to discuss, and just to say it, I will show that this is the most important among the two, and why and how, that I will describe in detail. Okay, so let us go to, yeah, please. Yeah, so here?
Yeah.
Yes.
So you were talking about these like Planck mass absorptions by the black hole, for Planck mass quanta, not Planck mass, sorry, Planck length squared area addition to the black hole, and that signature being observable for like 10 solar masses, which is not that bad. Like we have observed 5 solar masses, black holes and all that.
Yeah.
So, but my point is that that would correspond to a very small mass, right? It falling into the black hole, and that would be happening all the time in the black holes that we've already
small mass in the sense?
Of the quanta that are falling in.
Yes.
Black holes already have that quanta falling in constantly, right?
Yeah, but I mean, normally you do not take those environmental effects, right? So the idea here, as I will describe, is like you have two black holes which are moving around each other. So gravitational waves are being emitted. So a part of the gravitational wave is going to impinge on one of the, or both of the objects actually, and they are going to absorb that. So that will change their masses, and that will affect how the evolution happens. And that is going to affect your signal, which you are going to see. So this absorption of the incoming gravitational wave, so that is this frequency, right? Because this is the frequency at which gravitational wave is being generated and is being absorbed by the black hole. So the point is, if this type of frequencies are there in your gravitational wave spectra, they can make a change of the area which is of the order of LP square. I mean, if you have a higher frequency, it will make higher amount of change, but at least up to order LP square are also present into the signal. So you hope to see them in the waveform as well.
Yeah, but my question is, presumably, even in binary systems, a lot of matter is just falling in. Like,
yes.
An area is changing in units of LP square. And
yeah, of course.
So they should already be there. Yeah.
No, they are already there, but you are not observing them, right? You are observing only the gravitational wave. How can you observe where matter has fallen into a black hole? Right? I mean, maybe many matter is falling into the Sagittarius A star right now. It is accreting, right? But we are not observing it right away. We can observe it into the gravitational wave signal, and that's where we are seeing it. I mean, you can see it in electromagnetism, like people do in accretion, but that will not correspond to this change of area. Maybe we can talk about it. Thanks. Okay. So again, as I'm trying to tell you, that what I am going to tell you is a general overview with some models put into it, because just to make the context clear. So besides the area quantization, there is another model which I am going to discuss, which is the membrane paradigm way of explaining exotic matters. So it was started, as you all know, from the Richard Price and Kip Thorne's seminal work. So the idea is that you have a black hole, but since you are standing outside, like all of us, it does not matter whether it's a black hole or not, but you can replace it with a membrane, a fictitious membrane with certain properties. So what are the properties of the membrane? You describe an energy momentum tensor to it with an energy density rho, with a pressure, but with viscosities. There is a shear viscosity eta and there is a bulk viscosity zeta. And this eta and zeta can take very specific value if you talk about black holes, like 1/16 pi, 1/8 pi, and so on and so forth. Now suppose it's not a black hole, it is some other exotic object maybe. What can happen is that maybe this rho and p, this eta and zeta, they are going to be different from that of a black hole. So the idea is, if you can construct some model or some quasi-normal mode, say for example, you have to parameterize them in some way with this eta thrown in, say for example, and this zeta being set to whatever the value for the case of a black hole. Then you have a one parameter family, and you can actually check whether this eta value actually corresponds to that of a black hole. If it does not, then that means the object from which you are seeing the reflection or from which you are seeing the ring down is not really a black hole per se. So that is the idea which was put forward by this paper by Paolo and Elisa in 2020. And we sort of took it further and introduced some quantum corrections to it. I mean, of course, semi-classical, not quantum gravity. So the idea is, in the classical context, you have the junction condition, that is the change in the expression for the Kb, the extrinsic curvature, is related to the matter energy momentum tensor on the membrane, which is written over there. And you just simply change it to expectation value of TAB and use some very simple model. You do not go to very complicated model, in the sense you assume that the membrane is constructed out of small harmonic oscillators which are fluctuating and so on and so forth, so that you can compute things explicitly. And it turns out that your R, which is the location of the membrane, is not at the horizon, but like slightly shifted from the horizon. And then you can sort of try to find what happens to the perturbations by studying the perturbation of the corresponding junction condition, and which looks like this. So after you all that, and if you just consider the axial perturbation, this is the final expression that you get, which may look messy, but let us look at some limits, then it may be more clearer. So let us suppose you are interested at the limit when you go to the horizon, that is your capital R goes to R plus. Then you can see your f vanishes, because f is 1 minus 2m over r. So when r is 2m, this f vanishes. So the whole term over here identically goes to 0. The potential, the axial potential, which is the Regge-Wheeler potential, it vanishes at the horizon. So therefore there is no contribution from this term either. So therefore you only have a contribution from the derivative of the psi and psi. And as you can see, the solution of this equation is psi being e to the power plus or minus I omega x, one of them, and that corresponds to ingoing mode at the horizon. So therefore, in the limit when r goes to r plus, that is when this membrane is sort of exactly at the black hole horizon, you get back what you expect for your black hole, that is a perfectly ingoing boundary condition at the horizon. But otherwise, what you have is, instead of a purely ingoing condition, you also have an outgoing wave which is present with a r which is correspond to the reflectivity of the membrane. And that is the key feature, and that's the key thing that we are interested in. So this R will dictate whether you are looking at a black hole or not. For example, if you compute this R under certain approximation, you can see the leading order term is 1 minus eta over eta black hole divided by 1 plus eta over eta black hole. So when your eta goes to eta black hole, that is you are looking at a black hole, then it identically vanishes, and reflectivity being 0 means you have a purely ingoing boundary condition at the horizon. So this automatically comes from the structure of the reflectivity. And sigma here is the additional quantum corrections that we had added. So a sigma tending to 0 and eta tending to eta black hole is your classical black hole limit, and you recover 0 reflectivity in that case. So what we have done here, we have plotted the reflectivity with the frequency. I mean, this the omega m is the dimensionless frequency. And if you look at the typical frequencies which LIGO measures, like omega m of order unity, then you can see if you have eta to be equal to eta black hole, the reflectivity is extremely small, like 10 to the minus 10 or so. But if your eta is different from eta black hole, then you can have reflectivity as large as 1 or maybe 10 to the minus 1 and so on and so forth. So with such a high reflectivity, you may expect there would be significant deviations in your ring down signal, and that is precisely what we see. So here what I have plotted is the wave function with time, and then you can see that there are echoes which are present, so in the logarithmic scale. So normally it should have just gone down without any changes, but there are amplifications which are present. The amplification goes down, again there is an amplification, and again there are other further amplifications. So this happens because, as I said, because of the cavity effect. There is a surface at r equal to r plus plus epsilon. There is a photon sphere. The wave goes, hits the surface and comes back to the photon sphere, and then you see the signal again. So this corresponds to the time delay which is present, and you can see this time delay is independent of the choice of eta. This only depends on your sigma which is present. So for all choices of eta, you get the peak at exactly the same time delay, and same over here. This peak and this peak appears at the same time. Here you cannot see the peak because the amplitude is small, and therefore the effect is not very prominent. But when your eta is different from eta black hole, you can actually see it. So the moot point is that if you can see waves, gravitational wave ring down up to a longer time scale, I mean, we have actually seen only the first few oscillations in the current generation. So if you can see it after a sufficient time scale, and if you see such peaks present in your GW signal, you can really say that we are not looking at a black hole, but we are looking at some object other than black hole. Whether it's a quantum black hole or whether it's some exotic compact object, that of course requires further elaboration, but at least that much can be answered from the quasi-normal mode analysis. And in particular, you can see it depends very much on eta. So if in future we have such a model, we have such signals in the data, we can actually constrain what value eta can take, and since this eta depends on the interior geometry, so it is actually related to some of the quantum gravity property, maybe what happens inside, what are the microstates, because these are responsible for the calculation of eta near the horizon. Then I come to the area quantization, and I'm sorry, again for some reason some numbers are missing which I can just write over there. So the simplest possibility is that the area is integerly quantized, so there is some parameter alpha which is present, and there is LP square, and then there is n. And LP square you can again expand and so on and so forth. So you can take exactly the same stance as before, so you can compute the change of area. So change of area would be related to change of mass and change of angular momentum if you are looking at a rotating black hole. And you can also say angular momentum is quantized like square root j into j plus 1, and therefore you can compute what would be the frequency for a certain change of the area quanta. Like if you go from capital N to capital N plus small n, what would be the corresponding change? And that is given by this result that omega n is kappa over 8 pi, there is a n alpha, and then there is 2 omega h. So you can see that it of course has to be related to kappa because the coefficient in front of delta m is related to surface gravity. Then you have a alpha, which is this coefficient over there. The n corresponds to the number of transitions that it has made into the area. And the 2 omega h comes from the angular momentum because you assume that angular momentum transition is from j going to j plus 2. 2 because in gravitational wave we are interested in the L equal to 2 mode, so that's why this is only up to 2. So that means your frequencies which you are going to observe or which the black hole is going to absorb are discrete, and they start at a minimum frequency which is related to the angular velocity at the horizon, and then it sort of increases with proper steps of small n. And this model was sort of considered by several authors, including Cardoso and later on by Shyok and others. And so you have to model it, the reflectivity appropriately. So one model is to use some square potential barrier, and you can see that the amplitude is decaying, but sort of the levels are equally spaced. This is one way of modeling. The other way is to sort of put whatever happens there explicitly, that is, it behaves like a classical black hole at exactly these particular frequencies, which comes up over there, and with a certain width which corresponds to the spontaneous emission, and that is related to the Hawking radiation. So this width comes from the Page's calculation. And with this input, you can calculate again what happens to the time domain signal, and you can easily see that depending on the boundary condition, like whether you use this type of a approximation or you use this type of approximation, you get different results, of course, but the features are same. So you have some initial wave, and then you have an echo of the initial wave appearing repeatedly. So again, we have only seen this part of the spectrum, so LIGO has not seen any of this because it's not sensitive enough, but hopefully in the future all of these results can actually be verified, and we can say whether we are actually seeing area quantization or membrane paradigm or something else, but that's a long-term goal. So that's why I said right now QNM is a very good possibility and very clean signal, but I mean it may not be possible in 20 years or so. So let us now go to tidal love numbers. So just a few basics about it. So for black holes, tidal love numbers are identically 0, and that is something which have, people were very happy to say that what happens if things are not black holes. So why it is 0? I mean, I will just show you the idea in a moment, but the point is you have the G00, I mean take Newtonian mechanics for example. So G00 is 1 plus 2 phi, and therefore you can expand it into a tidal part and a Qij, which is the quadrupole moment part. And the relation between the quadrupolar deformation and the tidal field is what corresponds to your tidal love number, which is called the lambda. So I will skip this ambiguity slide. So anyway, so since nothing is appearing here, so let me discuss what was there in the previous slide. So what was happening is that the tidal love number has some ambiguity, in the sense it was defined with the r to the power 3 and r square kind of quantities. So therefore people tried to get a gauge invariant definition of the tidal love number, and that was achieved by only in 2021 by using Weil scalar. So we have heard in today's morning that Weil scalar are really good things to talk about, and because they are scalar, they are gauge invariant and so on and so forth. So instead of expanding the Newtonian potential, they tried to expand the Weil scalar, and from there they read off the coefficient of the falling powers of R and growing powers of R, and from there they computed the tidal love number or the response function. And this is the result that they obtained. Let us forget about this term for the moment. Let us look at the first piece here. And you can see there is clearly an I factor sitting over there, which means that the real part of the quantity, the first quantity, is identically 0. And that is why this is the result for a Kerr black hole, and that's why for Kerr black hole, tidal love numbers are identically 0. Just to put things in context, I mean, these tidal love numbers were only known for slowly rotating black hole. There was a paper by Poisson which explicitly stated or proved that it is 0. But for arbitrary rotation, there was no result as far as I know. But this particular approach of using Weil scalar to get the tidal love number sort of settled it and said that this has to be 0 even for arbitrary rotation. Weil scale is psi 2? Psi 0 or psi 4. Okay. Then we tried, this is with Sudipto Sarkar, who may not be here now. So, so what we tried is what happens if you have a non-zero reflectivity of your system, like for compact objects. And then you get this extra piece, which has this B over A ratio. This B by A corresponds to the reflectivity. So, and the gamma 1 and gamma 2 are some complex functions. So, in general, depending on the reflectivity, you can get non-trivial value for the tidal love numbers. Afterwards, what we did, we sort of moved to the de-Wheeler function, just because the Tucholsky function does not define plane waves properly. It has this r to the minus 2s minus 1 and delta to the minus s kind of coefficients present. So we tried to go from Teukolsky reflectivity to Detwiller reflectivity, and using that, this is the result that we obtained for the case of a love number with a non-zero reflectivity. So you can see that except for r equal to 1, for all the other reflectivity, including r equal to 0, which corresponds to black hole, you can see which is a straight line over here as it should, it always vanishes. I mean, it of course is non-zero for finite frequency, but other than that, it always tends to 0 in the static limit. Only for the case r equal to 1, it has a finite value when you go to the static limit. And this is explained by this result which we had derived, that in the static limit, that k2m is related to this particular combination. And if your r is equal to 1 plus I omega r1, then you can see this 1 cancels this 1 over there, and the I omega is cancelled, and you get a finite result with a negative number over there, and which is precisely being reflected at this level as well. Please.
Calculation based on the Y scalar.
Yes.
Is it understood in relation to the work of Binet and Poisson?
Yeah, but that was for the case of, exactly, but that is exactly the same, since those were done in the static case. I mean, not for the rotating.
Slowly rotating.
Slowly rotating, but that is already contained here, right? Because if you take slow rotation, just that these factors can be ignored, because this p plus depends on a square. So even if you ignore to leading order in A, you can see that they are 0.
So I'm sorry. So you're
Sure.
talking here about the perturbations, side 4,
Yes.
side. Oh, so that's what I confused about. Okay,
Yes.
These are perturbations, not
Perturbation.
the background. Yeah,
Not the
the Kerr background thing itself.
No, this is just the perturbation, psi 0 and psi 4 of the perturbation. Yeah. And then what we found is that this result, which is the final result of our finding, it goes as a power law in epsilon and not as a logarithmic. And this has to do with various weird things, like in the strictly zero frequency case, there are different branches of solutions compared to when you do the dynamical case and then take the zero frequency limit. So let us not get into that. So let me skip all of this, but let us go to tidal heating. Thanks, since I have 5 minutes left. So let us discuss what is tidal heating. So as two compact objects in spiral around each other, as I said, the tidal field of one affects the other. So there are two objects which are moving across each other. There is a gravitational wave which is being generated, and both of them are absorbing that gravitational wave. And as a consequence, their mass is changing, and as the mass is changing, their orbits are getting different, and therefore that is affecting the amount of gravitational wave that is emitted, and there would be effects in the phase of the gravitational wave. And so effectively what you compute, change in horizon area, change in mass, and change in angular momentum. And these modifications are related to the boundary condition, because anyway you have to solve some equation, which would be Teukolsky's equation always. So therefore it depends on what you put at the boundary, whether you put an ingoing boundary condition or whether you have a reflective boundary condition at the horizon. So all this calculation is going to change depend on that. So for example, if it is a black hole, it is going to absorb everything. So therefore rate of change of mass would be higher. If it is a reflective surface or maybe a quantum black hole, it is only going to absorb selectively. So therefore its rate of change of mass is going to be different, and therefore its evolution will be different, which will affect your GW signal. Yes.
Which is hotter in this sense? You're saying tidal heating, so
Black hole would be hotter because it absorbs more. Yeah. So, so effectively we follow the Hawking and Hartle's approach. I mean, in 1972, so you may be more familiar with their quantum cosmology work, but they had a very interesting paper on how null generators modify the horizon area. And in particular, this is the result directly from their paper. So what they do, they have a sigma, the shear, in the Hartle-Hawking tetrad. So normally Teukolsky's equations are written in the Kinnersley tetrad, which are not well behaved near the horizon. So Hartle and Hawking introduced a new set of tetrad which are well behaved near the horizon. And using that, you can compute the rate of change of area. And the sigma can actually be related to the Wild scalar, because the perturbation of the Wild scalar, and that comes from the Teukolsky's equation. So after you put all of those in, this is the final result for the rate of change of area of a black hole that you get. So you can see the individual masses are there, B corresponds to the separation of them, chi1 corresponds to the dimensionless rotation parameter for the black hole. And we just did it with the electric charge thrown in, but I mean, you can also put Q equal to 0. But what matters is the change of mass. So you can relate change of area to change of mass and change of angular momentum by some integral I of theta naught. So this sort of follows from the work by Kip Thorne and Alvey in late 2000. And this is the final result that you get for the rate of change of mass. So first part is the standard d dt that you get. Then you can see there is a term at order v to the 5, and that's why I was mentioning that tidal heating starts at 2.5 pn, because the leading order effect comes at v to the 5 and is proportional to the rotation and the spin orbit coupling of the system. And then there is a v to the 8 term comes due to the multiplication. So for non-rotating object also there is a tidal heating, but that only appears at order 4 pn. So armed with all that, we tried to ask the question, what happens for a quantum black hole? And this is in general the phase that we will have. So you can see there is a, forget about this 1 by v to the 5, which just comes from normalization. There is a v to the 5 term with some log v correction. The psi 5 and the psi 8, which is appearing over there, these are the terms which includes the correction coming from the area quantization. For example, the alpha parameter is embedded into them. So the question is, if we have such a phasing, so in the GW we have a point particle phase, we have a phasing due to tidal deformation, we have a phasing due to this tidal heating. So we can add all them up and see how it matches with what we have seen really in the LIGO. So that part we are still yet to do, but we have done some simulated run whose results I am going to describe now. And again this Q, the result is sort of has a minimum value 2 omega h, because if you see I have presented over here, so it only starts absorbing from 2 omega h. There are no energy absorption beyond that. And at maxima it is bounded by the ISCO frequency, because beyond ISCO it's not really in spiral, the plunging phase starts. So you cannot really trust this calculation beyond the ISCO frequency. So you have two cutoffs, one is this 2 omega h which comes from your quantumness, and the upper one is ISCO which comes from the physicalness of your system. So these are some plots of the reflectivity for various choices of alpha. So this corresponds to the total mass of the system, which is 26 solar mass. This is the mass ratio, which is 7.6, and these are the two spin value of the two companions. So you see when alpha is very small, like 0.001 or up to 0.1, they all overlap. I mean the individual levels, they all overlap. So that's why you just see a continuous line at the top. But when alpha becomes larger, like alpha equals to 1, you can see all these small lines which are appearing. So they are 1 at exactly those frequencies, and at other frequencies they are just 0. If you take alpha equal to 10, which is an even larger value, you can see there is one peak which is appearing over here, which is this 2 omega h, and then there is another peak which is appearing over there, and there are no other peaks which is present. So therefore, depending on your choice of alpha, the reflectivity contributes very differently. Smaller the alpha, the better it is towards your classical black hole. Larger the alpha, the sparse is the spectra. Here I have done the same thing, but with the different choices of the spin parameters. So the spins are different, as you can see. So in that case, even for alpha equal to 1, you can very easily see the overlapping effect. So for alpha equal to 1, you have one peak over there and another peak over there. So that means these two separated lines which were present here, they overlap. On the other hand, for alpha equal to 10, there is just one peak which is present. So with all that, you can compare what happens to the case of a quantum black hole and what happens for the case of a classical black hole. So this is the phasing that you get for a quantum black hole with frequency and for various choices of alpha. For small alpha, you get a continuous like line which mimics that of a classical phasing. But the only thing is classical phasing has no lower limit, but the quantum case there is a lower limit at 2 omega h, and then it sort of continues. And this is the case of a equal mass ratio, just to show you the differences. So where you can see the difference between the QBH. So the two lines comes because there are two black holes which are present, and this is the corresponding classically expected curve, so which is very different from what you get from the quantum nature. So I cannot show you the statistical analysis because that is still under progress, but what we are finding is that the larger values of alpha are very difficult to constrain, like alpha equals to 10 or 20 is very difficult since the distribution is almost flat. But if you take smaller values of alpha, like alpha equals to 6 up to 6, we have some good results, and things are more or less going towards smaller alpha for some reason. And as Abhay mentioned that from cosmology he is getting around 5. So we would be very happy, to sort of see, how GW and cosmological results sort of tally with each other to give a value of alpha which is consistent with other observation. But as I am saying, we are using a small range of prior, like alpha from 0 up to 6 or 7, because if we go beyond that, the results are not at all convincing. But for the moment being, but hopefully in the next generation of detectors, like in the Einstein telescope or in the case of DESIGO, these things can be much more improved. So the reason is the following, which I will come back to. So the reason is these results are most important for the intermediate mass black holes, which we have not seen in LIGO, and even if we have seen, we have only seen the merger and the ring down part. Since this inspiral for this intermediate mass black hole happens for smaller frequencies, and that is precisely what DESIGO and ET are going to probe, like the frequencies of the order of 0.1 hertz to 10 hertz. This is the ratio, this is the band which is important. And if we have those inspiral regimes, maybe we'll have better data and maybe we'll have better constraint on alpha from this. So therefore, just to summarize, the tidal heating, as I said, appears at 2.5 pn, but even there are rooms, like there is a 3.5 pn term, which Poisson and Nico Yunes had obtained earlier. On the other hand, the recent result by Alessandro Buonanno did not find the 3.5 pn term. So therefore, there is a controversy what happens to 3.5 pn, and therefore, if you add a 3.5 pn term, maybe the analysis would be much more robust in that context, because it adds more meat to the corresponding phase. And then if we can actually probe the plunge phase as well, not just the inspiral, because the plunge phase will also capture these effects, then maybe we can move beyond the ISCO frequency and we will have more data, because the gravitational wave signals are more prominent beyond ISCO. Of course, till some point, till the linear analysis or linear regime is valid, maybe that will also enhance the constraint on alpha to a better value. So with this, I will conclude. So I have shown that models of quantum black holes imposes reflective nature on the black hole horizon, and there are echoes in the ring down signal. So there were 3 separate avenues I explored: the ring down part, the tidal love number part, and the tidal heating part. The QNM show a echo kind of a structure, but on the other hand, this appears at a late time and therefore may not be very easy to detect with even future generation of detectors. The in-spiral part is more interesting because this is something we have a better handle on, but the tidal love number seems problematic, since earlier expectation was that we have a log epsilon and people were excited, but now it seems it's not really log epsilon, because the dynamical case should be considered, not the strictly static case, because everything is dynamic in the observation at least. On the other hand, the tidal heating looks the most promising among all the 3, because it has a phase effect, and indeed the change between, and it appears at a much lower post-Newtonian order. So hopefully, if not with the present generation, at least with the future generation of detectors like DESIGO and ET, we'll have a much better constraint on the quantum gravity parameter. So I guess this sort of summarizes what I have to say to you today. So just like cosmology can be a very interesting probe, the early universe cosmology of quantum gravity, gravitational wave also poses a similar probe. And there are other avenues also. For example, the multipole moment is also an avenue to probably test theories, like there are the various fastball-like solutions, and people have been trying to get their multipole moments, and hopefully, since they're anyway different from the car, maybe at some stage they can be constrained as well using the gravitational wave observation. So I thank all of you for your attention, not being sleeping, and thank you very much.
So very interesting work. My question is that in realistic cases of astrophysical black holes, the black holes also have spin angular momentum, and they need not be aligned. If the spin angular momenta are not aligned, then as they come closer, there would be precession. So they would affect the phase of the inspiraling. So how will it interfere with the quantized area results that you're getting?
Okay. So first of all, I have taken rotation, not just very small, but in this case like of the order of 0.1 or like in the previous plot even up to 0.4. So rotations are taken into account. And the tidal heating, if you see the first term here is actually a spin orbit coupling term. So it's a coupling between the orbital angular momentum and the spin of the individual particle. So that effect is there, but what you are saying is precession, I mean that only appears, that only appears at higher PN order. So that we have not taken into account because we are just interested in the leading order behavior. But I agree that if you want to do a full comparison, then you need that. But the problem is the following. You see, I mean, we need to have the least number of parameters. So the best thing about this model is that I just have one parameter which is alpha and I can play around with it. But if I have alpha, if I add eccentricity, if I add other spin precision, then I would have too many parameters and I will not be able to get any constraint at all on alpha. So maybe alpha equals to 5 corresponds to some spin precision equal to 0.3 or something. So that degeneracy somehow we had to break. So we took the minimal choice where you only have masses, spins and alpha, right? So that we can get some idea. But I agree, I mean in a full picture we need to add all this.
Yeah. So I think you already answered partially, but if I just look at the tidal heating term, and if I just said, okay, I modify it by a phase, which is starts kicking in at 2.5 or 3.5 PN order, is it, I mean, could I not have some other theory of gravity which would also have some phase? How would I know that it only comes from area quantization with alpha? But I think you are saying because it's independent eccentricity, etc.
Eccentricity is different, but I think the main problem is as follows. So let me explain what the main problem is with other theory of gravity. So first of all, you have to give me a Teukolsky-like equation in other theory of gravity, which in my knowledge does not exist except for GR. So for example, even rotating solutions in, maybe,
the way people, the way I think in LIGO people are looking at alternative theory of gravity, they're agnostic about the theory itself. They just put some modified phasing term, etc.
But those phasing terms only appears at higher PN. I mean at 2.5 PN, it's only the tidal heating, and that's what we have taken, right? So I mean, I would have loved to see what degeneracies are there, but the problem is in a rotating case, getting a separable equation is, I am not sure whether it's at all possible. So.
Yeah, I have a similar question I had about the generacies which you had there, because I could modify the the properties of the black hole, the mass, the spin, I take a different. So at the end of the day, it's a bit unclear to say if it's a modified gravity, if a different astrophysical quantity. So the problem is much more complex than just changing. So I mean, because you try to somehow to test a particular model.
Okay, let me answer this, maybe it will be. So we took mass, spin and alpha all as free parameter. We have not assumed that mass is that given by LIGO or spin is that given by LIGO. So for us the M1, M2, Chi1, Chi2 and alpha all are free, and we are just fitting all of them from the data. We are not assuming anything for the masses or spins.
So at the end when you wanted your here, I mean, whatever, any of those.
Yeah, but these were not the, real statistical runs. These were just to show that there are differences.
There are differences. That's why I'm saying you can change something there, the mass, the spin, the whatever, and you can mimic the results with a different value of alpha. So at the end of the day, there is a degeneracy there by definition. I mean,
Yeah, absolutely. But the point is there are two main differences. One is that this region, for example, there would be classical effects, but there would not be any quantum effects present.
Certainly, but I could mimic this effect by changing something, either the gravity theory that you took or the parameters, the intrinsic astrophysical parameters of the model. So I could mimic the same thing with a completely different value for alpha, because at the end of the day, you said you want to put a constraint on alpha. But what I'm saying, you see what I mean? There is a degeneracy there. So
I completely agree with you. I mean, at this level, I completely agree.
I talk about what you saw. I don't know.
Yes. But what I'm saying is that the next plan is to take masses, spins, and alpha all as free parameters. I'm not saying that my mass is what LIGO has measured or my spin is what LIGO has measured. I'm trying to constrain them separately.
I was talking about the plots you saw.
Yeah, here I agree.
That's a story you didn't present. I cannot make any comment. But from what I see the degeneracy. That's all.
Sure, absolutely.
Thank you.
No questions. Yeah. Please.
I'm a little bit. Can you show us again where alpha was defined again? Because I just.
Yeah, so it was in Psi 5. So the way Psi 5 is defined is exactly this V to the 5 term, and then you multiply it by h of f, and this is your h of f. And this h of f
But
depends.
alpha must be somewhere, no? I mean, alpha by itself.
Yeah, because so.
What
I mean,
alpha by itself?
The alphas were in the
there,
frequencies.
In there. Okay, I said that. Now, so the main point is that your assumption is that area spectrum is kind of
absolutely
discrete. And
yes.
For example, in loop quantum gravity, that's not the case at all. It's not like a simple harmonic oscillator. It crowds exponentially. And this is something that we showed a long time ago.
Yeah.
And so, therefore, for solar mass black hole, for example, or even for a centimeter, for a black hole with a centimeter radius, the splitting is not going to be anything like Planck length. I mean, it's going to be incredibly minuscule. I mean, very, very, very 10 to the minus some huge number times Planck length, or e to the minus huge number times Planck length.
If I may, so the change in area is always LP square, right?
No,
because
the change in area is from one area eigenvalue to the next eigenvalue to the next eigenvalue, and those exactly those are crowding exponential.
Okay.
So I think what these effects they rule out. I think that they will rule out actually the quantization of area, which is along the line of n alpha.
Yeah.
But if they really don't test anything in theories like loop quantum gravity, where the area crowds exponentially. The separation between, exactly what you are saying is the key point, that the difference between the area eigenvalue, consecutive area eigenvalue, or even 10 eigenvalues, so to say, is exponent, some huge, e to the minus some huge factor. How much huge? When if it is 1 centimeter squared, then it's 10 to the minus 66 times Planck length. That is the reason why continuum limit is so good in LQG. So those things, I think, will not be tested by these kinds of experiments.
Possibly.
Of course, this is like the Bekenstein-Mukhanov idea of this equal area spacing. And those, I believe that Largo will pretty soon rule them out, actually.
Yes.
So, and there are many proposals to do that.
But just one note on this context is that, I mean, as I was saying, this is just a model. So for example, if we do not see such corrections, that will say black hole is the final thing. Like the exotic compact object domain can also be ruled out by the same logic, because ultimately we are,
exactly. So. Yeah, I mean, as you were saying in answer to Marie's questions, that with alternate theories, we really don't know how to do the calculations.
Yes.
So therefore, it is difficult to.
Exactly.
So you can just parameterize them and put bounds on the parameters, but that's all we do. The second thing is that in the beginning, you mentioned something about the instability of quasi-normal modes.
Yes.
But of course, you use quasi-normal modes all around.
Yeah.
And so I just want, I mean, some people might be confused about this because if they're unstable, then how can you use them? Because realistically, I don't know that these are the quasi-normal modes.
Exactly.
So I just wanted to clarify something, and maybe somebody else wants to make some remark about this. This instability of quasi-normal modes was something that was being very nicely discussed, started with the old work.
Visheshwara.
No. Instability, no.
I think Visheshwara had a paper in 2007 where he actually discussed this instability. I mean, not 2007, 1995. I think after that in 97, Nolan and they had the paper, but yeah.
Right. You're right. Yes. So Nolan and Price and then everything. But I think, in order to make them okay, there are two different issues. Here you're only talking about the principal quasi-normal modes.
Exactly.
You're not talking about the
overtones.
The overtones, exactly. So for principal,
they are stable.
They are stable, except if you have perturbations which are extremely high frequency. And this came because of Nolan thing. He was approximating the potential
delta function
by little step functions up here and so on and so forth. And they, in order to approximate better, they had to make it very high frequency.
Yes.
And so that I think is true. That one could rule that out. But there is no astrophysical process which will actually prepare such high frequency perturbations.
I just have a comment is that, I mean, recently in 2021, there was a paper from Jaramillo, Macedo and
I'm
others.
talking about Jaramillo's work itself.
Okay.
And just recently, a month ago, there was this meeting in Copenhagen in which these things were discussed in great detail. And And Jose Luis Aramillo actually he agreed with us that there is no astrophysical process which will actually create the kinds of perturbations that are needed in order to make the principal quasi-normal more unstable.
Correct, absolutely.
What happens with overtones is a different story, and we can talk about it in great detail. But since you didn't mention overtones, maybe we should not get into that. Overtones, I think those effects are important. But for the principal ones that you're talking about, they're really not important at all. So, so I think they are stable. There's no problem about that.
But there is just one comment is that this result is true in asymptotically flat case. If you add cosmological constant, then actually the fundamental modes also gets destabilized.
Let's talk
this
about that. I think
okay, sure.
So just one last question, if you still okay. Then if not, I think now is a good place to stop. Let's thank someone.
Thank you.
So quick announcement. So we'll have a longish break now. We'll try to come back exactly